to for further proceedings, please.
Absolutely, sir. Good morning, good afternoon, and good evening to all the participants. So, we shall move on to the 10th technical session of ICSTC 2022, which is to be chaired by Dr. A. Loknathan. Now, Professor Loknathan is a former professor of statistics from Manonmaniam Sundana University, Tamil Nadu, India, who had been in the teaching profession for over 2 decades. His area of specialization is Bayesian inference in finite mixture distributions, and he is deeply interested in the domains of finite mixture distributions, acceptance sampling plans, life testing and reliability theory, as well as cluster analysis. He has over 40 publications to his credit, including Bayesian reliability sampling plans under the conditions of Rayleigh inverse Rayleigh distribution, published in the International Journal of Economics and Quality Control, as well as single sampling plans by variables under the conditions of exponential distribution, published in the Journal of Statistics and Applications. Professor Loknathan is a recipient of the Young Scientist Award by Tamil Nadu State Council for Science and Technology and is a life member of Indian Bayesian Society, Calcutta Statistical Association, as well as Indian Society for Probability and Statistics. He has also played a major role in the designing of new curriculum by serving the Board of Studies of MSU, AU, as well as University of Madras. And it is with great joy and honor that I invite you, Professor Loknathan, to chair the session. So over to you, sir.
Thank you. Thank you for your good words, Dr. Ranjana. Let me thank first Dr. Satish Kumar and his team for organizing this kind of an international conference and having given me this opportunity to chair this session of a great statistician, Dr. Barry C. Arnold. Let me, Professor B.C. Arnold, now the time is 9:16. They said we can go till 10 o'clock. And let me introduce, of course, Professor B.C. Arnold is known for everyone. However, I am given an opportunity to say a few words about Professor B.C. Arnold as a little bit introduction. Of course, it is not an introduction, yeah, forward. Professor Barry Arnold is a distinguished professor of statistics, emeritus at the University of California, Riverside. He obtained his MS degree in the year 1963 and a PhD degree in statistics in the year 1965 from Stanford University, California. His main research interests include estimation theory, probability, stochastic processes, order statistics, mathematical learning, and biological models and characterizations. He is a fellow of the American Statistical Association, American Association for the Advancement of Science, Institute of Mathematical Statistics, Royal Statistical Society London. He is an elected member of ISI Netherlands. Professor B.C. Arnold is or has been on the editorial boards of many reputed journals, including JASA, Journal of Multivariate Analysis, Sankhya, Communications in Statistics, Metron, and several others. He has published around 300 papers and 10 books. Let me, this is a brief few words about Professor B.C. Arnold. And now I invite, on behalf of the organizing committee of ICSTC, I invite Professor B.C. Arnold to present his keynote address on the topic, a characterization miscellany. Professor B.C. Arnold, over to you.
Thank you. See if I can do this right. But that didn't work. Okay.
Bottom there is an upward arrow. I hope can do upward arrow. Yeah, now it's coming. Yeah, now you can choose the file presentation.
Well, let me stop sharing. Let me see if I can find it. Oh. It didn't come up. Oh,
Yeah,
wait a
now
second.
it is coming, Professor. It is coming. But this no, yeah, some other, whether it is the part of the presentation,
It's not.
we can go to the
Stop
file.
sharing.
Yeah.
Ah,
Barry, I have
Window.
an idea.
okay.
What you can do is you open your presentation file first and then click on the upward arrow button and choose the window, and the talk presentation file will be there. You can click on it.
Trouble is, I don't find an upper.
The bottom, if you go to the screen in the bottom, there will be an upward arrow button in a square. After the 3 vertical dots, there will be an upward arrow button.
I'm going to wait a second. Let me start again.
It is
Yeah.
starting. Let us see.
Okay, now I want to present it to everybody. Now, share. How do I get a share screen? A window.
Professor, you can keep
You
your
can-
file open.
No, sir. You choose the upward arrow, then enter screen you choose. Click on the upward
Yeah.
arrow, then
Oh, now,
please,
shouldn't I be able to open that?
yeah.
Sir, Professor, please open the file first.
Yeah. Now, yeah, it's better to open first.
You can open the file.
Now you can open and then no problem.
Double
It's
click.
better open first.
It's okay. Double
You
click.
can double click it.
Let me stop sharing. Now I want to share again.
It seems you have not opened that presentation file.
Yeah, yeah.
Now, I present a window, right?
Yeah.
Okay.
And then now I look in here and I have presentation B. I have Charlotte, the link to it. The presentation B twice, but I can't get it to open.
Probably you are opening that PPT file, isn't it? Not in the.
If it is convenient, otherwise the organizers can receive the file and operate.
No, please send to me so that I shall.
Sir.
Nikhil will.
Professor Barry Arnold, if it is convenient to you, you can share that. You can send the file to the organizer. Let them open it. Otherwise, if it is convenient to you.
Sir.
Okay, that's
Professor, we received the file. We shall share it from here. Professor Barry?
Yeah,
we
I'm just
received
gonna
the file.
That's
Yeah,
fine.
I'm coming back.
We shall share from here. You just say the commands to Nikhil. He will move the files. No problem. Professor, we can, anyway, we have a little bit late, not bother about that. We can manage the time. Please give maximum time to Professor.
Sure.
Okay. Can you hear me?
Yes, we hear.
Yeah, we can hear you, Professor. We can hear you.
You know, I tried this out yesterday and it worked fine. I don't know what's going on. It just won't open up the last time I did this and was able to open it
Really?
by just clicking on this.
Yeah, it is now. Yeah, you are trying to open it.
It doesn't want to open.
What happens? Okay, Professor, if you are trying to open, it is not possible for us to share from here.
Okay, now can you show it for me, or can I control it when you show it, or do I have to have you?
Okay, Professor. And if it is, whether you, which is more convenient, if it is not convenient from it, anyway, please stop the sharing and we can, or otherwise, okay. Yeah, Professor, is it okay?
That's it. Yeah.
Visible.
Can I change the pages?
No, Professor. Here, Nikhil will change the page as per your command. You just say next or previous or whatever be. You can give the command. He will obey. Will do the needful. Is it okay for you?
You have. How do we change pages? You have to change the pages for me.
Yeah,
Yes,
Professor.
yes. They will, you can direct them. They will move the pages.
You just speak from there, Professor.
Well, I can speak, but how are the pages going to change?
Yeah, you can change from here, Professor.
Oh, okay. Well, okay. I don't know how am I going to tell you when to change a page?
You have to just say
next.
Yeah.
Next, okay, is what I'll say. Okay. Let's do. Can I start again? Back to the beginning.
Start again. Yes, start again.
Okay, here we go. All right.
Okay.
Thank you, Satish, for inviting me. Can you all hear me?
Yeah. Yes.
Yeah, you can hear
We
me.
hear.
Okay. Sorry for all this chaos.
Okay, Professor.
I think I'll have to shoot my computer.
Yeah.
Everybody can hear me? Okay.
Yeah.
Look, thank you, Satish, for inviting me. And I'm going to talk about characterizations. Next. And I thought about an alternative title for this, which was going to be a truckload of characterizations, but I was talked out of it. It sounded too facetious. So I switched back to the characterization, to the title that I gave you. And I'm going to start out with the question of why characterizations. Whenever you submit a paper which involves characterizations, it's almost certain that an editor or a referee is going to say, why do we care about these characterizations? This is just a mathematical game, nothing to do with statistics or really of no use whatsoever. Well, I don't think that's completely right. Next, because first of all, they help us to greatly understand the consequences of common distributional assumptions, and they might be useful for testing distributional assumptions. So let me talk a little bit about that first possibility. Suppose you were trying to model, this is an old example, but it's a good one to illustrate the utility of characterizations. Suppose you're trying to model the distribution of heights and weights of the students in your university. And you go out and get a sample of students, and you measure their heights and weights. And you look at the data, and you sort of notice that if you looked at all the people who were about 5'10", their distribution of weights was kind of bell-shaped, almost kind of normal. And if you looked at all the people who weighed 180 pounds, the distribution of their heights was also kind of bell-shaped. Pretty good approximation of normal. So you might immediately say to yourself, well, I think I can go here and assume that I have a nice bivariate normal model for this data. But be careful, because what you've done is you've convinced yourself that the cross-sections of the joint density are normal, or bell-shaped, if you wish, but in both directions, with cross-sections parallel to the axes. And that is a property of the bivariate normal, but there are other distributions that have that property. In fact, an old paper, 1943, by Anil Bhattacharya, identified all of the possible distributions that you can encounter which have normal conditionals, but many of them are not actually bivariate normal. Some of them have more than one mode. Some have three. So you need to look more carefully at your data. Now, you can stick on some additional conditions. For example, if you just assume that one of the regression functions is linear, that would be enough. Or if you assume that one of the marginals was normal, then that would be enough. Now, that second one you might check by just doing a histogram of all the data thrown together and just plot a nice histogram. And if it looks bell-shaped, then that's pretty good evidence that the marginal is going to be normal. And you could go ahead and use your model. Well, one of the things also is once you recognize the utility of these things for understanding what you really are assuming when you make your assumptions for the model. And if you assume bivariate normality, you're assuming more than just normal conditionals. You're assuming more than that. And these things, these characterizations might also be useful for testing distributional assumptions. I'll give you some examples of that in a little while. Next.
Yeah.
Next. I think they're fascinating and sometimes surprising, and you beat me to it. Finally, I think they're kind of fun, and we should have some fun in our lives, especially during COVID. So I'm doing a favor for you. We're going to have some fun here. Next. Okay. I'm going to start out with a couple of old results that I'm sure you've seen before. One of them, suppose that we have two random variables that are IID with finite variances, and if for some constant C, the distribution of the sum is effectively a scale change, or it's in the same family, same scale family as the distribution of x1. So that the only thing here is, and now we assume finite variances. Now, if we do that, we can quickly decide that actually by looking at the variances that C must be 1 over root 2. And then after you've decided that, you can quickly decide that in fact, the means of these things must be 0. And then, next, then you can actually convince yourself that that thing, now you skip over, then you could convince yourself that the distribution was actually standard normal distribution with mean 0 and variance sigma squared. And the proof of that, it uses the central limit theorem, okay? And you could use that as a sort of a crude test of normality of a data set, because you could divide your data into thirds and add pairs to get one set and look at the single observations for a second set and compare the histograms of those two. And that would be a quick and dirty check to see if you had normality. What would be important is if the histograms were radically different, then that would be strong evidence against normality. So in some sense, the characterization might be used not so much to identify the distribution, but to identify cases where it doesn't have a possibility of being true. Now, a parallel result where instead of sums, we look at minima involves the exponential distribution. And that's not an unusual situation. Sums and products work for normal data, and maxima and minima show up for extreme value data. So the fact that we have a parallel result for extreme distribution, namely the exponential, is not surprising. It says that if the minimum of 2 independent observations, except for a scale change, is the same as the distribution of an individual observation. Now, C bigger than 1 is obvious, because if C was less than 1, there would be no chance of this being true, because the minimum is always less than or equal to x1. It has to be boosted up to have equality. But if this is true, then you can iterate this thing, and next you can draw the conclusion Next. I know you have a terrible, and I apologize for putting you through this, because it's very hard to be sort of paying attention and then missing the occasional next. Then in this case, we have an exponential distribution. You caught that one though. Okay, now what I'm going to do now is talk about a potpourri of results that probably you haven't already seen. Okay, next. Next. First of all, we're going to think about characterizations that are motivated by the nexus between convolution and size biasing for exponential variables. Now, I have to explain that word. I kind of like an opportunity to use the word nexus, but it confuses a lot of my audience members. What happens is that if you take a convolution of two independent exponential random variables, what pops out is just a size bias version of the exponential distribution. It's a very unusual property to have that convolution being identified with effectively size biasing. It's also the basis of what's known as the inspection paradox. If people are looking at, for example, a Poisson process or some renewal process, and which has exponential lifetimes, then if you look at the item that's currently in service, the lifetime of the item in service is twice as long, and roughly speaking, as the usual distribution of a lifetime, because the item in service, if it's an exponential distribution, still has an exponential distribution of time in its remaining lifetime. And if it's far enough along in the process, its age is probably going to be approximately exponentially distributed too. So the size of the interval associated with the item in service currently is actually like a sum of two exponentials. And that's a classical result that people have enjoyed, but people have made mistakes with it. That people have done sampling where they in fact did, one of my favorite examples of that is if you want to figure out how long people stay in a hospital, you run into the hospital, you grab a person gently who's in the hospital bed, and you ask them how long they've been there, and then you keep track with the nurse to let me know when they get out. Okay, and you add the two together, and that's the amount of time that person spent in the hospital. If you do that, you get a very, very large bias in favor of longer stays in the hospital. Okay, now a second thing we're going to talk about are size bias convolution pairs of densities, because the fact that f and g, two density functions, when convolved, yield a size bias version of one of them, is a very special situation. It's true for the exponential, but there are other cases where that happens, and I want to investigate that possibility. Next. Next. And then we're going to look at records and linear combinations in the continuous case, and the same thing in the discrete case. The key thing here is that if you have records, sequence of IID exponential random variables, for example, then the sequence of interarrivals of the records are again IID exponential. And so effectively the sum of the first two records is just a linear, has the same distribution as 1 plus 2, x1 plus 2x2, which is a linear combination of exponentials. That's an unusual property, and we're going to look at variations on that theme in the continuous case. Now, turns out, for what we're going to look at, the discrete case is easier than the continuous case. Now, that's unusual for records because, typically speaking, records, when you go to the discrete case, life becomes a little more complicated because of the possibility of ties. But for our applications, we're going to find this is the case. Now, throughout this talk, we're going to also think about the discrete version of the exponential distribution, namely the geometric distribution. And whatever we do for the exponential distribution, we're going to try and do the same kind of thing for the geometric distribution. Next. Okay, now that's a tall order, all that stuff there. And what I had in mind was that we'll see how far we go, and we'll, we won't be able to get all of it covered, I don't think. Next. Okay, in fact, I timed a trial run of this talk the day before yesterday when my microphone was working fine. And I decided afterwards that I better concentrate on the characterizations motivated by the convolution size biasing thing and leave the other items for another day, and that's what I'm going to do. It'll still take, I'll use up 45 minutes of your valuable time, but we'll just focus upon this. And if you're at all interested in the other, well, maybe I'll meet you at some other conference, or maybe if you send me a note, I can send you a copy of the material that you're going to next. Next. Wish I had some other way to say next. Most of the results that we're going to talk about are joint work with my friend and colleague, Jose Villaseñor, who's in Colegio de Postgraduados in Mexico. Next. Next. Okay, we're going to talk about convolution size biasing. And now we skipped a slide there. Back. Well, okay, we'll skip it. Okay, here we go. Okay. This is a slide to indicate notation, right? We're going to use X's for the IID observations. We're going to use SN for the sum of N of them. We're going to use Laplace transforms. That's the right thing to use for positive random variables. We don't have to worry about existence. We don't have to worry about that moment generating function only existing in a neighborhood of the origin, etc. And we don't have to use characteristic functions because sometimes they lead us into sort of shaky areas where we have to figure out how to do integration of complex functions and have to do contour integration. All kinds of things like that can complicate our lives. If we're dealing with non-negative random variables, Laplace transforms are exactly the tool to use. Now, just to remind you, a convolution is just defined in this fashion, and you can think of it as being a situation where you ask for the probability that x plus y is equal to x by conditioning on the value that y takes on. That's a statement that only makes sense in the discrete case, but the formula effectively is valid when you replace summations by integrals. And so it's a valid thing. Okay. And a size biased version of a density is just a density of the form x times the density. And there's also a concept of a weighted density where you have a more general function than x. So we'll run into that too. Next. We know that for the IID exponentials, we've beaten this to death, that in fact S2, the density of the sum of two of them, is a size biased version of the density of one of them. Next. Can you see that little thing that blocks my screen when I put it on there or not? I hope not, because whenever I try to point at something on the screen, this little oblong thing comes up and sits on the screen. Okay. I claim that property is in fact something that holds only if they are exponential. Next. Next. Okay, now the idea is that you use the Laplace transform. Since we have S2 being a sum of two IID random variables, its Laplace transform is just the square of LX1. And then using the definition of the Laplace transform of the weighted version down here, we can recognize that it is just minus c times the derivative of LX1. Next. So that gives us a nice simple differential equation which even I can solve. And during the playing with this material, I had to go look up my old differential equations book, which I bought when I was a student at McMaster a few years ago, 1958. But fortunately, differential equations has not changed much since 1958. The general solution of this is just given by here, k plus s over c to the minus 1. But we can also remember that a Laplace transform at 0 is always equal to 1. And also, for that tells us that k is equal to 1. And we can immediately see that we have an exponential distribution. So that characterization was quite simple. Next. Next. Okay, we're going to, after seeing that result, we're going to have many possible parallel results that suggest themselves. Next. Next. Oh, no, that's not next. How did you get there? That's way back. Okay, where are we? Okay, I think. Okay, that's where we were now. Go to the next one. Next one. Some are easy to prove. Others are a bit more challenging, and others are only as yet conjectures. Now, when I present this material, I think that some of you will be kind of, tired of it after a while. But what you can do is you can keep track of the conjectures that I make that are still open. And while you're either sitting there or tonight when you're, watching TV or something, you can resolve some of these conjectures for us. And we'd love to hear from you. And now another thing too is as we're going along, it would be kind of hard work for you to write down the conjectures as they show up. And if you are interested in trying to resolve some of those conjectures, send me an email and I'll send you copies of these slides so you can figure out what are the things that I left unproven. Okay, next. Okay, that says perhaps you'll be able to solve them during the next few minutes. That's kind of optimistic. Next. Now, here's one variation. Suppose that we have same setup, IIDXs, and we define Sn to be the sum of them. And let's suppose that the density of the sum of k plus one of them is a weighted version or a size biased version of the density of a sum of k of them. But in this case, I claim that we will still have an exponential distribution, but now it will be a parameter 1 over ck instead of 1 over c. Next. Okay, again, Laplace transforms are the tool. We set up our equation, and you'll notice that in this equation, remember that L sub x1 to the k plus 1, that's the Laplace transform of sk plus 1. And notice that there's a factor of k minus first power of L that you can cancel out, and lo and behold, you get the same equation. Once again, we have exponential. Next. Okay, now here's another possibility. Suppose I have f composed, the convolution of f and g is equal to a size biased version of f, where I tell you that g has an exponential density. Okay, I claim under those circumstances that f must have a gamma density. Next. Okay, once again, Laplace transforms, because we write down the Laplace transform of f star g, which is just a Laplace transform of f times, now this is an exponential Laplace transform. The other one is our old familiar friend, minus c times the partial derivative of L of the Laplace transform of f. And the equation we can solve to get 1 plus s over lambda to the minus alpha, where alpha is positive. So what we have is that f must be a gamma density. It could work for any alpha positive. So it's much more, not just exponential solutions, but gamma solutions are possible. Next. Okay, now let's see what happens if we change. Okay, instead of having a size bias version, which just had the weight function of x, what if we try x to a power? We'll start off, baby steps first. We'll start out with c equal to 2. So suppose we have two IID random variables, and suppose that the distribution or the density of their sum is equal to cx squared times the density of one observations. Okay, now it turns out in this case, I cannot prove that these things are going to be have a gamma distribution with the shape parameter 2, unless I make an assumption. I assume that the variance of x1 must be equal to 1/2 the square of its mean. That's a property that the gamma with shape parameter 2 has anyway, so we're not surprising, but we need to assume that. If you don't assume that, I think that there will be solutions here that are not gamma distributed. I'm not sure. Okay, so next. Okay. First of all, we know that it's true that double star property holds for a gamma distribution with shape parameter 2. And then if we assume that double star holds, then we can very quickly determine that C must be the reciprocal of the second moment. And then we have a Laplace transform. Using Laplace transforms, our condition becomes a little more complicated than before. It's the second derivative of the Laplace transform. This is L of S is the Laplace transform of the individual x's. And that's going to be equal to mu 2 to the minus 1 times the square of the Laplace transform. Now, that's a little more complicated differential equation. Okay. Now you can work on that, and we'll be able to prove. We'll be able to solve it. Next. But it requires a couple of steps, and eventually you'll find that we do get a Laplace transform of a gamma distribution with shape parameter 2, an arbitrary scale parameter, okay, or intensity parameter if you prefer to use that. Okay, so next. Okay, now, after we, here's another conjecture for us. After we see that result, it's inevitable, I think, that you would like to consider the following unimproved conjecture. Suppose that the convolution of f with itself has as its density function a weighted version of the density, the individual density f, okay, and the weight is instead of x or x squared, it's x to the alpha, where alpha is some positive number. Well, we expect under those circumstances that we should have a characterization of the gamma distribution with shape parameter alpha. We also expect that we probably have to put in some regularity conditions involving moments, perhaps, but except for that, and they should be fairly benign ones, probably conditions about the first and second moment that are already satisfied for a gamma with shape parameter alpha, then we will have the result that we want. Now, next. Okay. I think we missed something, because what I did say is that last result we were not able to that was a conjecture. We don't have a proof for it. Okay. And we know that the result works for the case of just one and two for two observations. However, I'm going to look at a more general conjecture that follows next, which I know works for n1 equals 1 and n2 is equal to 2. We're going to take our sequence of IID positive for absolutely continuous random variables. We're going to let Sn be the sum of the x sub i's, okay? And we're going to look at two numbers, n1 and n2, n1 less than n2. And if that's the case, if there was exponential distributions, it would be the case that Sn2, the density function of a sum of n2 of the observations, is a weighted version of the density of a sum of n sub 1 of the observations. And the weight function is x to the n2 minus n1. We know this result is true when n1 is equal to 1 and n2 is equal to 2. Okay? And we think that that's going to be true for any n1 less than n2. Okay, next. Okay, we might have to put in some additional regularity conditions on moments, but so far that result is just a tantalizing one that we cannot quite nail down. However, there's better results available in the discrete case. Okay, remember I pointed out that the exponential distribution has as its partner the geometric distribution. My geometric distribution has possible values 0, 1, 2, 3. It's the number of failures that precede the first success. And you know that there's a nice little result that says that if you have an exponential distribution, you can represent it as a limit of a sequence of scaled geometric random variables. And so that allows you the possibility sometimes of proving a result for geometric random variables and using it to get a sort of a cheap version of a proof in the continuous case for the exponential distribution. So it's worthwhile looking at the discrete case, even if you don't think that you will have that many uses for it. You might only use it just to get insight as to what's going to happen in the exponential case and to possibly give you a nice way to prove it. Next. Okay, so we're going to have, in the case of geometric distributions, we almost have the very same thing about size biasing being the same as convolution. Let me write down the formula for that. Next. Okay, here's what it is. If you have x1 and x2 on negative integer valued random variables, and suppose that we have the density function of the sum, okay, independent ones, is essentially just a biased version of the probability X1. To be a perfect parallel to the continuous case, you'd have just K here, but to make it work out right, you have to put K plus 1. Okay, this statement is true for a geometric distribution, and I claim that, in fact, it's only true for the geometric distribution. Okay, so this is a nice parallel to the size bias result that we had for the exponential distribution. Now, we started, heaven knows what time, and I'm losing track. I have no idea how much longer do I have? I'll do my best to stop. I can stop anytime you want me to stop. Okay, I'm not proud. If I stop in the middle of the sentence, that's okay. But if you give me a rough idea of how much more time I have, if any, I'll continue.
No, the time is 9:56. We can go till 10:25. Sir, is process or will it affect your
10:05 or
10:05?
like,
okay.
You're telling me India time. What does that mean to me?
Actually, you should give them. You allotted.
Is that 8:30?
Minutes.
so
My time is an hour and a half.
Then take 10 more minutes, Professor.
10:15.
Now it is 9:56 here.
Yeah.
9:56. Can take 10 more minutes.
45 my time. Okay. 10 more minutes.
10 more minutes can take.
Okay. Well, we'll stop when we get to 10 more minutes, or I'll keep going and you shut me up soon after 10 minutes as you can. Okay. So let's look at this thing. We claim this characterizes the geometric distribution. Next. And the proof for this is what's the right thing to use for non-negative integer valued random variables? Probability generating functions. Essentially, that's the same as Laplace transforms. We could use Laplace transforms because they are non-negative random variables, but the natural thing is to use probability generating functions. And so if we look at our condition, it comes out to be equivalent to p squared s, where p of s is the generating function of the x's, is equal to cs times p, the derivative p prime of s. You rearrange that, you get this expression here. Okay, and once again, I go running to my old differential equations book. Next. And I recognize that if what they always do is they write dp by ds as for p prime of s, and they just put p for p prime. So this is the differential equation in the notation you'll find in your differential equations book. And notice that this is separable, because the right-hand side just involves s, and the left-hand side just involves p. And so we can do a partial fraction and expansion of the left-hand side, which I now put on the right-hand side, and then you can integrate, and you get this nice little equation for the effectively for the function p. Next. And so after we sort things out, we end up with that p is equal to c over 1 minus s over k. And then we know that p0, it's a generating function, so p0 is equal to probability x equals 0, that's p sub 0. And p1 is always equal to 1 for any generating function. So we put that into the formula that we have, and we end up with the generating function that we have here at the bottom, which is just a geometric distribution with parameter p sub 0. Next. So that worked out just like the exponential. There's a more general result. If we have independent random variables that are geometric, we can look at the ratio of the density of Sn and the density of Sn plus 1. And that is of this form. And typically, what we're going to argue is that that kind of ratio determines the common distribution of the x sub i's. Next. Next. Okay. So this is the statement that we have before that I just hinted at. If the density function of Sn, the ratio of that to the density function of Sn minus 1 is of this form, okay, then necessarily it will be the case that the x's have a common x geometric distribution, because this statement is true for the case, and we can prove that that works in general. Next. Okay. Well, we end up with, once as usual, writing the generating function of the sum as ps to the n, and we end up with a differential equation that's down here. And this is the same equation that we solved in the case n is equal to 2, and so we get a geometric distribution here too. So this is parallel exactly to the exponential case because we had the same thing there. We proved the case n equals 2 and the case for larger n simplified down to the same differential equation, so it was easy to handle. Next. Okay, an even more general result, which we can prove is we could prove there was a characterization result in the exponential case that we couldn't prove, but we can prove it in the geometric case. Next. Okay, and so this is the one that we were able to prove in the geometric case. We look at n1 less than n2, and we look at the ratio of the discrete density of Sn2 and the discrete density of Sn1, and that's if that is equal to this expression here, then we must have a geometric distribution. So that's exactly the thing that we had in the exponential case, but now proved in the geometric case. Next. Okay, but I'm not going to prove that result as it stands. I'm going to prove later on a much more general result, but the idea effectively is that the quantity Ank that I have here, which is the ratio of the density of the sum of n to the ratio of the density of the sum of n minus 1, that effectively determines the common distribution of the x sub i's. Okay, and I'm going to prove that result if I have time, which I probably won't have time, but I will have that in mind. But before we do that, next, I'm going to look at a special case which is a little easier to handle. I'm going to switch gears and think about characterizing a Poisson distribution. So let's take a sequence of IID random variables, non-negative as usual, integer value. Sn is the sum. If the x's are Poisson, then we know that S of n, the sum of n2 of them has a Poisson distribution with parameter n2 times lambda, and the sum of n1 of them has a Poisson distribution with parameter n1 times lambda. And the ratio of those two things in the case of a Poisson distribution is just given by n2 over n1 to the k multiplied by a constant, and that constant, if you ever care about it, is e to the minus n2 minus n1 times lambda. Okay, so this thing makes us think that perhaps we'll have the following characterization of the Poisson distribution. Next. Okay, suppose we have IID random variables, and suppose that the ratio of the density of the sum of n2 to the density of the sum of n1 is of the form c n over 2 n1 to the k power for some c for every k. Then x's must have a Poisson distribution. We know that this is true for the Poisson. We claim that it's only true for the Poisson. Next. Okay, now it's tempting to try to resolve this issue by using probability generating functions. Okay, but what you get is, for this, is that Pn2 of s is c times Pn1 n2 over n1s. Now that's not the obvious kind of equation that you can find people solving. It's not a differential equation. It's not a nice difference equation. It's a well-defined equation, but it's kind of an awkward one. So we back off and say, well, you know, even if n1 is equal to 1 and n2 is equal to this is still going to be challenging, because then you're going to have that the n2th power is equal to the n first power evaluated now at 2s. Okay. And, you know, maybe you'll be able to handle the one. N1 is 1 and N2 is equal to 2. Maybe you could do that. Next, let's do something different.
Excuse me, there is only 1 more minute.
Okay. All right. Let me finish the Poisson example, then I will bow out. Okay. It won't take a minute. We can make progress by considering the equation for a series of values of k. We're going to denote the probability that x1 is equal to I by p sub I. That's just notation. And we're going to denote the ratio between p1 and p0 by lambda. Now, because this is a random variable which has positive values, all the PIs are positive, then P1 divided by P0 could be any positive real number. That's perfectly fine. And so if you look at the case with k equal to 2, you'll find that P2 is equal to P1 squared divided by 2P0. Substitute in what because P1 is equal to lambda times P0, and we end up with lambda squared P0 divided by 2. This is like eating potato chips. You eat one, you can't avoid eating another one. Let's try k equals 3. We do the same thing, and lo and behold, we find that P3 is lambda cubed P0 divided by 3 factorial. I guess you can imagine what happens to the kth one. It's going to be lambda to the k, P0 to k factorial. Use a careful induction argument, and we have our Poisson distribution. Can I see the next slide before I say that's it? Okay. Okay. I am going to, I won't have it, but if you're interested, I can prove in the discrete case that basically the ratio of the densities of SN1 and SN2 determines the common distribution of the x sub i's. I have to put on one little regularity condition. I have to say that the two densities will be the same under those circumstances as long as the probability that they each take on the value 1 is the same. So next slide, maybe I have that statement stated. I don't think I do.
Can you?
Okay, I'll stop there.
Yeah.
And I thank you very much for changing the slides for me. And I do apologize because it makes for a very disjointed presentation. And I promise you it would have been smoother. You may not believe that. Okay, thank you for your attendance. Oh, go swing on down to where I say thank you for your well, I have a thank you slide. And
thank you, Barry Arnold, for sharing your ideas and suggestions regarding the characterizations, convolution, size-biased distributions, and their variations, and conjectures, and their discrete parallels. Already, I think the organizers are running late in time. Considering this, however, there are many people to share their, to express their comments and to ask queries. However, due to time constraints, I think we can allow one quick question or a comment. Anyone? Professor Balakrishnan?
Actually, I have Barry, I have an inquiry. You know that in that Poisson example that you gave, you have N1 and N2. And, is it not easier to take the log and then take the differential to get a differential equation?
In the discrete case, I don't have a differential equation.
No, but you will have the probability generating function, a differential equation for probability generating function.
I'm not sure. I didn't think that. I didn't think for the discrete case that in many situations I felt that you needed a difference equation rather than a differential equation, and also I found that the differential equations didn't seem to help so much. I had to use sneakier ways to get to the problem, which quite possibly there's definitely these things can be handled in more than one way, and I'll be happy to think about that one, and thank you for the suggestion.
Yeah.
Well, thank you, Dr. Balakrishnan, and let us conclude this session, the keynote address session. And I thank the organizers and Dr. Satish Kumar for giving me this opportunity to chair this session. Thank you. Now over to the organizers.
Thank you, Professor. Thank you, Professor. Thank you, Professor Loganathan, for chairing this session. And thank you so much, Professor Barry, for your wonderful talk. In fact, we are very much grateful to you, professors, for your support to our the activities. So, thank you so much. I hope you let us move to the next session without wasting much time. Next session, once again, Professor Barry and Professor Lavinath. Let us move to the next session. Roshni, please introduce the chair and please support the chair for its further proceedings.
Sure, sir. A warm good morning to everyone present here. We all are honored to be presented with the opportunity of attending a session chaired by Professor D.K. Ghosh. Professor D.K. Ghosh has accomplished his PhD on the field of design of experiments from ISI Delhi. He also was head and prime faculty of Saurashtra University, Rajkot. He was designated with many supreme positions, including being the research investigator, junior scientific assistant, senior research scholar, and many more to add. With 44 years of experience, he has contributed in more than 150 publications of research papers and published 3 books, namely Distribution Theory, Factorial Experiments, and Biostatistics. Professor Ghosh is also the recipient of John C. Pace Fellowship Award, $I. Mangad Award for Excellence in Research, and a countless designation to state. He presented his share of work at many national and international conferences, with conference at University of North Carolina, seminar at University of South Alabama, and a 4-day seminar at University of West Florida, to name a few. He has contributed his share of expertise in the field of statistics by being the editorial board member of many national and international journals, and presented with eminent and executive positions like being the Vice President of Gujarat Statistical Association and Executive Committee member of Indian Science Congress. His major projects include preparation of table of PBIB design with 2 associate classes and a study of survival analysis of breast cancer and its statistical analysis. We look forward to this session with great anticipation. Over to you, sir.
Thank you very much, Dr. Satish. You gave me this opportunity to sit on a chair. The speaker is a renowned statistician in the field of directional data, Professor Ashish Sen Gupta. Of course, he is a very good friend of mine also. We are associated at several places. And now time is 10:12, and we should give him 40 minutes. So we'll request him to complete by 10:50. Now I request Dr. Ashish Sen Gupta, go ahead.
Hello, can you hear me?
Yes.
Okay, so I want to share my screen. So let's hope it comes up. I put there, I have shared my screen. Can you see?
Yes, Professor, the screen is not, you can see your desktop. Please, you can go to the slides.
So I am going to share my screen now, okay?
Yeah, Professor.
Here's my entire screen.
Yeah.
So I should click on, let's see, this is being,
The consent files.
okay, see the screen now? My file?
Not yet, Professor, not yet.
It should be coming. Is it shared? Is my screen shared?
So please repeat it, Professor. It is not yet.
I'm going to share my screen. So,
I think you please firstly open the presentation in your system.
Yeah.
Then
It
you
is
click
open.
on this arrow, which is on the right side,
Yeah.
next to the 3 dots, and click on that, and then share screen or
I have
share
got
window,
the shared
and click
screen
on the
already.
presentation.
I have got my shared screen already. I
Now
don't-
it's okay. Yeah,
So
yeah,
you're
it's coming.
presenting your screen.
Yeah, now it is coming.
Can you see
Now-
my screen now?
Yeah, we can see the desktop. You can,
Yeah.
now it is.
Yeah, it has come.
Right, so it just took us a little
It has
time.
come.
Okay, let me make it full screen.
Yeah,
Yeah.
fine.
Yeah, it's right.
Okay, great. Okay, thank you very, very much. So, can I start now?
Yes, sir.
Okay.
Yeah, Professor, please.
Okay. Thank you, Professor Ghosh, and for steering this session, and thanks to all of you who are here. Good morning to everybody. And I'd like to thank the organizers for inviting me here for this talk. And it would be my pleasure to give this talk to you once again. But this kind of iconic conference, it has been going on for many years in spite of lots of hazards in the couple of years. So today I'm going to talk about a new distribution. It's cooked up thoughts and also cooking up ones too. So there will be few open ends. It's work is going on in those areas, and some of the results are to be obtained. I'll indicate some open problems possibly, which might interest the researchers, and I hope that you'll be able to get a flavor of some problems in distribution theory and applications in circular statistics. So let me move on to my next slide. Okay. So on the construction and inference for a highly flexible family of circular distributions. That's the title, and I'll explain to you what are circular distributions and the inferential aspects.
The slides, Professor, you are presently on the first slide. Okay.
The next slide. Let me go on
The
to the
slides
next.
is not moving.
It's moving now, right?
No, Professor, please.
No, it is not
You
seen.
can, you can share it once again.
No, it is moving. It on my screen. It has come up.
It is not, Professor.
She is not on screen.
Please try to share it once again, Professor.
Did the first screen show up? Did the first slide show up?
Yeah, now there is no presentation here in what we see here in the computer
No presentation.
presently. So you have to go to presentation.
Okay, I'll do the sharing again. Okay.
Yeah, share.
Here
Share.
it is. Your entire screen. Okay. And which one do I click now?
And then
Full screen.
I'm saying share.
yeah, share. Now the share button will be active, isn't it?
Right. I
Yeah.
put on the share. It is coming up.
Yeah, now it is coming.
Right.
Now you can go to the slides.
Yeah, that's what I did. But why did I lose it?
Now it is fine. We can see
Now
the
it's coming.
second slide. Yeah.
Okay. So can I put it on the full screen now?
Yeah. Ashish,
Yeah.
use the up and down arrow to move the
Yeah,
slides.
that's what I'm doing here. So
Yeah.
has it come up now?
Yes.
You can see my second slide, motivations.
Yes, we can see it.
Okay, good. Okay, so I'm losing time this way. Okay, so here are the motivations. I'll give you some real life problem. Like we see the circadian rhythms, which are circular data. You can think of 24 hours. Yes? Yeah. So you can think of 24 hours in a day and as a circular event, a phenomenon. And similarly, in the data analysis, where you think about
Excuse me 1 minute. Dilip, please mute your microphone. Dilip, please mute your microphone.
Okay. Someone's microphone is on.
Just a minute. Yeah. Go. Oh, sir, now you can continue. No problem.
All right. So we'll think about how to model these, because what we come across in the circular data especially are the problems with the tails and also the requirement of periodicity. So the usual distributions that we see on the real line sometimes are not adequate, and we need some highly flexible family. And we have to do the optimal inference, depends on the harmonics, because again, but because of the periodicity, the usual estimators like the mean, sample variance, they do not really hold good here. The motivating real data set, this data is a challenging data. It has been referred to by many authors. This is a very well-known data given by Anders. and was collected from the reference mentioned there. And now this is on regarding the movement of ants. There's an illuminated object, and the ants are supposed to move towards that object, but not all the ants do move there. Some of them do go astray, and but most of them will go there. So what will happen? There will be quite a peak at the 0 direction. That is the direction where the illumination is. In the other places, over here, the ants will go awry. That means it will be a sort of a uniform distribution, random directions. So there's a lot of interest because this is just a generic example. You can think of this in signal detection. You can think of this in astronomy, astrophysics, all kinds of situations. And a lot of people have tried to model this, but unfortunately, the usual circular normal doesn't hold good. And we'll see that when you move on to stable distributions and their extensions to the circular case, there also the family fails to model this kind of distributions, this data, in spite of the flexible tail behavior of this same family of stable distribution. So we really need to move up to some other families, and that's what the talk is going to be concentrated on. And I'm going to talk about an alternative family, which is the wrapped Linux family. So the roadmap is a challenging data set, as I mentioned to you, the flexible circular probability, this is a new wrapped Linux distribution that I'm going to talk about. Properties, I'll give some counter example, will show the difference between the circular and the linear case, the tail behavior, the geometric infinite divisibility, the problems therein, the identifiability problem of the mixtures of these distributions, and the open problems therein. Some computational issues, I'll give you the estimators and their asymptotic distributions, and finally, the real life examples. Okay. So I told you there are lots of applications. For the sake of time, I'm going to skip these. And I think most of you are familiar with circular distributions and circular data. They relate to the directions, they relate to orientations, they relate to dihedral angles. So anything that can be put or mapped onto the circumference of the circle, and which are strictly periodic, for example, also, they do fall into the reign of circular statistics or circular variables. So here's an example where we do deviate. As you can see from the linear case, if you take the 15 degrees and 345 degrees, usual mean will be the 180 degrees, which points in the wrong direction, because actually if you look at the vector resultant, that will give you a 0. So the arithmetic mean is a useless measure here, and you have to think about the trigonometric mean in such a situation. If the arithmetic mean doesn't work, neither does the usual variance, nor the correlation, or most of the other measures. So the initiating references at this book that is coming up to 2022, I wrote there, it is possibly going to come up in 23. It won't be there in December. The other one, the directional statistics, this just came out. You can see lots of examples here, and also theoretical developments in many of the papers. And then this is our old book, textbook on the topics in circular statistics. So the density probability function of a circular random variable, those two conditions are the usual ones. The third one is the one specific to the case of circular random variables because of the inherent periodicity in the angle theta. So here are some descriptions of the data set, the way that you represent the data. As you can see, the first one that gives you the density in a 3D plot. The second one, when the mean direction is taken to be at 0, you can see the range now is from the support is from minus 2 pi to plus 2 pi at minus 3.14 plus 3.14. But if you go to the support from 0 to 2 pi, the same distribution that is having a bell shaped and gives you a nice interpretation, you can easily understand the mode as 0. Over here in the circular case, that becomes a bathtub shape. So inverse bell shaped, as you may say. And over here, the range is from 0 to 2 pi, the usual one that we look at. But unfortunately, the distribution gives you the interpretation, or the impression rather, that the 0 is the anti-modal point and not the modal point. But this is of course not true when you put the graph on the circle and plot the distribution on the circle. Now here you can see when you put it on the circle, obviously the direction that we're going to get is correspond to from minus pi to plus pi. That is again going to be equal to 0 direction. Okay, so the mean will be 0. So even in the plotting of the data, one has to be careful and as for his interpretation, because a linear plot will not give you the right impression when you're looking from the data from 0 to 2 pi instead of looking from minus pi to plus pi. So the tail behavior for a random variable of support R is quite transparent. But when you look for circular distributions, the support is only 0 to 2 pi. So what is the tail over here? So that is not so clear. So the CD is now the circular distributions will have tails extending over the entire support, as well as non-trivial probabilities thereon. So if you go from 0 to 2 pi, the concept of tail has to be thought of. So long and short tails in this case do not really arise as such, but whether we may say these are like heavy and thin tails. So we'll have to characterize or talk about the thin and heavy tails. And we'll come to that. For example, look at this figure. So to do so, we have now matched the modes of two distributions, which are called the circular normal, and then over here we have also the Rapt-Cauchy densities. So I have made the two modes to be the same. So that way the modal density has the value 0.3410 at the value of 0 point of the mode. And then the corresponding parameter is matched. For example, the corresponding parameter for the Rapt-Cauchy to the circular normal distribution 0, 1 gives you the value of rho is 0.3645. So if you now plot the Rapt-Cauchy with rho equal to 0.3645, then you get the particular distribution here that you can see. And this distribution then gives you the solid one that you will get over here is the Rapt-Cauchy density. And that clearly shows that this has a heavier tail than the circular normal density. Okay? So, but we have to match the modes in order to make this type of comparison. So similarly, we can think of looking at the modification of the tails through mixtures. Now, one way of doing that without perturbing the shape of the distribution, which you can easily do by taking the different probability distributions over certain arcs or certain parts of the support on 0 to 2 pi, that will perturb the shape of the distribution. Rather than do that, you can take a mixture on the entire 0 to 2 pi support. And in this case, what will happen is that you will have the tails now will be more prominently distorted, or rather they will be modified. So you can see if you take a circular uniform mixture, the circular uniform mixed with, let's say, another density over here. And in this case, the one that I showed you earlier, Pf1 theta 1 minus Pf2 theta. So if you take, for example, F2 theta as the circular uniform distribution, F1 theta is certain unimodal symmetric distribution, you can see the new distribution that you get now has a tail which will lie between the uniform and the original distribution F2, which means that now it will have a more heavier tail. So this is one way of trying to modify the tails by looking at mixtures. Mixtures have obvious difficulties, for example, with the big knot in the exponential family, increasing the number of parameters. But with 0 to 2 pi mixture, the advantage is there is no additional parameter except for the parameter P, the mixing proportion. Now, going to some definitions over here. Let's see. Yeah. So a random variable, as you know, is said to be infinitely divisible. For example, if you can write it in the form of the convolution of independent random variables x1 and to x2, xn. So this is said to be the random variable then as that you get over here is said to have the Arrhenius characteristic function equivalently to possess the infinite divisibility property. And then you can think of the compound distributions. And if you now let n over here to be a random variable itself, let's say a geometric random variable, then you can have geometric infinite divisibility. Geometric infinite divisibility plays a very important role and is very useful in applied sciences in various areas. So that is a desirable property also. So we'll try to just say a few words on the GID property of the distribution that we're going to propose. Now, so similarly, when you think of this mixture distribution, you can also look at this particular characterization by Atienza. Then that we say that G is identifiable if and only if for this mixture Gj that we have over here, G1 equal to G2 holds if and only if K1 equal to K2, and the permutation, all these pi1, I1 and pi Fi1 is a permutation of the pi I2 and Fi2. So that way, the distributions that we have in this family are going to be identifiable. Otherwise, different parameter combinations can result in the same distribution. So this another approach to defining identifiability is looking at the particular characterization that we have of the functions f zeta. So the family, then the family that we're looking at over here for any distinct of the functions f I theta are going to be linearly independent. Okay, so if they're not linearly independent, then we're going to say that this mixture is not identifiable. The results for the linear case, they need not carry over to the circular case. That is the problem over here. For example, the Holzman proved that even though the finite mixtures of Poisson distributions are known to be identifiable, the finite mixtures of Raft Poisson are not. Okay. So similarly, there's another example, the triangular density. So what is true in the linear case with the identifiability doesn't hold for the case of the wrapped or rather distribution, the circular counterparts of the same distribution in the circular case. So one has to be careful about the identifiability property when we're talking about the distribution derived by wrapping, for example, from a linear corresponding distribution. So now here is another example. So if you consider two parameter location scale families, then the characteristic function be for each phi t. So if the characteristic function of this location scale family satisfy this limiting condition that the ratio is equal to 0, okay, for sigma 2 greater than sigma 1, then the finite mixtures are identifiable. This is a very nice result, and this way we can prove, for example, the identifiability of the mixtures when it comes from, let's say, a stable family of distributions. Because if you take the ratio, it's obvious that this condition is satisfied. But then this condition may not be convenient to apply in the location scale Linux family or circular distributions. Okay, this family of distributions, as you'll see, that this limit really doesn't go to 0 in that situation. So we need different conditions and generalization of these conditions. So this opens up another area of possible research in the circular families. Okay. So the Linux family of distributions, let's see, yeah. The Linux family of distributions was first proposed by 1953, and it had lots of applications and was popularized, for example, by Professor Barry Arnold and Anderson. A lot of work has been on there. So what we propose to do is to use it for a circular case by wrapping the Linux family of distributions. And this is done by using the certain results and the Fourier analysis that being a periodic function, it admits of a representation in terms of the Fourier coefficients. So for that, we need to have the moments and the characteristic functions. And you can see over here, the characteristic function is given by the psi p theta equal to exponential of 1 plus p sigma to the alpha minus 1. So once we know that, and being a symmetric function, our Linux distribution after wrapping, the sign part drops out, and we get the wrapped Linux distribution given by the quantity over here, f theta, defined as presented. So it gives you the adaptogenic family, and we'll now study the tails about it, tails of this distribution, also certain properties. Now observe that the Linux family of distributions is defined in the real case for the parameter space alpha on 0 to 2. Okay, 0 less than alpha less than equal to 2. And alpha equal to 2 in the linear case gives us the double exponential distribution, a Laplace distribution. But when we have in the circular case, there is a counterexample that this entire parameter space does not really apply to the circular case. If you have values of alpha, for example, less than 1, then this distribution in the circular case is not defined. So the general approach of wrapping a linear distribution to a circular distribution cannot be used here indiscriminately. One has to be very careful here because the parameters that you are looking at, the parameter space may not be at all defined in the circular case. As an example, in this case, if you have sigma equal to 1 and sigma less than 1, and for over here, you see as a, let's see, let me give you the example specifically. So the wrap exists for alpha greater than equal to 1. So if it alpha is less than 1, and let's say over here, your theta is equal to mu naught, then the series, the resulting series does not converge. It is going to be a divergent series and shown here. And that will be true also for mu naught, theta equal to mu naught plus pi. Or if theta is in the range greater than pi, then it is also going to be true for theta less than mu naught, theta equal to mu naught minus pi. Okay, so in that way, the values of the cosine quantity that you get over here, that will give you the values equal to 1 here or negative 1, so that this series will be becoming a divergent series, and hence this distribution is not going to be defined at all. So the number of terms of truncation, this is an infinite series. So how do you deal with that in terms of the real life application? So one needs a table over here. So I've given computed the tables where the number of terms for the truncated series, what is the number of terms needed for the computation. For example, you're looking at goodness of fit test, or when you're looking at the estimation of the parameters, how many terms are to be retained. It turns out that it does depend on the value of course, of the alpha, and it's taking an initial value of P naught and then we increment it, and going by the definition of the convergence of the series over here, for example, if the alpha is missing, then we have power to the alpha over here, sigma p to the alpha. So depending on the alpha, this number of terms can go from, let's say, 10, 12, and even to hundreds and more than a couple of hundreds for the convergence of the series. So in real life computations of the estimators, one has to take care of the number of terms for the convergence of this particular Fourier series. The tail dominance, again, as I gave you the example with the symmetric stable and the linear distribution. So if you look at the compute these particular densities by equating the modal densities, and then look at the corresponding parameter to be equal to, for example, when you look at the circular normal that I showed you earlier, you take the corresponding parameter for the wrapped linic and you try to see what happens to the tail of the behavior. Then we can make a reasonable comparison, and this is where the trick lies, to find out the value of the modal density and then find out the value of the parameter to which this but other competing density, let's say the symmetric density, corresponds. So if you look at the empirically, we can now compare given these theoretical values of alpha and the what I showed you earlier. But now what happens if you don't want to constrain the modes? Then you have to do these computations empirically, and we'll show here empirically over here by the two curves that you see that these two, almost in all the cases, the solid red line corresponding to the wrapped linic, let's say alpha equal to 1.4 and alpha equal to 1.6, where alpha has to be greater than 1, as I mentioned earlier for the linic, this almost uniformly beats the wrap stable family of distributions for alpha in the entire range from 0 to 2, 0 excluded. So you take values of alpha less than 1 and alpha less than 2, but nevertheless, the rapid also uniformly dominates, except for the case, a very, let's say, almost trivial case when alpha is very close to 0, like 0.1. Okay, except for that case, in all other cases, this rapid distribution dominates the tape. So that gives us the impetus of taking this distribution further for exploring the behavior of the other other property. So now let's look at the property of we talked about identifiability. Now talk about the infinite, the divisibility property also. Okay. In the linear distribution, it is known that it is a geometrically infinite divisible, and it depends. It's obtained by this particular proof. I'm giving you the proof for the linear case. I'll tell you why in just a minute. So if you look at this, then a function, this characteristic function satisfies the condition that phi t is exponential of 1 minus 1 over ft. Then this is an infinitely divisible characteristic function. Okay, this is by Klebanov et al. This paper. So for each alpha equal to 0 to 2, if you look at this particular exponential function and if you have the linear distribution, it turns out to be exponential of minus t to the alpha. But that is simply the characteristic function of a symmetric stable distribution, and hence the linear family of distributions is geometrically identifiable. Okay, the above proof holds for all t, but if so, then it also holds for all p in the Z, that is in the set of integers. Okay, so hence this characteristic function defined for the set of integers p is nothing but the characteristic function of the wrapped linear distribution, and thereby it proves that the wrapped linear distribution is also geometrically infinitely divisible. So this we may use for other distributions. You may get excited, so okay, we have a good theorem, but be careful. Recall that by Bochner's theorem that we need this characteristic function to be continuous at the origin. But in the case of circular distribution, this is not true, because the circular distribution characteristic functions are defined only at integer values. It could be negative or positive, but it could be minus 1, 0, 1, and so on. So which means that we do not have the continuity of that characteristic function for circular variables at the origin. That calls for a generalization of Bochner's theorem for the circular case. And I would invite you, the students and the researchers, to have a thought about it, and it will be a nice, interesting problem. It's an open problem that I came across, and it will be good to use it for our circular distributions at large. So that's what I mentioned in a nutshell. And we need to, for the asymmetric case, this particular theorem that I showed you doesn't hold. So I'm going to, and it also doesn't show you that it is the components of the GID components. What are the GID components over here? By definition, it should be having a closure property that it should come from the same wrapped linear family. And here is the proof for the second part. So if you look at the P prime being the argument of the characteristic function of the linear distribution, and phi p prime being the characteristic function of the wrapped linear distribution given in 6.3, and this is a geometric distribution that we are defining by 6.4, then assume that these are independent. Then what happens is, let's see. Okay. Then you can, by conditioning and by unconditioning, by direct proof, you can see from here that the characteristic function for the sum that you have over here, by scaled by p to the 1 over alpha for each theta, that characteristic function turns out to be the characteristic function of the wrapped linear distribution also. So which means that the wrapped linear family is identifiable, is geometrically identifiable, and it also has the closure property. That the elements of the sum that you have, they are going to be coming from the same family of wrapped linear distributions. Okay, so that settles the issue with the infinite divisibility. But again, I told you about the warning regarding the characteristic function and also about the divisibility property, the identifiability property. So let's move on. Okay. Now, for the estimation part, for the estimation part for the linear linear distribution, obviously the moments of order greater than one, they don't exist in the linear case. So Kuzabuski used the moments of what are the fractional moments.
Dr. Sen Gupta, you have 5 minutes only.
Yeah.
You have 5 minutes.
Yeah. Okay. So
5 minutes only.
So I'm going to now very quickly go over to the inference.
Yeah, 5 minutes.
So the estimation of the parameters over here cannot be done as usual. As I mentioned earlier, the mean doesn't make sense. And further, the parameters that you estimate by using the moments, regular moments do not apply. So we go on into the estimation for the trigonometric moments. Well, that is where we're going to go ahead and stay. This is a part of the work that we have gone through, and I'm going to very briefly breeze through the estimation part because of the time. Let's see. So, as I mentioned to earlier, this is a joint work with one of my PhD students. Let me quickly go through. I talked about the tail dominance part and the constraints on the parameter space. Let me go on over here. Okay. So the estimators over here that we're going to get is obtained through the trigonometric moment estimators. And the estimator of alpha, for example, over here is given by the quantity that is written over here, alpha 2 hat. I equate the trigonometric moments. Alpha 2 hat is given by the second one that we compute, and C1 and C2 are the sum of the cosines, two moments. So summation cosine theta is given by C1, and summation cosine 2 theta is given by C2. Okay, so and then divide by n. So these are the trigonometric moments, and we are able to get the asymptotic distribution of the estimator of alpha. And this is a sort of a non-trivial in terms of the big expression, but we can show that this in fact converges to a by central limit theorem to a normal distribution. Okay, the 4 components C1, C2 bar, S1, S1 to S2 bar. This leads to the theorem that the distribution of alpha also converges in law to a normal distribution. So this proves the asymptotic, the consistency of the estimator alpha. Let me tell you, in the case of the linear situation, the estimators that you obtain of alpha have to be done from the using the fractional moments. But since the alpha is preserved in the circular wrapped linear to be the same as the alpha in the linear case, so this estimator based on the trigonometric moments can still be used, or rather can be used for the linear linear distribution. So it means that we have been able to here provide also a consistent estimator of the parameter alpha of a linear linear distribution, along with that for the circular linear distribution. Okay, so I'll just give you the expressions are pretty, as you can say over here, are going to be quite a little bit a long expression, but they can be worked out, and with modern day computers, just programming it is not at all difficult.
So 1 minute, please complete it. 1 minute. Please complete it.
So I'll just give you one example. I'll give you one example, and then we'll be done with it. Okay. So there is a modification of this estimator, because this estimator, as usual, is the problem with the moment estimator that can be more than can go beyond the range. So it truncated alpha 2 hat is a truncated estimator to keep it within the range. And finally, if you do this truncation and keep it, it can be shown that the truncated estimator also has a asymptotic normal distribution, and that means it's also going to be a consistent estimator, but a much better and improved estimator, as usual, an efficient estimator of alpha. So let me go quickly to just one example, and we'll finish there. Okay, so this is there are in fact 4 different examples shown in this paper, but I'll give you this example with the movement of hand. So this was the classic example. Neither the circular normal nor the whole family of lap stable distribution could provide a fit. Okay, and as you can by the Watson's U-square, we use the lap stable distribution, and we saw that it also doesn't give a fit. Now, motivated by the Linux family of distribution with the different tail behavior, we used it for our data, and we saw, as you can see, the goodness of fit statistic. We found out to be given the value, the p-value of the is 0.71. Okay, the rep Linux distribution fits the data pretty well, and this gives a solution to this problem of rather modeling that classic data set. And of course, this, as I said, is a generic data set. I think I should stop now. There are many other examples, tables, etc., the comparison of the estimators. And I will quit now. Let me go to my just one. Let me escape from here and do the last slide. Oh, the last slide. Thank you. Okay. Okay.
Thank you very much, Assistant Gupta. And it was a very interesting topics on RAP linked family distribution. I'm sure that the new researcher and research scholar will be benefited with this talk. They will get the opportunity and extend this work for their future. Since we are short of time, so, we can ask only one question if you have. If you have any question, one question.
Hi Ram, I see you there. Ramanathan is there, right?
Yeah, I'm there.
Yeah. Okay. So
Go ahead. Please go ahead. If there is no question, then I hand over to Professor Satish for the further proceedings.
Thank you. Thank you, Professor Ghosh, for chairing this session in a very nice way, and Professor Atish for your excellent talk. We are grateful to you, Professor. In fact, several are anxiously hearing about further things about this talk. I hope you can share your experiences in the next time through our workshop. Some more things regarding this circular distribution, rapid distribution, and further recent developments in that respect. Professor.
thank you very much, Dr. Ghosh, and thank you also, Satish.
Thank you so much.
And for all those who attended, patiently hearing this talk. Thank you again.
Okay, thank you, Professor, for your our activities and this conference. And now let us move to the next session, since we are running in a little bit late due to the problems occurred in the beginning of today. Now we have, without wasting time, Professor Malikoshi is waiting, and everyone are waiting to hear from him. And Neha, please introduce the chair and do the needful for supporting him.
Warm greetings to all. Now we move on to technical session number 12 of ICSTC 2022 to be chaired by Professor Ramanathan Tekevariam. Dr. Ramanathan is the professor in Department of Statistics, Savitribai Phule, Pune University. His main areas of research include inference in stochastic process, financial time series, non-parametric inference, generalized linear models, model selection, and econometrics. He has published more than 50 journals and books and has also organized several conferences. Professor Ramanathan also received Jan Tinbergen Award. We're indeed privileged to have you here, sir. I cordially invite Professor Ramanathan to chair the session. Sir?
Thank you. So I welcome Professor Malay Ghosh. Professor Malay Ghosh doesn't require any introduction to this group because he's such a senior academician. Perhaps he started his career before some of you have even born. I mean, some of the young researchers. So I welcome Professor Malay Ghosh. In fact, half an hour will not be enough to read out his credentials. So I'm directly handing over the mic to Professor Malay Ghosh. Please start your presentation. Malay Ghosh.
Thank you very much. I need someone to flash the slides. I send the slides to Satish. And can you do it for me?
Yeah, Professor.
Please do it. Then we can start right from there.
Okay, Professor. Just, I have to check whether the slides are good.
Yeah, please. Our university doesn't allow anyone to, doesn't allow sharing the screen unless it is Zoom. That's the problem.
Okay, Professor.
Thank you very much.
Now it is coming.
Full screen?
Yeah. We can, yeah.
A little bit clearer.
Is it okay, Professor?
A lot of focus.
Yeah.
Yeah, focus.
Full screen.
Okay. Yeah. Thank you. Thank you very much. Well,
please carry.
Yeah. Thank you very much for this kind invitation. I'm sure this talk does not fit in with the theme, actually, of this conference, because there is not much of a distribution theory going on here. I get this talk in a small area conference, and I just got this invitation when I'm in Calcutta, actually, right now, visiting the family. So I didn't have anything in hand, so I decided to talk about this particular area, which is small area estimation. It's a joint work with my student, Tamal Ghosh, Jerry Maples from the United States Bureau of the Census, and Xing Tang, also one of my PhD students. Next slide, please. So I'll give a very brief introduction to small area estimation, actually. Then I will introduce the so-called global local prides, which have now gained popularity, not in the context of small area estimation as such, but more in the context of high dimensional data under sparsity. But that's another story. But then I will talk about the multivariate hierarchical model, a little bit of theory, data analysis, simulations, and some final remarks. Next slide, please. So what is small area estimation? Okay, the demand has increased, I said, but what it is? Small area estimation means, actually, as I said, in a small area estimation meeting, I don't have to define small area estimation. Small area estimation means actually estimation for small geographical areas, but I will try to clarify what I mean by small geographical areas: counties, census tracts, school districts, etc. But even states can be small areas, and I will tell you why, and make it a point later. For example, the original survey was carried out to get a desired level of accuracy at a national level. You don't have the resources to conduct another survey, so you are using the same data for estimating whatever quantities of interest for the 50 states and possibly even the District of Columbia. Then the states become small areas. Also, it could be small domains, like people classified by ethnicity, age, sex, etc. So small area actually doesn't necessarily mean that the area has to be very small. Okay? And very important current day program is undertaken by the United States Bureau of the Census small area income and poverty estimation. This is very important. The program is targeted to provide estimates related to income and poverty based on American Community Survey data at the state level and even at lower levels of geography. I will talk about the state level. Counties, I have some previous analysis for the counties, but not right now. In this particular context, census tracts, school districts, etc. Why they need it? Because they want to estimate the proportion of children under poverty. This is one example. There are other things also. For example, in providing the midday meals for schools in different counties. So even states will need something like this, to find out the proportion of children under poverty, as I'm saying. Next slide, please. Now what happens? I said it. Direct estimates for small areas are accompanied with large standard errors or coefficients of variation due to small sample sizes. And I just said earlier, the original survey was designed to achieve accuracy at a higher level of aggregation, doesn't have the resources to conduct a new survey at a lower level of geography. So use the same data for original survey, which will typically fall short of desired measure of precision. I will give you an example. This time I was involved in designing the survey in estimating the proportion of people without health insurance in the different counties of Florida, the state where I belong. So we got a sample of size 17,000, which was adequate to get desired level of precision for all the counties. But the very next year, the state authorities wanted to use the same data for 9,000 census blocks. Now, 9,000 census blocks with a sample size of 17,000, so you can imagine most of the blocks, there is no data. So how can you actually get at least some sensible measure of estimation? The necessity, the use of models to link the different small areas. Next slide, please. And I'm going immediately to model, just for the sake of history, little bit of history. That's when the thing started, people did not think about this kind of model. What they used to do is something like this. For example, we are talking about a state level estimate, and then you are using the same data for the county levels. Instead of using the direct county estimates, so take the population of the county and take a weighted average, weighted by the population county, and use the same state level estimate for the area means, for example. And then people realized it is not a good idea. It possibly gives better precision, but there is a lot of bias. So they talked about, so these estimates were called synthetic estimates. So they introduced composite estimates. The composite estimates are typically weighted average of the direct estimates and the synthetic estimates. But that was the early history. The real breakthrough came in 1979 when Fay and Harriet introduced a random effects model. They called it empirical base, which is fine also, but it is essentially the same. So yi's are the direct estimates, theta i's are targeted small area estimates, i's are the errors. But now you model the theta i's, the area level parameters, including the covariates available for the area plus an area level random effects. So yi's direct estimates, the xi's are the vector of auxiliary variables. Now we are not talking about large p, small sample size problem. The p is smaller than m, typically much smaller, number of small areas, but only a few covariates. So X has rank P. Now here is an important point. The errors are normal with a mean 0, that's fine, but known variance. Indeed, they are not known. Typically, they are sample estimates, but why known? The reason why it is, you can think about it, just think about, if you put the expression for theta I, what is it? Yi is xi transpose beta plus ey plus ei. So there comes an identifiability issue. You can get the total variance for ui and ei, but you do not get the individual variances. To avoid non-identifiability, they have assumed the error variances vi to be known. They don't typically use the sample variance that's modified. Buffet has a software called GVF, Generalized Variance Function, which is slightly better than the direct sample estimates of the variances. And area level effects are normal, 0, and the variance, sigma, u squared. Okay, next slide, please. Now, the Fay-Harriott model is still used. If you look at the number of citations, possibly it has more than 1,200 or 1,300 citations, and it's being used because of its simplicity and things like that. But a very important, I'm jumping possibly a period of about 30 years, or more than 30 years. So something which recently surfaced in the small areas literature. The question was, do we need random effects in all small area, or whether even fixed effects? You don't have to use the area level effect. I have some concerns about that. I will talk about my own research soon after. But this is how the whole thing got started. And believe me or not, this is one of the, not quite the first paper, one of the papers of Peter Hall. One of my colleagues said Peter has never worked anything on mixed models, but this is one of his first contributions. He had a couple of others, actually, with Gauri Datta, my student, and Gauri's colleague, Abhuda Mandal. But their approach was a test-based approach, typically what Peter likes. The null hypothesis is the common area level effect, variance, the sigma u square is 0, or not. So it is all or nothing. If it is 0, they're all fixed effects. If your test says otherwise, they're all random effects. So test was based on a discrepancy statistic measuring the lack of fit, of course. We don't have to go for that. Next slide, please. Now the Datta-Hall-Mandal procedure works very well when the number of small areas is moderately large, but not when they're very, very large. For example, when you're talking about the counties in the United States, there are more than 3,100 counties, about 3,140 or something like that. So in such cases, what will happen? The hypothesis of no random effects will be rejected, primarily due to significant departure of the direct estimates from the regression estimates, which are the synthetic estimates in a model-based case, caused by very few large residuals. They will pull everything out, and then you have to use a random effects model. So Gauri and Abhuda realized that. So let's model the random effects to spike and slab priors. The spike and slab priors is a mixture priors. Ashish talked about mixture, but here there is a specific reason for using a mixture prior, which puts a point mass at 0. That's the spike, and a 0 mean normal distribution, which is slab. I have some reservation about the normal distribution there. It is not sufficiently heavy-tailed, so it still can pull many towards 0, but that's not the main point. The point mass is suitable for areas where regression estimates are adequate. You don't have to go for the random area level effect. The normal, that is their objective. Normal distribution actually part is useful when the regression model as such is not adequate. Now you don't have to use specifically a point mass at 0. You can put a mixture of two normal distributions, one with a very small variance, that is tending towards zero, if I want to say it that way. And the other one is very large. So the one tending towards zero will try to get the zero area level effects. The large one will be dragging everything for where the area level effect is very large. Next slide, please. Now here was my concern when I first looked at the paper. I did not look at the Datta Mandal first. I first looked at the Datta Mandal and the subsequent paper. I found that is why it should be just how do we can approximate this spike and slack price? And really, the zero is not really right, because there is still a very maybe insignificant small effect. So what we started, they approximate the spike and slack price closely, but continuous priors, and the biggest advantage is they're much, much easier to implement rather than spike and slack priors. For example, if you have something, whether area is there or not, there are m areas 2 to the power m models, you have to take into consideration m very large. Even for 50, it is 2 to the power 50. So it's not a very convenient thing. But these priors were not introduced for small area estimation. They were introduced for high dimensional data under sparsity. They meet the same objective as spike and slack priors, much easier to implement, as I said. These priors allow area-specific variance components of random effects. So what is Fairhariot? They're using just a global variance, sigma u square. For Datta Hall and Mandal, either it is zero or just one variance, or if you have a mixture, there are two variants. But now we are keeping it flexible. We'll talk about it immediately. In areas where random effects are not needed, of course, that depends on the practitioner, depending on the threshold, the variance component can be very small. We are trying to estimate them. We are taking an adaptive approach. We are not saying zero or anything else. And in areas where regression estimates are not adequate, the variance component can be large. Next slide, please. The feature mentioned above is attained by employing two levels of parameters to express prior variances of normally distributed random effects. The first level consists of the local shrinkage parameters, distinct for each area. This is the new thing. The global shrinkage parameter is common for all random effects. I will make it formal in the very few next sentences. The global shrinkage prior causes shrinkage on all random effects to capture the small random effects. The local shrinkage parameters try to neutralize for areas that need large random effects. The degree of this neutralizing effects is closely related with the tail of the priors of the local parameters. We'll talk a little bit about that. If the prior is appropriately heavy-tailed, both small and large random effects can be well captured. Next slide, please. I'm going to multivariate without going to univariate, unfortunately. There is a paper appeared in JASA a few years ago for univariate situation. That was the starting point for us, where we tried that and applied that for estimating the area level effects. That is the key point for more than 3,100 counties of the United States, and that gave some more precise information for the counties than using the Fairhariot model. Anyway, so now we're talking about vector level parameters. Theta I is a small area, mean vectors. Yi is the direct estimators. Modeling is very similar. Yi is theta I plus ei. Theta I is equal to bxi plus ui. The ei is the normal independent variance covariance matrix vi rather than a single variance, and the ui is a normal 0 lambda square sigma. That is the setup. See, we are keeping the area level effect same for all the components. So that is an important point. You can possibly generalize it, but we did not. Of course, it is a full Bayesian. We put a flat prior, which is customary for the regression matrix, but the posterior is still proper. Otherwise, the prior is improper, posterior is proper, and inverse Wishart prior for the variance covariance matrix. The key thing is the local parameters. And this is a very general way of putting. There was a time when people didn't realize they were putting one or other individual distributions for the lambda square, the most popular one being the horseshoe. We'll mention that later. But there are other priors also, and they're tackling each one individually, but they all can be brought under one umbrella by using this representation. Lambda square minus c minus 1, and L lambda square is a slowly varying function. For those of you who are not aware of slowly varying, don't worry about it. The property is something as x goes to infinity, L of ax over L of x is equal to 1. Think about, for example, the log of ax over log of x, which is, if you take the x goes to infinity, it is exactly equal to 1. And most of the priors can be brought under this umbrella setting. Next slide, please. I'm just giving some popular ones. Now, the first column gives the names of the priors and why it was, but marginalized over lambda square. It is not based on the distribution of lambda square. For example, if you put an exponential prior for lambda square, and then you have a normal prior for the theta, then it turns out to be double exponential or Laplace distribution. Normal gamma priors. Horseshoe is interesting. It is a special case of what I put later, 3-parameter beta normal. This is a very general class. I love it. Put A equal to half and B equal to half, you get horseshoe. You put A equal to 1 and B equal to half, you get the Strodom and Barger. But that's also a special case. A equal to 1 and put an arbitrary B positive, that is normal exponential gamma. There is also a generalized double Pareto. That's a little more complicated. And people have written separate papers on that, but they all can be brought under this umbrella. There is a whole bunch. Next slide, please. Can I go back to the previous slide? One point I would like to mention. Sorry, I missed one important point. If you look at this prior, I used to call, because of my Calcutta University education, type 2 beta, because if you take x over 1 over x, that ratio, it is just a simple beta distribution with parameter A and B. But nowadays, there are 3-4 other names. One of my students call it beta min, somebody called something else, beta something else, whatever it is, there are 3-4 names. I will call it a type 2 beta. That's and possibly most people in India will call it type 2 beta. Next slide, please. So notations, why is this? The whole vector of this, and it is a random matrix. X is also a random matrix. U is a random matrix. D lambda is a diagonal matrix. And lambda square is the vector of all the local area level variance components. Rank of X is still P. Now, what is the matrix variate normal? Matrix normal Z, actually, in general, it is, I'll specialize it immediately. It has a mean, the variance is a cross product of W and R. That's what it is, all it is, and that is the matrix normal. Think about an M by P, okay? M rows, which denote the samples, P columns. So each vector is a P component vector. All right, that's all. And people has a symbolic version of it, rather than writing it every time the density. They call it multivariate normal, M and W and R. In our special case, it turns out this is a matrix normal with mean 0. The W is d lambda and R is the sigma. You can think about it, each component has mean, say, mi, zi, and the variance is sigma. That's all. The posterior is proper, even if pi b is improper, if lambda square and sigma has proper PDFs. Next slide, please. Implementation, I'm not going to go to the details. All it is, the theta i's are normal. You can easily generate, it is Markov chain Monte Carlo, the Gibbs sampler. You can easily generalize. The B is also a matrix normal. Again, software is available. Sigma is inverse Wishart. This one is tricky. It depends on which, this part is a normal part. This part is not a problem. But what about, depending on the prior, you put on lambda I squared, the pi lambda I squared, but we put something simpler, that all the special cases of 3-parameter beta normal, and then if you use some kind of parameter augmentation, then everything, an extra parameter, everything becomes very standard. Next slide, please. Generation is simple. Little bit of theory. The ability to assign non-trivial probability to both near 0 and in the tail. So multivariate global local models captured both large and small area effects. The interesting thing, what is the expectation when I have not put any distribution of the local parameters, the regression, the variance covariance matrix, the error variance covariance matrix sigma, it becomes this. So just look at it. If VI sigma inverse is very large, what does that mean? You can think about it. This thing, that means if VI is small, if sigma is small, compared to, if the error variance is small compared to the area level log variance is small compared to the error variances, then of course it will shrink everything towards the regression coefficient. And opposite is the case if the error variances are small compared to the area level variances. And this is called shrinkage factor, and you can write it also alternatively in the form sigma plus VI over lambda I squared inverse, and then VI over lambda I squared. Think about it that way. A larger shrinkage factor causes more shrinkage and produces an estimate closer to the synthetic. And the following one gives using the Frobenius norm of the shrinkage factor, just again, a big terminology possibly. What is the Frobenius norm? Take a random matrix or anything, any matrix, n by p, say, call it whatever you want to call it, A, n by p. The Frobenius norm is the square root of trace of A transpose A. That's all. Trace of A transpose A is also trace of A transpose, as we all know. Next slide, please. How much time I have? 10 minutes? 5 minutes? Whatever. I will. How much time I have, sir?
You have about 7 minutes.
7 minutes, that's good enough. Okay, so all I'm saying is, this is the important thing. If the variance covariance matrix is 0, the shrinkage factor smaller than any epsilon, any epsilon has to go to 0. And again, the next slide, as I said earlier, in words, theorem, next theorem, next slide. And theorem 2 says exactly the opposite. If sigma inverse goes to 0, then what will happen? Then, of course, sigma is going to infinity, the error variance, so everything will be shifted toward the synthetic estimates. Bigger than any number will go to 0. shrinkage factor, close to 0. Next. Data analysis. We have a 4-dimensional response, which is the median income of house owner, renter, married and unmarried population. And data was aggregated at the US state level, including District of Columbia. And it is a public use some micro data. Besides the intercept, very simple model. Only per capita income was included as auxiliary variable. We scaled down the data by dividing each component by 1,000. And we have used 4 different models based on different choices of the local priors. The global prior is the same, just one distribution, inverse Wishart. So estimate the 4-dimensional random effects. Use the Laplace and horseshoe, Strodden-Barger, and normal exponential gamma. The picture doesn't say much, except that you can see many of the areas are hovering around 0. And some of the areas are really not outliers, standing out as such. For example, I think for owner, Utah and Hawaii, they're standing out. Same thing about married or unmarried Iowa. The renter, the married one, it is District of Columbia. It is kind of standing out completely out others. Next slide, please. I'll give you the results. What we found actually, the horseshoe, which is the most popular nowadays, Laplace, Fay-Harriot, all performing similarly in detecting, so why the new thing, of course you might say, for those 3 of the 4 component vectors. One exception is the married category. You can still single out for each. If you go back to the previous picture, you can say that Fay-Harriot doesn't capture all of them, but the married category, horseshoe is doing the best in detecting the large area level effect for the District of Columbia. What I want to underscore is the objective is not just to ensure the presence or absence of the random effect, but to find the extent to which the area level random effects has its influence in estimation of area level parameters. This is the adaptive nature of the proposed models, is possibly their most appealing aspect as I see it. Next slide, please. Data generation, we kind of mimicked this. 50 states and District of Columbia, 4 random effects p equal to 2, but this time we are not using the original data for all the states. We are generating data using this model. Actually, we are not also putting a flat prior, obviously, for data generation. We are putting the least square estimate for the real data set. This is the interesting part. We have several generation for the random effects. One is a common sigma. That means what? If it is all common, there is no lambda squared there, it is the Fay-Harriot should be doing best. But let us see whether we can come close to Fay and Harriot. The second one is the mixture prior. We are not taking any of ours. Which one we mimic very closely. Sigma I is just like Datta and Mandel. It is a mixture of actually 2 normal distributions, one with a very small variance covariance matrix and the other with a very large variance covariance matrix. And the third one is lambda square sigma, but we are trying to neutralize it. Many different lambdas equally spaced between 0.1 and 10, and UI is normal 0 sigma. Next slide, please. Next slide. The priors. The priors for the UIs, Fay-Harriot, horseshoe, Laplace, Strodden-Barger, Nevetic exponential gamma. We took the inverse Wishart for high. Nu naught is 4. MCMC ran 20,000 iteration. First term discarded as Bernie. So theta hat is the posterior mean of theta I. And what we computed the average absolute deviations, average squared deviations, average relatively absolute deviations, and average squared relatively absolute deviations. So next slide. And sigma, the first one is best variant, but we are cutting close. 0.494301.19, we are really coming close, 0.50. So what you say, how do you want to choose one of your local parameter priors? Really, I don't have a recommendation. Possibly horseshoe, although this one, horseshoe is not doing a slightly worse, not much. But horseshoe is typically what people use, easier to implement, easier to describe, because you can think about a half Cauchy prior for the standard deviation. If you use a half Cauchy prior for the standard deviation, for the variance, you get a horseshoe prior. That's how the horseshoe is generated. Okay, next slide. The second setting. This is our setup. So one of us should be doing better. We are doing a lot better than Fahrenheit. This is the ideal situation for us. Although we are not using our technically global local, we are taking a scenario which is more suitable for global local, so it is doing better. And again, horseshoe is doing the best in almost 3 out of the 4 situations, although the others are again pretty close. Laplace is not doing as well sometimes because it is trying to pull everything towards 0, more zeros than anything else, or more small random effects than anything else. So this is our ideal situation. And the third one, it is a very neutral situation where everybody will be doing well. Next slide, please. So setting 3, everything is the direct subst always bad. We are doing better than Frey-Harriot's, obviously, but here Laplace is doing better because we have sprayed everything. There will be more shrinkage towards 0. So Laplace is doing the best actually out of all these priors, although average relative bias or average squared, they're doing about the same. But for average squared deviation, Laplace is doing better. And horseshoe, even if people recommend all the time, as you can see, many of ours, like Stroderman-Barger, normal, exponential, gamma, they are also doing better than horseshoe. I'm about done. I think next slide. My final remarks. Issue of multivariate sparsity. So what is the sparsity here? It is not sparsity of, typically one is what? Sparsity of genes, micro experiments. That's where people started thinking about this kind of prior with sparsity. Because, for example, although there are possibly millions of genes, only a few have the effect on type 1 diabetes. And Wellness Remarks said only 7 of them, type 1 diabetes. So how to select that? We are able to estimate the random effects for different correlated groups, correlation structure, etc. Some concentration inequalities for tail behavior of shrinkage factors. For our multivariate global local model, can identify states with insignificant random effects as well as the few states which have large random effects. Thank you very much. Thank you for moving the slides for me. I really appreciate. I wish I could flip my own slides, but that is not possible according to our university regulations. Only if you use the Zoom, we can do it. Share the screen. Otherwise, we cannot share the screen. Thanks again.
Thank you, Professor Ghosh. Any quick question? Ashish want to ask some questions.
Yes, Ashish, please.
No, I don't want to ask a question. Just anyway, it's a very interesting talk. I've been thinking about it. So, about the choice of your priors. No, Maulana, anyway, very warm welcome to you to Calcutta.
Thank you.
And look forward to meeting you if possible. Okay. Thank you.
Well, I've been
Thank you.
eyesight spies. I've been working with Arijit Chakravarti a little bit because we have some. He also works on these global local things very much, and as my students also. So these global local things are used quite a bit. Thank you.
Professor Ghosh,
Arijit has been a very proficient researcher, very good and sincere researcher. I'm sure your collaboration will be fruitful to eyesight, very helpful for the academic community.
Thank you.
thank you. Professor Ghosh, I have a very general query.
Yeah.
See, when we apply MCMC for complex models, which involves, dimension of the parameter is high, complex expressions of conditionals.
Correct.
One problem that we face is the probability of acceptance is very low. So people suggest HMC and things like that, but I find most of them more or less similar. Did you face any such kind of issues in this particular study or otherwise?
Yeah. The microarray people will laugh at me. For them, large means 4 million, maybe. For me, large means 3,100. For 3,100, it is okay. But for 1 million, even it is not. One of my colleagues, several of my colleagues have said, actually, Matt Wand of Australia is one. There are others, Michael Jordan from Berkeley and others. They talk about variational Bayes.
Okay.
I have some reservations about variational Bayes myself, but what they say that variational Bayes can do things faster. But nowadays, there are other options, isn't it? Sanjay Chaudhary of NUS, and there are many others. Sanjay is not the only one. They talk about the Hamiltonian Monte Carlo.
Yeah, HMC. Right.
Hamiltonian thing. And those things possibly will work well. Yes, I totally agree with you. The straight MCMC with millions of data is a useless thing in some sense. It will take you ages to implement your procedure. Luckily, I have not faced any such problem. One time we did classification of gene expression data, but that was not a big data. Okay. Only 600. Okay. 600 covariates, but sample size was 25. So it was a large p, small n. That was okay, but implementation of the MCMC was easy. Okay. Even if it was a large p, small n, 600 covariates, 25 samples, it was easy to implement, believe me. I don't usually do the implementation, but my colleagues do. And when they say something, I usually trust them. Yeah. And I think they're right in this case.
Thank you, Professor Ghosh. So thank you very much. It was an excellent presentation. I have one, the youngsters should learn how to make a good presentation. So actually, because as always, he is so energetic and enthusiastic. This is how one should actually make presentations.
Okay, thank you.
This is just a suggestion to the youngsters.
I will take the compliment, but I will thank you.
Thank you, Professor Ghosh.
Thank you.
Over to Sadish Kumar.
Thank you.
Thank you, Professor Ghosh, for your wonderful presentation and wonderful talk. In fact, several are benefited, no doubt about that. Also, we extend our gratitude to Ramanathan for chairing the session in a very nice way. And on behalf of the organizing committee, we would like to extend our gratitude to Professor Malay Ghosh and Professor Ramanathan for your support.
Thank you very much.
I hope you will continue to support us.
Sure.
Professor Malay Ghosh, thank you so much.
Thank you.
Since Professor Malay Ghosh is now in India, that is why we scheduled the talks in this time. Thank you so much, Professor. Neha, please. Neha, please extend the gratitude, extend the thanks to Professor. on behalf of the student. Neha?
Okay, sir. It will be my privilege to introduce Professor Malay Ghosh, currently a distinguished professor at the University of Florida. He completed MA in 1964 from University of Calcutta and was awarded PhD in 1969 from University of Carolina. Some of his areas of research include non-parametric inference, sequential analysis, decision theory, Bayesian statistics, and small area estimation. He has co-authored 2 books and more than 250 research publications and is the advisor of over 40 PhD students. Dr. Ghosh is elected Fellow of Institute of Mathematical Statistics and American Statistical Association. We are indeed honored to have you here, sir. Once again, on behalf of the organizing committee of ICSTC 2022, I extend my gratitude and thanks.
Thank you.
Thank you, Professor. It's for the participants' awareness. That's why. Okay, Professor. Thank you so much. Now let us move to the next session, session 13. Here, Gokul, please introduce the chair and do the support to the chair. Before another announcement in this time, our 2 parallel sessions, 13B and 13C, on contributory sessions, and one for the competition of the best paper, research paper. The preliminary will be on that 13C. So please, those who are interested can join those parallel sessions too. Now let us move to the next session. Gokul, please introduce the chair and do the needful.
A warm welcome to everyone. I hereby welcome you all to the technical session 13 with the session chair, Dr. K. Jayakumar. He is currently working as a professor and head of the Department of Statistics at the University of Calicut. He has 25 years of PG teaching experience and 30 years of research experience. His areas of specialization.
Just a minute, whether Jayakumar joined or not, we have to check. Just a minute.
Yes, I am here.
Please continue. Please continue.
Dr. K. Jayakumar has 25 years of PG teaching experience and 30 years of research experience. His areas of specialization include distribution theory, time series analysis and forecasting, statistical inference, and stochastic modeling and probability theory. He was the president of the Kerala Statistical Association and is a life member of the Indian Society of Probability and Statistics, Kerala Statistical Association, and member of the International Indian Association Statistical Association. He has received many awards and honors, including the Jan Tinbergen Award. He has published more than 100 research papers. We are really lucky to have you with us, sir, chairing the session today. Without delaying you further, I once again extend a warm welcome to you on behalf of the organizing committee and kindly request you to take over the session. Over to you, Professor.
Thank you. Thank you. In this session, we have, may I audible?
Yes. Audible.
In this session, we have 2 speakers. One is Professor K.K. Jose, and the second speaker is R.L. Shinde. The first talk is on the topic Pythagorean and Gumbel count models and their applications. Professor K.K. Jose, please.
So thank you, Professor Jayakumar, for giving this occasion. I am grateful to Professor Sadish Kumar for organizing this program actually, so that is actually giving a very good opportunity to all of us to listen to these international speakers. So I will be coming to my talk. So the topic of my talk is actually Pythagorean and Gumbel count models and their applications. So as far as this is concerned, this is actually concerned with some climate modeling or modeling of statistical data to different distributions, which are, the data is actually with respect to climate change and so on. In earlier days, the association between climate change, I am audible? All right.
Yes.
Okay. In earlier days, the association between climate change and incidence of diseases have lacked quantitative support, especially for cholera, chikungunya, and other diseases, with less consensus on environmental factors. Very recently, Miguel et al. Studied the influence of temperature and rainfall on the evolution of cholera epidemics. Then Mercedes et al. 2002 analyzed the quantitative evidence on incidence of cholera and climate change. And Michael et al. Studied the seasonality of cholera from 1974 to 2005. Changes in temperature and rainfall will lead to frequent occurrence of floods, droughts, as well as heat and cold waves, causing threat to all sensory creatures and habitat, including flora and fauna. The untimely rainfall in Kerala, so that has been every year affecting the entire region and causing damage to crop, then floods, loss of animals, widespread of diseases, and so on. It is estimated that farmers in Kerala, the southern state of India, could not harvest paddy. That is also every year. So, for example, in 2010-11, so they lost rupees 128 crores because of this untimely rainfall due to unexpected flooding in the fields during the year 2010-2011. And it is worst affected by Kuttanad, Alapi area, which lies below the sea level, which is a well-known center for paddy production in Kerala. Is the worst hit area, along with a few other regions in the state. This loss is immediately reflected in the price of rice in the state, which is already in an all-time high. So now the price has gone above 50 rupees. So it is also a matter of concern that the untimely rain may cause an outbreak of infectious diseases, like cholera. The state had witnessed infectious disease in the last few years during rainy season, and particularly chikungunya, dengue fever, rat fever, and many such diseases are emerging in this region. There had been reports of jaundice attack at many places in Kerala. In recent report in the daily news paper Hindu, it is noticed that abrupt changes in precipitation and temperature are the main characteristics of climate change. Hence, both the government and scientists must explore the relation between the incidence of epidemics and climate change. The present study is motivated by these alarming facts. So even though politicians say or scientists say this is all because of climate change, not much empirical studies are happening in our state. That is actually why we have conducted such a study. So as far as these models are concerned, Poisson models are usually simple, and they are actually the starting point. The common regression model for the number of events in a given interval of time, or count data, used by most researchers is the Poisson model. The widespread popularity of Poisson model for count data arises from its simple derivation as the number of arrivals in a given time period. And we have the inter-arrival times as exponential distribution. But of the many other count models that have been developed over the years, Wimmer and Altman, 1999, very few share this straightforward connection between a count model and the timing model or the inter-arrival time distribution. Usually, a Poisson autoregressive model controlling for seasonality and trend was built to estimate the association between the increase in the number of epidemic diseases and climate factors such as daily maximum temperature and rainfall. The goodness fit was assessed through the standard Poisson regression models by looking for the model that minimized the residual autocorrelation graphically through examining the simple autocorrelation function, then the partial autocorrelation function, and their plots. So from the relationship between a count model and its timing process, a researcher can develop a model using one form, either the timing, that is the inter-arrival time distribution, or the counting process, but apply it using the other. For example, marketing managers and health statisticians frequently collect inter-arrival time data and make predictions of the number of arrivals or purchases, number of treatments, or number of patients for treatment, etc. So that a particular customer or patient is likely to make over the next year. So the Poisson count model is valid only in the case where the data of interest support the restrictive assumption of equidispersion, that is, the conditional variance equals the conditional mean. But typically, the conditional variance in many cases exceeds or is less than the conditional mean. When it exceeds, it is called the over-dispersion, and otherwise, it is the under-dispersion situation. So in the case of many data sets, equidispersion is just a belief only that. So there are also cases where the conditional mean exceeds the conditional variance. In either case, the estimation based on Poisson model is inefficient and inadequate and leads to biased inference. So Winkelmann, 1995, cites various examples, various data sets. Thus, the Poisson model becomes inadequate in most of the biostatistical and socio-econometric applications. The Poisson model would be ineffective when the data is over-dispersed or under-dispersed. In such situations, we have to develop alternative count models which are effective in forecasting the climate variability. A heterogeneous gamma Poisson or negative binomial model is the first count model invoked for this purpose. And another is actually to accommodate the data sets with under-dispersion. Statisticians considered this, and various papers have come out. King, 1989, Cameron and Johnson, 1997, Cameron and Trivedi in 1998 are such examples. But with the possible exception of a count model featuring gamma distributed interval times proposed by Winkelmann, none of these under-dispersed count models offers the conceptual elegance and usefulness of Poisson exponential connection. An important entity for the analysis of durations used to capture duration dependence is the hazard rate, which gives instantaneous exit probability conditional or survival rates. So hence, here we consider the hazard rate, which is the ratio of ft divided by f bar, 1 by minus ft, or which is actually the derivative of d by dt of logarithm of ft, where capital Ft actually represents the cumulative distribution function of the inter-arrival times. The hazard function captures the underlying time dependence of the process. A decreasing hazard function implies that the waiting time is less likely to end. It will last longer. The situation is referred to as negative duration dependence. An increasing hazard function implies that the waiting time is more likely to end the longer it lasts. So a speedy ending. This situation is referred to as positive duration dependence. No duration dependence corresponds to the case of constant hazard. So if you are having exponential situation, there is no duration dependence at all. The hazard rate is constant if and only if the distribution of waiting times is exponential. So these are actually some common results. Yes. So we assume that the waiting times between the events are independent but not exponential. Instead, they follow some other distribution with a non-constant hazard function. If the hazard function is a decreasing function of time, the distribution displays negative duration dependence. If the hazard function is an increasing function of time, the distribution displays negative duration dependence. If the hazard function is an increasing function of time, the distribution depends positive duration dependence. In both cases, the conditional probability of a current occurrence depends on the time since the last occurrence rather than on the number of previous events. Events are dependent in the sense that the occurrence of at least one event, in contrast to none, up to time t influences the probability of a further occurrence in t plus delta t. So there is a link between duration dependence and dispersion. So that is also important. If we denote the mean of the interval time distribution by mu and variance sigma square, then we say that the distribution has negative duration dependence if the derivative of the hazard rate function is less than 0, and positive duration if the derivative of the hazard rate is greater than 0. If the hazard function is monotonic, then we have sigma by mu less than 1. And the other situation, if d by dt of ht equal to 0, that is constant, in that case, sigma by mu is equal to 1, that is equidispersion. If d by dt of the hazard rate is less than 0, then sigma will be greater than mean. So that is over dispersion. So the three cases correspond to count data characterized by under dispersion, equidispersion, and over dispersion respectively. It is shown that negative duration dependence in the asymptotic case at least causes over dispersion, and positive duration dependence causes under dispersion. The Poisson process can be taken as a sequence of independently and identically exponentially distributed waiting times. To derive a generalized model, we replace the exponential distribution with a less restrictive non-negative distribution. And possible candidates are the Weibull distribution. So that has been extensively studied by McShane in 2008, McShane et al. In 2008. And another is the gamma. So that has been studied by Winkelmann in 1995. And the log normal distribution and so on. So for details, see Bratlow et al. 2002, Everson and Bratlow 2002, Miller et al. 2006, and so on. So both Weibull and gamma nest the exponential distribution. So exponential distribution is a special case of Weibull, and gamma distribution we all know. And both allow for a monotone hazard rate function that is duration dependent. And myself, Jos and Bindu, 2011, developed a count model with Mittag-Leffler interval time distribution. And another count model in 2013, we developed a count model with the Gumbel interval time distribution for modeling climate data. So here, so in the present paper, we replaced the exponential distribution by Mittag-Leffler and type 2 Gumbel distributions, where Weibull and Frechet are the special cases. So the corresponding count models are formulated, which next Poisson process as a special case. The Mittag-Leffler and Gumbel interval time models are richer than the exponential because they allow for non-constant hazard rates. And we can derive the models by using a polynomial expansion. So specifically, Mittag-Leffler distribution was introduced by my professor, Professor Aaron Pillai. So the function, the Mittag-Leffler function, E alpha Z equal to summation over k equal to 0 to infinity z raised to k by gamma 1 plus ak. So this was first introduced by Mittag-Leffler in 1903. And it is actually common in mathematical areas, mathematicians, along with mathematicians who have conducted various studies on Mittag-Leffler functions. It was subsequently investigated by Wyman, Pollard, Humbert, Agarwal, and Feller. Many properties of the function follow from Mittag-Leffler integral representation. During the last 2 decades, this function has come into prominence after about 9 decades of its discovery by Mittag-Leffler because of the vast potential of its applications in solving the problems in physics, biology, engineering, space sciences, and earth sciences. So we can see many research papers in these areas. The Mittag-Leffler function arises naturally as the solution of fractional order integral equations or fractional order differential equations, and especially in the investigations on fractional generalizations of kinetic equation, random walks, Levy flights, fluid dynamics, super diffusive transport, and in the study of complex systems. So that is available in mathematical literature, physics and astrophysics, and fractional calculus, and so on. It may be verified that, so E alpha Z, we can have the integral representation also, some complex integral representation. And it may be noted that it was Pillai, Professor Aaron Pillai, in 1990, proved that this f alpha x equal to 1 minus E alpha minus x raised to alpha, where 0 less than alpha less than or equal to 1, represents distribution functions having Laplace transform 1 by 1 plus t raised to alpha. So which is completely monotone for 0 less than alpha less than or equal to 1. And he refers to f alpha x as the Mittag-Leffler or the CDF of the Mittag-Leffler distribution. The Mittag-Leffler distribution is certainly a generalization of the exponential distribution, since for alpha equal to 1, we will be getting the exponential case. So Pillai has shown that f alpha x is geometrically infinitely divisible and is in the class of in the domain of attraction of stable laws. It belongs to the classal distributions and so on. Some problem. Some problem is repeating.
Yeah. I think it is better to restart the sharing.
Yes.
Stop sharing.
I will.
Share it once again.
Okay. I think it is coming. Okay. So, sorry for the interruption. So
Yeah,
actually, no problem.
No, it is fine, sir. Please.
Okay. So as far as the material order distribution is concerned, the material order function arises naturally as the solution of fractional order integration and so on, and that is applied in various areas of astrophysics and so on, fractional calculus, etc. So it was Pillai, 1992, who introduced the material order distribution, and the material order distribution is a generalization of exponential distribution. When alpha equal to 1, we get the exponential distribution. So Pillai has shown that it is geometrically reproducible. It actually belongs to the classal distributions, and it is in the domain of attraction of stable laws. And Jagumar has done has published various papers on material order distribution and its generalizations. Then a random variable x has the material order distribution if its cumulative distribution function is given by fx alpha equal to summation k equal to 1 to infinity minus 1 raised to k minus 1 x raised to k alpha divided by gamma 1 plus alpha k. Then the PDF is also having a closed expression. Recently, material order distribution have received the attention of mathematicians, statisticians, scientists in physical and chemical sciences. It can be used in reliability modeling as an attractive alternative for exponential distribution. Jagumar 2003, Lin 1998, Jagumar and Pillai 1993, myself, Joseph and Pillai 1996, etc. have done extensive studies on material order distribution and its generalizations. Joseph et al. 2010 extended this to develop a more generalized material order distribution. Hillett 2016 investigate various stochastic processes where they play a key role, among which include the discrete space-time. Never a branching process, the discrete space continuous time process have been developed in branching processes and renewal processes, the rare events, etc. Its relation to self-decomposability and branching process with immigration has been studied by Neve and his colleagues. Now we will be coming to the material order count model. So we can describe a general framework utilized to derive the model that is based upon the relation between inter-arrival times and their count model equivalent. So let yn be the time from the measurement origin at which the nth event occurs. Let xt denote the number of events that have occurred up to time t. The relation between inter-arrival times and the number of events is, so the sequence gamma yn less than or equal to t is equivalent to the event xt greater than or equal to n. That is a standard result in counting models. So here, m and t, that is probability that xt equal to n, that is same as probability xt greater than or equal to n minus probability xt greater than or equal to n plus 1. So that is actually the usual method for discretizing distributions. So that is actually probability yn less than or equal to t minus probability yn plus 1 less than or equal to t. And using this, we will be getting m and t equal to probability xt equal to n that is equal to fnt minus fn plus 1t. And using that, you can obtain the probability that xt equal to n. So in this case, when the measurement time coincides with the occurrence of an event, it is simply the n-fold convolution of the common interval time distribution, which may have a closed form expression, in many cases may not have. And now, we assume that the interval times are independent and identically distributed according to Mittag-Leffler distribution instead of the usual exponential or usual variable or gamma. To obtain the equation, we use the recursive relationship m and t equal to this one that we can obtain. So that is actually the convolution. So integral 0 to t fn minus 1 t minus s fs minus integral 0 to t fn t minus s into fs. And that will give you the integral representation or recursion relationship. And before that, we can obtain. So before proceeding, we develop the general solution to the problem. We note that fnt is equal to 1 and fit, that is the interval time distributions, are all commons, that is IID. So fit is equal to ft for every t. Therefore, we have m0t minus f0t we can obtain very easily, that is f1t minus f0t minus f1t, which is 1 minus ft, which is having this closed form expression. And that will give you this expression. And we will be going to the next one, that is actually m1t, that is probability that xt is equal to 1. And that is having this expression m2t. And this actually we are stating in the form of a general result. So if the interval times are independently and identically distributed as Mittag-Leffler distribution, then the count model probabilities are given by m and t equal to probability xt equal to n is equal to, this is the closed form expression. And we have the properties. The Mittag-Leffler count model generalizes the most commonly used models such as the Poisson case. So when alpha equal to 1, you can see that it actually leads to e raised to minus t, t raised to n by n factorial. This is a Poisson process with unit rate. Mean and variance of the Mittag-Leffler distribution. We have closed form expression. The mean is the mean function expectation of xt is equal to t raised to alpha by gamma 1 plus alpha. And variance of xt also having a closed form expression. And the Hazard function is also having a closed form expression. Certainly it will be difficult. So we have conducted simulations and we have computed the values. So through extensive simulations, we have verified that the Hazard function of the Mittag-Leffler distribution is a decreasing function of time. And here is the graph. The model can be handled for over-dispersed as well as equi-dispersed data. So that is actually specialty. So when alpha equal to 1, it actually coincides with the exponential. So it can be used for modeling equi-dispersed data. Otherwise, when alpha is less than 1, it actually corresponds to an over-dispersed case actually. So here is actually the graph of the hazard rate function. So it is very clear that it is actually decreasing. So if the interval times of the data set are Mittag-Leffler, then we have a corresponding count model to use. The model is derived from Mittag-Leffler timing model. The link between the timing model and its counting model equivalent is maintained. Hence, in those cases where the analysis of interval suggests that a more flexible timing model is needed, it can now be incorporated via its count model equivalent. Furthermore, in those cases where the only one has count data, but would like to make forecasts of the next arrival time, this can be done using this count model and timing equivalent. And however, the Mittag-Leffler model can be used for over-dispersed and equi-dispersed data also. So that is actually a limitation of Mittag-Leffler model. Now we are actually proceeding to another one which actually accommodates both over-dispersed as well as under-dispersed cases. The Gumbel distribution was first developed by German mathematician Emil Gumbel. And Gumbel's focus was primarily on applications in extreme value theory. In engineering problems, it is common with engineers, then with the hydrologists also. In particular, for modeling meteorological phenomena such as annual flood flows. The Gumbel distribution is also known as the extreme value type 1 distribution. The cumulative distribution function is given by fx a b equal to 1 minus e raised to minus b e raised to minus alpha. So the moments exist for k less than a. So we can define type 2 Gumbel distribution also And here the polynomial expansion is actually made use of. So summation, the distribution function is summation j equal to 1 to infinity minus 1 raised to j plus k.
Sir, 5 minutes left.
Okay,
Sir,
I will.
5 minutes.
I will. So the PDF is there, and here is actually the hazard rate function. So we have the constant hazard rate, the increasing hazard rate, the decreasing hazard rate, and so on. And Gumbel has shown that the maximum value in a sample of a random variable following an exponential distribution approaches closer and closer to the Gumbel distribution with increasing sample size. In hydrology, therefore, Gumbel distribution is to analyze such variables as monthly and annual maximum values of daily rainfall and river discharge volumes. So Gumbel count model. Here also the same methodology is made use of. So GNT, that is equal to probability yn less than or equal to t minus probability yn plus 1 less than or equal to t, so that we will be getting the probability of xt equal to n as fnt minus fn plus 1t. And we have made use of the convolution methodology, and using the polynomial expansion, we can obtain the distribution as GNT is equal to, and 1 minus of f of t we can obtain, and that will give you the probability distribution function of the Gumbel process, Gumbel count model. And here is actually the values, and we can obtain the mean and variance also. And this model is suitable for both under-dispersed as well as over-dispersed cases. And the graph is also given here. So that is a simulated graph actually. Now we will be coming to figure 4 and 5 displays the situation when it is under-dispersed. And that is actually, we have the probability of histogram for an over-dispersed case actually. Then the model generalizes the most commonly used Poisson model. Certainly, you can apply it to over-dispersed and under-dispersed cases. And here we are giving a table of probabilities of type 2 Gumbel count model based on a simulation study. So here you can have the values, and we can see that the mean variance also we have tabulated, and there are under-dispersed cases. Then we have equi-dispersed cases, that is for -1, and over-dispersed cases. So these values and the probability values as well as the mean and variances are also given for different parameter values of A. Then application to the real data set. So as far as the application to real data sets, so we are actually making use of some data on monsoon. That is actually according to World Health Organization, an outbreak of chikungunya. So that was actually, so you remember, in 2006, 2007. So all over the world, especially in India, peculiar in Kerala, it was actually very much affected. And that was actually the situation where we have considered, and we have obtained the data, and that data shows positive correlation with the chikungunya incidence and rainfall. And there are other reasons. And the outbreak of chikungunya in July 2005 to May 2006. So we have made use of that data, and we have considered that. And there, to study the climate change, so this is the relation, this actually shows the relation between temperature and the spread of chikungunya. Then, to study the climate change, it is necessary to know the pattern changes. For that, we have considered the mean, variance, and so on. And the monthly rainfall of the data shows that the conditional mean is 1.5 and the conditional variance is 1.3, so that it is over-dispersed data. And in that case, we have made use of the Kolmogorov-Smirnov test, and we have fitted the Gumbel distribution to the data, and it is found to be a very good fit. And the probability histogram of the expected number of months having extreme rainfall has been considered. And to estimate the number of months having extreme rainfall, we use the Gumbel count model, and that has been made use of, and we have obtained the data. Similarly, the maximum temperature in Kerala, so that has been considered. For that, the conditional mean is 1.75 and the variance is 6.25. So it is over-dispersed data. And there also, we have considered the Kolmogorov-Smirnov test, and we have showed that it is actually following the Gumbel distribution, and it has been made use of for obtaining the probabilities also. And these are actually the diagrams. And finally, we will be coming. So here we have introduced two new count models based upon Mittag-Leffler and Gumbel arrival time processes for studying climate variability. More importantly, the models provide a sizable improvement over the more traditional Poisson process. One important advantage of the new models is that it removes the artificial symmetry between over-dispersion and equi-dispersion. The new models are actually allowing enabling us to develop models for over-dispersed data as well as the under-dispersed data. In the case of Mittag-Leffler case, we are having over-dispersed or equi-dispersed case, whereas in the case of Gumbel model, so for the study of the relation between the number of chikungunya incidents and set of climate change, it is clear that epidemics is positively correlated with the climate change. To forecast the epidemics like chikungunya, the new model can be used as a tool for prediction of climate change. And during last year also, when last 2 years, when we are experiencing COVID also, so people were saying that there were some, scientists were saying that there was some connection between temperature and so on. Anyway, it has been ruled out scientifically. Now, the new Gumbel model can be applied to real data sets of climate where the assumption of equi-dispersion is violated. Thus, this new model can be used to study climate variability in an effective manner, which provides an opportunity for epidemic forecasting also. So these are the references. So the paper by Hallett on Mittag-Leffler distributions. Then myself and Bindu, K.K. Jose and K. Jayakumar's paper with R.N. Pillai, K. Jayakumar's paper on Mittag-Leffler distributions, and so on. My paper on generalized Mittag-Leffler distributions. And actually, we have made use of this paper, R.N. Pillai's paper on Mittag-Leffler distributions, then, and so on. So thank you. So certainly, I have introduced this, people, so youngsters can think of such models in the COVID, with COVID data also. So thank you. Any questions?
Thank you, sir. Thank you very much. Any questions or comments from the audience? Otherwise, let us thank Professor K.K. Jose sir for giving a very good talk on the count models with Mittag-Leffler distributions and the Gumbel distribution. Thank you, sir.
So,
thank you very much.
So, thank you, Professor Jayakumar and Professor Satish Kumar, for providing this opportunity. Thank you very much. Thank you.
Thank you, Professor. Thank you.
Thank you, the audience. Thanks to audience also for their listening. Okay.
Our next speaker is Professor R.L. Shinde, and he's talking on the topic stochastic mortality modeling for Indian population and its applications. Professor Shinde, please. Is it audible?
Professor Shinde, not audible. Secondly, I don't know whether I started or not.
He started sharing the screen, but now it's not seen.
Probably there is a network, weak network. Professor Shinde, whether you are muted or there is some problems with your audio. Also, you have to share not share the screen. Shinde, we can see your desktop, not the slides. You please go to the slides.
There is some problem in presentation, so
Yeah, let us wait 1 or 2 minutes because he is trying to share his screen.
okay.
Professor Shinde, do you have any difficulty in the presentation there? The sound is, no, we can't able to hear you. We can't hear you. Probably your mic, the computer, where there is some sound is muted probably. Uh, if there is a computer, the problem with the computer, to switch off the shut down the computer and restart. That's better. Or otherwise, there is a switch with the okay.
Now also is not audible. That's the problem.
You can share your slides to me and you can speak from there using your mobile. Probably that's maybe better.
That may be possible. I think that's a good suggestion.
Can you hear me?
Now we can hear you. Can hear you.
But there will be problem.
Yeah, Professor. It's better whether you share the screen. Is it possible for you to send the slides to me? And mobile is not working well.
Can you hear now?
Okay. Yeah. Now it is fine. Now
It's okay. It's okay.
now we can see the slides and okay. Also, some audio. Volume. You please can after unmute the mic.
Okay, so sorry for interference. My talk is on stochastic modeling or mortality modeling for Indian population and its applications. Hope you are getting now. Are you getting?
Yeah. Audible, but the screen is not seeing. We can't see your screen now.
Can you see the screen?
No.
You please share it once again. Share the slides once again. It has gone.
Now can you see?
Now it is fine. Oh, now it is fine, but it has gone suddenly. Disappeared suddenly.
Now?
Once again, try. Now, not yet.
Okay, I will continue like this. Now you can see, I think.
Yeah, now we can see. Okay,
So,
please continue.
stochastic mortality modeling for Indian population and its applications. This is joint work with my PhD student. So, introduction, first of all, mortality modeling has been major area of such models were available, but the mortality modeling took the large step forward after arriving the Lee Carter's model in 1992. This is the first mortality model with stochastic forecast. Lee Carter model became very popular due to the simplicity in the parameter estimation. It has been fitted well for many developed countries. After Lee Carter, there has been some extensions of the basic Lee Carter model by including different factors. Among them, Booth and others consider the multi-factor age period extension of Lee Carter, 1992 Lee Carter's model. Then range RH model, they have proposed the cohort effect into the model, and Cranes and others, they have used logic transformation of this model for mortality modeling. Life tables generally they represent mortality profile of the community or country as a specific point of time. Life tables are usually constructed separately for men and women just because of their substantially different mortality rates. Other characteristics such as risk of smoking status, occupation, socioeconomic class, and other aspects can also be considered in order to construct the life tables. But here we have considered only two, men and women. Notations generally in life tables, I will not go in detail, but these are notations. X age of individual, px is the probability of surviving from x to x plus 1, qx is the probability of dying in the age group x to x plus 1, x year old will die in the next 1 year. L naught, that is Radix for population of newborn. Lx plus 1, that is the expected population at x plus 1. Capital Lx is average population, expected population in the age group x to x plus 1, or otherwise you can say total expected number of years lived between the age x to x plus 1 from the original L naught levels. Dx, that is expected number of death in the age group x to x plus 1. Tx is expected recurrence relation, Tx is equal to Lx plus Lx Tx plus 1, and Ex is equal to T of future lifetime of the individual of Lx. That is the expected life at age X, life expectancy at age X. Example specimen life table I have presented here. That gives you idea about the life table: Qx, Px, Lx, Dx, capital Lx, Tx, and find Qx is the probability of dying of newly born in first 1 year, and Ex is life expectancy at birth. So this is specimen life table I have given here. Why do we need the stochastic mortality model? Mortality rates have been declined, but the declines, this suggests that the future mortality rates will be uncertain, and this needs to be taken into account when forecasting. Due to the increasing focus on risk management and measurement for insurers and pension funds, the literature on stochastic modeling models has been developed rapidly during last 2 decades. stochastic mortality models either model the central mortality mx or initial mortality rate qx at the starting of age x or central mortality mx. So where mxt, where x is age of a person and t is the year of life table. So as we are going to consider many life tables here, that is why t is introduced here. Rate corresponding to age x and age year t. So mxt is the central mortality and qxt is the probability of death of person aged x and he dies before x plus 1 in the life table t of for year t. A relation between mxt and qxt, you can have qxt under constant force of mortality assumption if you apply on the probabilities qx. So qxt is equal to 1 minus exponential of minus mx. This relation one can. Stochastic mortality model is good if the model fits historical data very well. It applicable for the full range of age group, age range, captures the cohort effect and has a non and has no robustness structure is relatively simple. So here are some models from the literature, stochastic mortality models. The first one is Lee Carter model in 1992. This is log of mxt is equal to beta 1x plus beta 2x into ktx, where beta 1, beta 2 are the age effect they introduced, and kt2 takes care of random effect, random period effect. It is one factor model resulting in mortality improvement at all ages being perfectly correlated. The countries where the cohort effect is observed in the past, the model gives a poor fit to the historical data, this Lee Carter model. The uncertainty in future death rates is proportional to the average improvement beta 2x here. And the basic version of this model can result a lack of smoothness in the estimated age effect beta 2x. M2, second model, after 15 years, the Renshaw Haberman RH model came into existence. That is, log of mxt is equal to beta 1x plus beta 2x kt2 plus beta 3x gamma t minus x3, where gamma is random cohort effect is introduced here and beta are nothing but age effects. For countries where the cohort effect is observed in past, the model provides a significantly better fit for the historical data. However, French and others, they have find that the RH model suffers a lack of robustness problem. Furthermore, although the model has an additional stochastic factor, that is gamma, for the cohort effect, the most of the simulated mortality rates and correlation structure is still trivial. So other models are also introduced. Those M3, third model, log mxt is equal to beta x1 plus 1 by n alpha, where n alpha is number of ages in the data set, and k2 t is already introduced, that is period effect, and gamma is cohort effect. So similarly, if the Crane's Black down CBD model, this is basic CBD model. There are some versions of CBD generalizations. So the logic model, logic QXT, is log of QXT upon 1 minus QXT, that is K1T plus K2T x minus x bar. So two period effects are introduced here again. And similarly, their generalizations are given here, logic generalizations. And late in 2009, given log mxt as this model, where beta 1, beta 2, beta kt3, kt4, and gamma code, these are introduced here. These betas are the age-related effects, kts are period-related effects, and gamma cohort-related effects. N alpha is number of ages in the data set. X bar is the mean age of the range of that age group. Sigma square mean of the x minus x bar square, and xc is a constant parameter used in some model. So if somebody is interested in details of these models, so these are the references: Crane 2009, Plate 2009, and Overendley 2012 discussed this model thoroughly. Some constraints are put on the in this model, M1 to M10, 10 models we have considered. In those models, due to the problem of identifiability, the constraints are considered. These are different constraints considered in the model. I will not go through all those details, but in this study, our objective is to mortality modeling through above well-known stochastic mortality models for Indian female and male population for the age group 20 to 99 years. Assessment of best fitted stochastic mortality model through BIC, forecasting future mortality rates based on the fitted model, and forecasting actual present values of life annuities and life insurance by using forecasted mortality. These are our objectives. Life table data used in this particular study, we have used the average life table form data for the years 1999 to 2017. These data are available for male and female population separately for Indian population. Sample registration system, Register General of India, from where one can get this data. These life tables are presented yearly based on previous 5 years Indian mortality data. That is, life table for the year 1999 is presented based on the mortality data for the period 95 to 99. So 5 years, 99's life table is developed based on last 5 years data. Like that, these data sets are there. For 19 life tables we have used, and those for the ages 0, 1 to 5. Then like this, these tables are, this is the data set which we have used for the purpose of modeling. Ages 0, 1, 1 to 5, 5 to 10, up to 85 plus. This is the original data available, average life table form. For example, the 1999, the death rate was 0.079. That means 79 infant mortality out of 1,000. And then 2017, it is about 41 out of 1,000. Now it has come down to up to 35. This is for female population of India, and this is for male population of India. So this is the basic data used, and one can very easily go through the graphical presentation of the mortality rates of Indian female population. One can see the major concern of Indian population, female population, is in the this age group around 15 to 40. There is a hike in the sudden height in the death rates. This is for 99, 2009, and 2017. Three central mortality rates are plotted here versus this is for male population. There is no hike as seen in the female. the hike is lesser in male, because in female there are many impact that may be maternal deaths or dowry deaths one can observe here. But in male you can see smooth line here. Complete life tables, as the data available was in average life table for, and we have to make it for all ages x is equal to 0 and 2 onwards, and then one can go ahead by using those mortality, stochastic mortality models. So this is done by using the Whitaker's graduation, and this method is described in Lee and Chen 2004 in detail. One can go through that. And after graduation and complete life tables are observed, made available for ages 0, 1, 2 up to 99, year 99 to 2017. So this is a modified data for the complete life tables for Indian female population. Central mortality rates are presented here, and similarly for male population, this is from 0 to 99 for these 19 life tables. Now estimation part, where the Birling 1986 number of deaths which are considered as the counting random variable, and if you consider DXT is the number of death in the age group x to x plus 1 during the year t. T means life tables year, you can consider. DXT that follows Poisson with EXT multiplied by MXT, where MXT is the risk exposure, or you can say the expected number of survivals in the age group x to x plus 1 for the life table T. And the parameter values for estimated by maximizing the log likelihood function given by this model, this function, where phi is full set of parameters, and MXT phi denotes shows the MXT dependent on parameters. The model for which QXT have to be used for, then one can use the relation MXT phi is equal to minus log of 1 minus QXT phi. And for estimation purpose, one can use the R code. We have taken this R code from here, and this R code is modified as per our need. We have taken the hectare of ages from 20 to 99 because our aim is to talk about the mortality modeling for the Indian population in the age group 20 to 99, particularly keeping into mind the actuarial science applications, insurance application. Vector of calendar years, that is 1999 to 2017, matrix of death, DXT, number of death of person age X during the year T, matrix of risk exposure EXT, average number of person exposed in the interval X to X plus 1 in the year life table T, and matrix of W0/1, 0 for data not available or incorrect or otherwise 1. So considering this basic data with in our code, BIC criteria is used, and I will not go through all the details. Our data set is 80 observations, 80 age group age years multiplied by 19, that is 1520 data we have. All those 10 models are applied for Indian population, these 19 life tables, and the number of parameters for different models, different number of parameters are there. Maximum likelihood is noted here, and BIC. So maximum BIC is obtained for this model EMET. EMET is given by Platt in 2009. This model fits relatively well in these available models for Indian population for female as well as male population. And the time series models for cohort period effects and cohort effect. This is cohort effect, and these are period effect observed in this model. We have the period effects and cohort effect. Those are modeled through the time series fitted models are recorded here. ARIMA models are fitted. And estimated forecasted values of K2T, KT3T, KT4, and cohort effect gamma T minus X5. Those are given for female population as well as for male population. And one can see the forecasted central mortality rates for the years 2020, 25, and 30. 20, 25, and sorry, the blue is 20, red is 25, and green is 2030. So there is some increase in the age group 50 to 70. We are likely to observe in the central mortality rate in 2030 for Indian female population, as well as at old ages there is a increment in the. Similarly, for male population, slight from 55 to 70, we are expecting the hike in the death rate in 2030, and similarly 2025 2030 in the old ages also. So using these, one can find obtain the forecasted life expectancy for the Indian population, for female as well as male. For 20 at age 20, forecasted life expectancy is around 54.48 in 2025. But it is interesting that it is getting down in 2030, 52.57 expected life expectancy at age 20, and at 65 suppose it is 14.67, for male 13.89. So and by using these forecasted values of those period effects and cohort effect, and then we can obtain the net single premium or one-time premium for whole life insurance, that is capital AX, and the term insurance for 20-year term when the rate of interest considered is 7.5%. Then female and male population, this AX and net single premium for whole life insurance and 20-year term insurance. For example, for year 2025, we are expecting the net single premium for 20-year person for whole life insurance is 3.63%. That means for 1 rupee, 0.0363 he has to pay for 1 unit. Female, she has to pay, and for 20-year term, this one. Similarly, for male, you can compare these values. And this is for life annuities. Finally, whole life annuities are presented here, and second part presents the 20-year term life annuities. The life annuity means you will be getting 1 unit till the end of your life. At the end of each year, after signing the contract, at the end of each year, you will be getting 1 till the death occurs. So, for example, 40-year-old female has to pay in 2030 10.76 in order to get 1 till death occurs. Similarly, for 20-year term, you can see these values. So this is what I wanted to say, the application of mortality, and some references are there, those models references particularly. The model fitted for this was 2009 plate model. This model, this paper was published in Mathematics and Economics insurance, mathematics, and economics. So thank you for your attention, and sorry from my side for disturbances.
Thank you, Professor Shinde, for the nice presentation. Dear
If
speakers,
you have any question, you may ask.
any questions or comments from the audience, please.
Yeah, myself, Gopal from Chennai. Dr. Shinde. Hello? Hello? Do you hear me?
Yes, we can hear you, sir. So please
Shinde is
proceed.
there or not? Dr. Shinde?
Yes.
Professor Shinde, your presentation is really very nice. I have one doubt. See, you introduced the MXT using age last birthday. MXT, you introduced MXT. You know MXT, yeah, MXT. Hello?
Yeah. Okay.
And you use the definition age last birthday. Am I right? Age definition. There are 3 age definitions.
What is?
There are 3 age definitions. One is age last birthday, age next birthday,
yeah,
age nearest birthday. But in your definition,
age last birthday.
Yeah, suppose you change your age next birthday. Age from next birthday to nearest birthday. Do you understand my question? Automatically QX will change.
Definition of MXT.
Yeah, QX will change. If QX changes, MX will also get changed. Okay. If that is the case, whether your results will get changed or how do you answer this question? See, the QX is dx by ex, exposed to risk.
Yeah.
Okay. Therefore, if the age definition changes, will the Lee-Carty model will hold, or do you have any other model in view of that?
No, we are not using Lee-Carter model. All models are fitted, and flat model is giving better fit.
But you used the original MXT using age last birthday.
No, we have used the age at the last birthday.
Age last birthday.
Yes.
Suppose we change it from age last birthday to age next birthday.
And whenever required, in some models, QXT is required, we have used the relation between MXT and QXT.
Right. No, whether they are using only age last birthday or they are using age nearest birthday or age next birthday. That is my question.
Age at last birthday.
Okay, thank you. Thank you.
Any questions or comments from the audience? Any other questions? Otherwise, let us thank Professor Shinde once more. Thank you very much.
Thank you, sir. I am also thankful to organizers for giving me opportunity to present my work here. Professor Satish.
Thank you. In fact, we are grateful to you, Professor Shinde and Professor K.K. Jose for your excellent presentations. And also, we would like to extend our gratitude to the chair, Professor K. Jayaguma, for nicely managed the session. Thank you so much. In fact, we are grateful to you, Professor, once again. Let us meet in the future with regard to several. In fact, we need your support in several respects, Professor Shinde.
Okay. Thank you.
Professor Joseph, please. Also, now let us conclude this session, and next, okay, now the parallel session 13B and 13C are going on. Those who are interested can join there, but now there's a lunch break time for him. Let us take a lunch break time and join in this platform. We will meet at 1:40 p.m.
Yes.
It is after 9 minutes. Let us meet here in this platform. At that, there is a special session organized by Arpan Bhomik from Assam, a special session organized by him. And thereafter, the sessions of Narendra Kumar, Ashokan, Professor Ashokan Variat, etc. Anyway, we hope to meet after 38 minutes. So please join the meet by 35 itself, 1:35 itself. Thank you so much. Thank you all. Thank you, professors.
Hello, am I audible?
Yes, yes.
Sir, good morning. Good afternoon, sir.
Good afternoon. Good afternoon. Let us start the session. Okay. No. Please wait.
Sir, there will be some changes in the schedule, means ordering, because some of the
Yeah.
inviter speaker, they are
Yeah.
having some unavoidable work, so suddenly
Okay.
came. So ordering will be changed. Okay, sir.
Okay.
So
Okay. How many?
accordingly,
Now, how many are there?
I think Dr. Mandal sir have already joined. Sankalpa, Dr. Sankalpa have already joined. Eldo
Okay.
Varghese sir, the chairman and invited speaker also, he also joined. I also
Okay.
joined. Anindita is joining shortly.
Okay. Okay. So, how many speakers are there in this
There
session?
are total 5 speakers, including me and Dr. Varghese.
Okay. 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 We can start the session within 5 minutes, I think.
Okay,
Yeah?
sir. Okay, sir. Okay, sir.
Yes. Also, your students can also, you can encourage to
We
join.
have shared some of the known faces we are able to see here, sir.
Okay,
We have
okay.
shared, but
This-
since some examinations are going on, ARS interview and all those things, so
Okay.
maybe
This
they are not joining.
especially for design of experiments, those who
Yes, sir.
are working in the area are
Uh,
more. Yeah. Yeah. Interesting.
We have already shared, but actually some ARS interview program and all those things are going on. So maybe that's why
Yeah.
some of them have not joined.
Okay. Okay. Just a minute. Let us start soon. Okay. Okay. Swapna is here. Swapna? Hello? Hello, Swapna? Swapna? Okay, now let us start the session. Swapna? Swapna?
Yes, sir. Yes.
Hello, sir.
Okay. Okay.
Hello.
Okay. Okay. Yes, we can
Sir,
hear
can
you. I'm calling you all the time. That's right. Let us start the session without wasting time. Please, Sabna, please introduce the chair and also the session organizer, and thereby support them to run this session smoothly. Please. So, Sir Arpan, students are. Sabna, please.
Hello, sir.
Yes, yes, you please start.
Sir, is it audible?
Yes, yes, you are audible.
Okay. A warm welcome to everyone. I hereby welcome you all to the technical section 40 with the section organizer Dr. Arpan Baumik. He is working as a senior scientist at Indian Agricultural Research Institute, Gogamuk, Demaji, Assam, and also obtained his master's degree and PhD in agriculture statistics from Indian Agricultural Research Institute. He has played a major role in multidisciplinary research and other diverse areas of experimental design, etc. He has published more than 120 research papers and authored several book chapters, e-articles, reference manuals, and other documents. He has organized a number of national and international training programs and workshops. We are really lucky to have you with us, sir, the chairing this section. Today, without any further delay, I once again extend a warm welcome to you on behalf of the organizing committee and kindly request you take over the section. Over to you, sir.
Thank you, madam. First of all, I would like to thank organizers, especially Satish sir, for giving us the opportunity to organize the session. I have organized this session with 5 speakers, including me and Dr. Eldo Varghese also there. So Dr. Eldo Varghese will be the will chair the session, and there are 3 more speakers: Dr. Baidyanath Mandal, Dr. Sankalp Ojha, and Dr. Anindita Datta. So before starting and before handing over to the chair of the session, Dr. Eldo Varghese, let me just provide one or two brief line about the speakers. First, let me a little bit introduce Dr. Baidyanath Mandal. He is presently working as a senior scientist in Indian Agriculture Research Institute, Jharkhand. Earlier, he served as a scientist in Indian Agricultural before Indian Agriculture Statistics Research Institute. He also served as a scientist in Indian Institute of Soil Science, Bhopal, for some period of time. Later, he has been transferred to Indian Agricultural Statistics Research Institute, where he has given his majority of the service period. And now recently he has been transferred to Indian Agriculture Research Institute, Jharkhand. So he is a means one of the pioneer in modern generation, we can say, in experimental design. Lot of good publications are there under his belt in a good national and international journal. He has also guided some MSc and PhD students, and recently he visited Australia also for his postdoc under Indo Australia postdoc fellowship scheme. So that is about the first speaker. The second speaker, although as per the schedules there are different, but since some unavoidable circumstances are there, so we'll be changing the schedule little bit. The second speaker will be Dr. Sankalp Oja. So he was earlier assistant professor in Navsari Agriculture University. Now he is working as an assistant professor in Uttar Banga Krishi Vishwavidyalaya. So he served around almost 9 years in his service period, and during his service period, he has guided several students in the discipline of agricultural statistics. So he is also having many publications in national and international journal. So he will be our second invited speaker. Our third invited speaker will be Dr. Anindita Datta. I hope she have already joined. I saw her name. So Dr. Anindita is working as a scientist in Indian Agricultural Statistics Research Institute. She also she's having many publication also in national and international journal. She's also recipient of prestigious ICR Jawaharlal Nehru Fellowship, Jawaharlal Nehru Award for best for PhD thesis, and recently she got Dr. GSF Memorial Award also. So she is also a young scientist in the area of experimental design. Fourth speaker is the chair of the session, that is Dr. Fourth speaker will be myself itself, so I can skip myself. And fifth speaker will be the chair of the session, Dr. Eldo Varghese. So he is also one of the prominent young scientists in the area of experimental design, having work experience around 12 years of experience. Earlier he was posted in Indian Agricultural Statistics Research Institute, where he served many years. Now I think within before 4 or 5 years ago, he was transferred to Central Marine Fishery Research Institute, Cochin. So he is also a recipient of many awards, including National Academy of Agriculture Science Young Scientist Award, Lal Bahadur Shastri Young Scientist Award of ICR, and IRI Merit Medal. So a lot of awards is under his belt also, and he has published many research papers in national and international journal. So these are the brief about the speakers. So now I will hand over to Dr. Eldo Varghese so that he can conduct the session as the chair. And sir, please also whenever one speaker is starting, kindly brief 2-3 lines about the topic also, so that the gathering can understand what is going on in the topic. So every speaker will be having around 20 minutes time, and 5 minutes will be for discussion. Okay. Thank you. Hand over to Varghese sir.
Thank you, Dr. Arpan. First of all, a warm good afternoon to you all. I would like to thank the organizers of the 80th International Conference of Statistics for the 21st century, 2022, especially Professor Dr. Satish, and for giving us, for organizing such a conference and giving us an opportunity to organize a session, especially on design of experiment. Actually, the theme itself, I mean, we have kept the session name as Statistical Design for Experimentation, since most of the speakers belong to National Agriculture Research and Education System. We do have, seen several practical
Start. I think some internet issues are there.
Yes, mic is.
Okay.
Sorry for the inconvenience. There was a network delay. That was. Am I audible now?
Yes, sir. Yes, sir. Please.
So that's why this topic is very pertinent. At least I feel that the youngsters will have a flavor of what kind of research is being undertaken at the area of design of experiment, and it will help them to take up some research problems further. So with this hope, we are going to start with the session. We are having, as Dr. Arpan mentioned, we have got 5 speakers, including myself and Dr. Arpan. So first speaker is Dr. B.N. Mandal. He will be talking in the area of order of addition experiments. So that is a very important aspect, and some of the construction of designs for such experimental situation he will be explaining.
And the second speaker will be Dr. Sangal Paoja. He will be talking in the area of outliers in design of experiment, because as many of you are familiar with the concept of outlier, mostly in regression analysis context, or maybe in time series analysis context. But he will be talking specifically concerning the blockchain setup, how this problem of outlier can come, and how those issues can be sorted out. Then third speaker is Dr. Ananta Aditya, our younger colleague. She will be talking on the topic generalized rock column design. Actually, it's a very important topic where most of us, I mean, those who are into design may be familiar with the rock column design and its application potential. But there are practical situations where when we want to have some experiments where when in a row column intersection there are multiple units are present. So she will be explaining all those. I hope she will be explaining all those aspects, including some practical situation and how we can do the analysis. All those things she will be explaining to us. Then fourth speaker is our respected session organizer, Dr. Arpan Baumik. He will be mainly concentrating on talking on the cost-effective design. So there are several aspects of cost effectiveness when we talk in terms of design of experiment. So he'll be mainly concentrating on, I think, the minimally changed sequences, because when we think of any factorial or any response surface or any other multi-factor experiments where the frequent changes in the factor level is a very serious issue. So he will be talking in that aspect. Then last is mine. I will try to cover something on response surface design and their rotatability aspect. So this is in nutshell about what the speakers are going to discuss about. So without wasting much of time, I would like to start the session with the speakers. And before the start of the session, I have an appeal to all the speakers that we have given 2 hours 30 minutes time for the entire session. Now I think it was supposed to start from 1:40 onwards. Now it is around 2. So each speaker is requested to finish their talk within 20 minutes, and so that we can have a discussion of about 5 to 8 minutes. Okay, so that we can effectively manage the time. So with that appeal, I request the first speaker, Dr. B.N. Mandal, to start with this session. Sir, over to you.
Yeah, thank you, Dr. Eldo. Good afternoon, everyone, all the participants. And at the outset, I would like to thank the conference organizers as well as the session organizers for giving me an opportunity to present my talk. So I think I am audible.
Yes, sir, you are audible.
Okay,
Clearly.
so I am presenting without wasting time. Okay, can you see my slide?
Yes, it is coming. Yeah.
Yes, it's coming. Yes.
So the title of my talk is Construction of Efficient Designs for Order of Addition Experiments. And
sir, make it little larger, zoom little larger.
It is full screen.
Acha, okay, no issue. It's my problem, computer.
Okay,
please
so
continue.
This is the title, and this is a new field, order of addition experiments. So to make the audience introduced to this topic, consider suppose experiments where 2 or more components are added to get a final product. For example, hydrogen and oxygen, they are added to get say water, or maybe milk and sugar and tea, they are added to get a cup of tea. So you get a final product is like a cup of tea, and the components are say sugar, milk and tea, and those are the components. So if there are 2 or more components, often apart from the quantity of the components or volume of the components or weight of the components, often the order in which the components are added, that can have influence on the final product. Okay, the quality of the final product may depend on the order of the addition of those components. So the experiments which deal with this kind of problems, where how the addition of the components, order of the addition of the components, reflect the quality parameters of the product, that is the area of the order of addition experiments. And for example, from animal nutrition, suppose one nutritionist wants to prepare a say cattle feed ration. Okay, so cattle feeds have different kinds of they have to have protein, carbohydrate, fat, so they get different ingredients to produce the final ration. For example, they use fish meal, they use roughage, they use concentrate, and so on to get the final feed ration. So order of mixing this ingredients that can influence the final quality of the ration. So this has been studied already by Wagner in 1995. So this is an example of illustration of where these are useful. So the naturally question is, in which order are the ingredients are to be mixed? So if there are just two components, so it can be say component 1 first and component 2 later, or another can be component 2 first and component 1 later. So only two possible ordering. Similarly, there if the number of components increases, the number of orders of addition will increase. So in that situation, to get the which order the ingredients are to be mixed, so that is becomes a difficult problem. So this is answered by a carefully conducted order of addition experiment. So these have applications in biochemistry, and these are some references. Then in chemistry, because in biochemistry and chemistry you use different chemicals to get the final product something. Okay, and similarly in food science there are examples of applications of this kind of experiments. So to make the audience further relate to the topic, suppose you are having a dish, say chili paneer. So you see, to get a chili paneer product, you use this many components and then you get the final chili paneer. And obviously you cannot just mix them in any order. There is a given order in which you have to mix. Then you will get the quality of the or taste of the chili paneer. So in which way they have to be added? So that is the question that we try to answer using this kind of experiment. So now we come to the statistical formulation of the topic. So here consider suppose an order of addition experiment with m component. M obviously have to be greater than or equal to 2. At least 2 components are required, then only ordering will be possible. If there are less than only 1 component, so there is no order. So obviously that is excluded. So we have at least 2 components and more than 2. So those are dealt with. In general, we say there are suppose m components are to be added to get a final product. So the m components can be added in m factorial possible number of ways. So suppose if there are 3 components, so there can be 3 factorial. That means 6 possible ways the components can be added to get the final product. So component 1, component 2, component 3, component. I'll show the table what are the possible ordering. So the objective here is that to get the final optimal or addition order which will give the best response. So the best response will be measured by the measuring certain attributes or certain response variables, and our objective is to get from that experiment to get the which is the optimal addition order, in which will be the addition order that will give the best response. So that is the main objective. So now how to conduct this experiment? So one of the approach is that yes.
Dr. Sankalpa, please mute yourself.
Okay. Because I am not seeing anything, I am seeing only my screen.
Dr. Sankalpa, please mute yourself.
Okay, so best approach will be that you select all m factorial orders and record the responses. Suppose you have just 3 components, you can test all the 6 possible ordering and get the 6 responses, and you can see which order is giving the best response. So that is suitable for or feasible for small number of components, small m. But if it is not feasible if the value of m is say somewhat bigger. For example, as you increase the m, because m factorial will increase. For example, you have 10 components, so 10 factorial will be too many components. So you cannot just test too many orders to or this will be economically as well as impractical in time and cost, both ways. So we need to have some practical approach. So here is that the practical approach is select some subset of n orders out of m factorial orders to investigate the dependence of observation on the orders. So question is which n orders are to be selected in the experiment. So for this purpose, we use the designing of the order of addition experiment. So that will be helpful in identifying the important order effects and to find out the optimal order of addition with fewer number of experimental runs and with greater precision. So that is the purpose of designing here. Okay, so to investigate this thing, there was a need was felt for a model, suitable model. So the first model proposed was by the Van Nostrand in 1995. He introduced something called pairwise order, PWO, pairwise order model. What is that? So for that thing, I will illustrate using this example. So suppose there are 3 components are to be added to get a final product. So, and we list the components by just using number 1, 2, 3. Here number 1, 2, 3 means first component is added first, then the second component, then the third component. So one way of adding the component is this. Similarly, another order can be 1, 3, 2. That means component 1 first, component 3 then after that component 2. So this way 6 possible ordering can be possible, 1, 2, 3, 1, 3, 2. So it is all possible permutation of the 3. So there are 3 factorial, 6 number of possible ordering. So this is a complete design because 6 only possible. There is no any other order possible in this case. So this is the design D. And for to get a PWO, pairwise order model, first you have to create a matrix that is called PWO matrix. We define it by Z, where if you see here, the all possible orders are taken. So whether component 1 is added before 2, if it is yes, then it will be +1. So for this run 1, 2, 3, you see 1 has been added before 2. So that means it is plus. So it is +1. Similarly, whether 1 is added before 3, yes, so it is 1. Similarly, whether component 2 has been added before 3, so it is yes, so it is 1. If it is not before added that, so it will be -1. For example, here you see 2, 1, 3 in this order. 2 has been added before 1. So 1 is not before 2. So it is -1 here. Similarly, this way for all the orders, this matrix is obtained. So for given m components, there will be possibly MC2 components. Okay, MC2 columns here. 1 before 2, 1 before 3, 1 before 4, up to 1 before m. Then 2 before 3, 2 before 4, up to 2 before m, and so on. So MC2, m into m minus 1 by 2 columns will be there. Number of runs will be as much as in the design D. So this will be the PWO matrix. Okay. So based on that, now the PWO model assumes that the expected response, that is tau O from a given order, the final measurement that you get from a given order. Suppose this way the components are added and the final product is obtained and you get some measurements, say quality parameter, say some value of response variable. So that response variable, that will be depending on this model. So that is specified by this model where it is beta naught, the intercept, plus the Zij and beta ij, where Zij's are these elements of the corresponding order. So Z12, Z13, Z23, and so on. And beta ij's are unknown parameters. So beta 0 and beta ij, these are unknown parameters. So, and this is exactly looks like a linear regression kind of model, or more specifically, it is a kind of linear model. And the coefficient here in the PWO model can be interpreted. So what is the interpretation of beta ij? Beta ij means the component I is added before component j will have significant effect. So if it is found significant, so then component I should be added before component j. So in this way, the model is formulated. And the designs of the order of addition experiments under this PWO model then will be represented by the PWO design Z. Okay. And the property of such a design can be studied by using its moment matrix M, which is nothing but x transpose x divided by n, so where x is nothing but the column 1 and the Z matrix. Okay, so it is because beta naught is there, so for that the column 1 is there and Z matrix is there, so that is the design matrix. So the property of this matrix design can be studied using this moment matrix. And you know, because that is a regression model, so the variance covariance matrix of the estimated parameters beta hat, it will be proportional to M inverse, and it is a regression model, so it will be true inverse. So our job is to minimize the dispersion of this. So we have to, in some sense, maximize the matrix M, because we have to minimize this. So minimize the M inverse. That means maximize the matrix M under some criteria. So under d-optimality criterion, we try to maximize the determinant of the M matrix for a given design D. So now Lin and Peng in 2019, this is a recent field, so most of the papers are recently 18, 19, and so earlier that only few papers are there. So Lin and Peng in 2019, they have given a measure of D efficiency under PWO model, and the D efficiency is computed by using this formula. So they have given the formula for measuring D efficiency, and where you can see determinant M is the moment matrix to the power 1 upon P. P is nothing but MC2 plus 1, okay, and M, you know, the number of components, and Q is here P minus 1. So this is the formula. So for any given design, you can measure the D efficiency of the design. So if the efficiency comes out to be 1, we'll say that it is D optimal design. So under the PWO model, we try to get as much D efficient design as possible. So now we make some review quickly. So the first model, as I said, Van Nostrand proposed the PWO model for characterizing such designs. Then in 2019, Voelkel has suggested a number of design criteria under PWO model, and through computer search, he has found some designs. Okay, then Peng et al. Presented the optimality criteria and presented a method of construction of optimal PWO design. And through their though their method gives optimal fractional PWO design. Fractional means not using all the possible component, only not all impactorial components runs are used. Only n numbers are used, less than impactorial. So those are called fractional PWO. So the problem with their method is that if the number of orders increases, the number of orders increases quite rapidly in their method. For example, for a 8-component design, their method requires 1680 orders. That is too many. So suppose someone wants to have a design with 8 component, but say less than maybe 50 run or in 100 run. So their method will not give that design. But only advantage is that their method gives optimal design. But the orders increases quite rapidly as the number of components increases. So further improvements are required to construct optimal fractional PWO design with smaller number of orders. Okay, and then Zhao et al. In 2021 presented a method of construction of designs for order of addition experiments with minimal number of points. So they have given one method, and their methods are highly economic. That means they require few number of runs and relatively efficient. And but they have their method also have a problem that the efficiency of their design is very low for large M. So for example, a minimal point design with M is equal to 7 component has the efficiency of only 0.375. So the efficiency reduces quite rapidly as the M increases. For so their method has that drawback. So there is also scope for improving or developing methods to obtain minimal point design with higher efficiencies. And in this talk, so I will present one algorithm. This will not be a theoretical construction, but I will present one algorithm to construct efficient designs for order of addition experiments. So to illustrate the algorithm quickly, this is in brief the steps of the algorithm. So given number of components M and number of runs N, an initial design is first generated at random. So suppose you have 4 components and you suppose want in say 7 runs. So 7 runs with 4 components will be at random will be generated one design. So now for that D0 PWO matrix Z will be obtained and moment matrix will be obtained, and the D efficiency will be computed, which is denoted all these are, and the suppose the D efficiency is denoted as E0. Okay, because the design was D0 initial design, so we denote the D efficiency as E0. Now for that design D0, we will interchange the 2 elements in a given order of the given run. Then it will be interchange will be carried out, and the resulting structure of the PWO matrix Z and the moment matrix M will be figured out. There is some algebra here, also that I will skip here because it will not be possible to illustrate all the algebra. So quickly we can decide what will be the structure of the Z and what will be the structure of the M matrix if any 2 elements of a given run are interchanged. So and then the computation part becomes easier because we have to only update that part of the matrix. And Z and M matrix are updated, and the D efficiency is updated as E1. So if the E1 is greater than E0, that means that if the D efficiency of the new design is more than the earlier design, then the design will be updated. Otherwise, we will go to step 3. That means we will go for next pair of interchange between other 2 elements, and so on. So this process will be carried out till we found no improvement in the D efficiency and all runs are completed. So the final product will be output will be the D1 with E1. That is the efficiency. A design with the highest efficiency will be obtained. So, but the problem with the algorithm, it is not that it will be means everything will be solved. So the pros of this algorithm is that efficient in runtime. So it takes only few seconds to construct the design, and applicable for constructing designs with any permissible n and m. Okay, so we can use it for any permissible n and m. And the cons of the algorithm is that the algorithm does not ensure global optimum. It is a greedy type algorithm. Those who know algorithmic work, they know that this is a greedy algorithm, because we are updating the design as soon as we get a better design, better efficiency. So it will not, and this method generally does not ensure global optima. Okay, so we can get some local optima. So to avoid very poor local optimum, the algorithm can be run t number of times, where t is suppose 100 or 500 or so, depending on you have the time and other things. So design with the highest E1 or efficiency out of these t designs can be selected. So that will be some acceptable design. So it will practically acceptable. We may not get the optimal design always for given n and m, but we will get efficient designs. Okay, so using this algorithm, we first implemented this in our language, and this is open source language, and then generated the designs in the parametric range m less than equal to 8 and number of runs less than equal to 100. So, and the distribution of the number of designs according to various m, these are the list. So for order 3, for component 3, we have 3 designs. For component 4, we have 18 designs. For component 5, we have 60 designs, and so on. So for component 8, there are 40 designs. Total 283 designs in this range we have obtained. And the distribution of the designs according to D efficiency. So let's see, the D efficiency with less than 0.8 is only 4 designs. And from 0.8 to 0.9, there are 46 designs. And 0.9 to 0.95, there are 17 designs. 0.95 to 0.99, 90 designs, and 0.99 to 0.9999, 120 designs, and there are 6 optimal designs. So this is the efficiency results we get from this. So you can see most of the designs have the efficiency more than 0.9. So there are certain designs, of course, between 0.8 to 0.9, but they are still good. And this part can be improved, okay, through running the algorithm more number of times. Now we list the there are, as I said, we got 6 optimal design, d-optimal design. So these are the parameters of the 6 d-optimal design. So with number of runs 6 and 3 components, and 12 4, 24 4, 36 5 component, 84 runs 5 component, 96 runs 5 component, and these two 6 and 3 and 24 and 4, because these are full design. Because for 3 component you have 3 factorial is
Hello.
Yeah, it seems there is some network issue. We are not able to hear him. Dr. Mandal, we are not able to hear you.
He may be joining again. He may be joining again. He has unshared his slides. He left. He will join again. Sir, it seems some network issues from his side. He's not reaching the call also. You are mute, sir. You are mute.
Oh, sorry. Okay, okay. Yeah, you can continue, Arpe, Professor Arpe.
Actually,
Network
things,
issue.
I think he is also
Yeah.
towards the last network issues.
Okay, okay, okay.
But I am calling him. He's not reaching.
To join.
Yeah, yeah. Let us wait 1 or 2 minutes for him. Yeah, no problem.
Yes, sir. I think orientation was towards at the finishing line, and that time.
Okay, okay. Since other parallel sessions are also going, I have to check the other way. That is why. Just in the.
No, sir. Very nicely organized, sir. All the links and all those things.
Oh,
Very
thank you.
systematically organized. Even
Thank
I
you,
was
sir.
also checking the website.
Yeah.
Very nicely, sir, built. Mandal Salit, sir, once again.
Thank you. How is Professor? Yeah.
Sir, namaskar. I am Shankal Poja from Uttar Banga Krishi Vishwavidyalaya, Pundibari, Coachbihar, West Bengal.
Namaskar. Namaskar.
Thank you, sir, for giving opportunity for having a talk. So I think after Mandal, sir, I am waiting for.
He's joining, sir. Mandal.
Okay, welcome.
Mandal sir
Okay.
is joining. Bola is some issues are facing his face.
Okay, please. And
He joined, sir. Mandal sir joined.
Sorry, there was network issue. So which slide I was, because I could not feel that I was disconnected.
Algorithmic slide, sir. Algorithm slide, sir.
Just I'll go back there. Because it is full screen and
I think
am
you are
seeing
towards almost done.
yeah, algorithm. Okay, just wait.
you can continue to share the screen and do the need. Yeah, please continue.
This one?
Yeah.
Okay, so
Please share the screen.
Please share the screen.
Share the screen.
Oh, this is good. Okay, so the algorithm is efficient in runtime and applicable for permissible any number of n.
Sir, please share the screen.
Okay, I'm sorry. Your enter screen. Oh, yeah. Screen allow. Okay, has it come?
It is.
Yeah. It's in now.
Yeah, it is visible. Please proceed.
Okay, and the constraint of the algorithm is that it will not ensure the global optima. So if you are lucky, you can get a optimal design, but mostly you will get the efficient designs. Okay, and to avoid very poor local optimum, so you can just run the algorithm much number of times. Say t is equal to maybe 50 times or 100 times or so, depending on the time you have. So if you have, suppose you have time, so you can run it 100 number of times or so, and then out of the 100 trials, you can select the design which is having the highest efficiency. Okay, so this is one way, but that is not the sure short way to get the optimal design. And using this algorithm, we just generated certain designs in a very restricted range with 8 number of components and up to 100 runs. So these are the number of designs that we have got for various M. For example, with 8 components, we have got 40 designs. For 7 components, we have got 77 designs, and so on. Total 283 designs we have obtained in this parametric range. And if we see the D-efficiency of the designs obtained in this range, out of these 283 designs, we can see that there are 6 designs which are D-optimal, 120 designs have D-efficiency within 0.99 to 0.9999, and 90 design between 0.95 to 0.99, 17 designs between 0.9 to 0.95, and so on. So most of the designs have higher efficiency. You can see only few designs have less than 0.8 T efficiency, only 4 designs. So we can say that the algorithm is efficient to get T efficient designs. And these are the parameters of the 6 D-optimal designs that we have obtained. Out of this, only 24 and 4, that is 24 runs and 4 components, and 6 runs and 3 components. These are full designs, and others are fractional designs. That means they require less number of runs than the complete possible number of runs required. And so to conclude my talk, I'll say that we have presented an efficient algorithm to construct design for order of addition experiments under a PWO model, and this can be used for any permissible M and N. And there is scope for improving it to get designs for larger M and N. It can be parallelized by certain tweaking in the steps, and it can be modified to get designs under other models such as component addition model recently proposed. So there are other models are being proposed in this class of designs. So that can be accommodated by updating certain metrics in the steps. So that much only required. Other steps will be more or less similar. So these are the references. Okay, thank you very much. Any comments or questions from the audience?
Thank you, Dr. Mandal, for a very enlightening talk. And now the topic is open for discussion.
Any questions from the audience? If not, sir, then I will have one question, sir.
Yes, please.
So, like first of all, very nice presentation, although technical interruption was there due to internet connectivity, but very nice presentation on an interesting topic. And my one just broad question query is that it is order of addition experiment. Is it little bit similar to train pre-resistant or train free experiments? Because
No,
they are one by
is,
one. We saw one design that.
No, trend free is there is trend effect or something like that. But here we do not assume that there is some trend or so, because you have to create a final product and the order in which the components are added. So there are multiple components are there. I don't know if you can establish any theoretical connection, but till now no such result has been presented in the literature that these two are equivalent. Okay. I think this is a different class of design altogether. Problem is different.
But that is a very interesting topic also, because
yes,
in future also we can do like I have seen some of your design that is trend free. Some of your order, 2-3 design
so that can be there. That can be there.
That is in addition of order of experiment.
When suppose one run can be thought of an incomplete block. So if you think like that, but it is not like that. The way it is. The model and all those things are different, so that's why they are different. Underlying models are different. So
no, I am not saying like that. I am saying that we can relation in near future also, in the future direction, that order of addition and train free, we can establish some relation.
Okay.
Chairman of the session,
I have one clarification. Arpan, would you like to say something? No.
I'm not getting your sound, Eldo. I think.
No,
Hello?
sir.
Am I audible now? Sir,
am I audible to me?
Yeah, audible.
I'm not receiving able to hear.
Acha,
we can hear you.
But
maybe my connection is from. But
Dr. Eldovarghese, sir, you please ask your question. I will share. If you share your question, I can communicate it to the Mandal, sir. Because
if there is a voice issue, it may be for other speakers also, no? That's why. Sir, are you able to hear
your voice is clearly audible?
Coming, sir. Your voice is coming.
So he's saying he's not able to hear. Okay, so I was minor concern regarding the model, because the model which he has shown is a sort of relative sort of model.
Can others confirm whether, because Anindita also was speaking something?
Yes, sir. All the speakers, sir, all the presenters, they are able to listen. Maybe from your end, some issues are there. Anyway, Dr. Eldo sir, once he is asking the question, I will communicate it to you. Okay.
Okay, no problem.
Okay. Sir, please ask the question, sir.
Okay.
No, it was not that serious. I just wanted to see, have a query regarding,
Okay,
a
thank you. I am
clarification
not
regarding
getting
the
sound
model
actually.
used.
Some problem is there. Please go with the next speaker.
Oh, okay. Then we will have it a later day. No issue. Let us thank Dr. B.N. Mandal for very informative, enlightening talk. We had some discussion with Dr. Arpan. Also asked something with regard to the trend-free design. A sort of concurrence with the trend-free design with these designs for order of experiments. So I think it is a very, very useful area where those youngsters would like to start working on, because it's a newer topic. You must have noticed the papers shared by Dr. Mandal. And one part, he was explained only the PWO model, which is very prominent when somebody works on order of experiments. But there are several other model forms available like CP and all. Many model forms where, because in PWO model, we are taking the relative position of the ingredients. We are not concerning the absolute form. So those who want to work with the absolute position, then there are models available and work on the theoretical developments regarding the efficiency, optimality, and sort of things. And apart from that, the convergence, like he has mentioned, the algorithm was not that efficient, even though he could get several optimal designs. But anybody, if interested, can work on that area as well to get a better algorithm to get good designs. So this is all about his talk, and I would like to thank Dr. Mandal again for giving a very informative talk. Thank you so much, Dr. Mandal. I think he has left due to that network.
No, I am not left. I am here. Now I can hear you.
Now he can hear, sir. You can address the issues now.
Yeah, thank you so much, sir, for joining us and having a very enlightening talk. We are really thankful to you. Since now we have, our time is short, so we will have a discussion at a later date or later time.
Yes, sure.
So I would like to proceed to the next speaker. So thank you so much once again. So the next speaker is Dr. Sankalpa Oja from Uttar Bengal Krishi Vishwavidyalaya. So he will be talking on the outliers in design of experiments with correlated errors. It is again an interesting topic because, as I said in the beginning, that outliers is always a problem, whether it is regression or time series models or a design. So he will be talking in terms of the control or the estimation procedure or the design construction approach when outliers are present, how robust it could be, and in the presence of correlated errors. So with this, I would like to invite Sankalpa to have the presentation. So over to you, Dr. Sankalpa.
Sankalpa, please share the screen. Please share the screen.
Am I audible to everyone?
You are clearly audible. You please share the screen.
Okay. I am sharing from another account.
It is coming. Okay? It is coming. It is coming. It is visible now. Please proceed.
Visible now?
Yes.
Okay. Thank you, Dr. Eldo Varghese, and thank you other dignitaries and Dr. Bhaumik for giving me opportunity to present my work. So now I will be presenting on outliers in design of experiment with correlated errors. So basically in design of experiment, it is generally assumed that observations are independently and identically distributed. But in many experimental situations, the assumptions of independence of observations gets violated. So in field experiments, observations are mutually correlated through some systematic pattern of environmental variations. As for example, in plots occurring closer together within the field area are well known to be more similar than the plots occurring far away from each other. Thus, in field experiments, blocks are often formed using adjacent plots within a field. Whenever spatial contiguity is used as a criterion for blocking, it is often the case that experimental units occurring close together within spatial blocks created are correlated. There are many significant trends even within the small blocks caused by things like fertility gradients within the field. In such situation, it is useful to have proper technique to deal with correlated errors for designing and analysis of experiments. So different type of correlation structures that may exist among observations within a block are moving average type. Okay. Then autoregressive and correlated observations. These correlation structures are described below. As for example, moving average type correlation, we can see this structure where, okay, it is for ith block, and for tth treatment I can say that, okay, if the correlation is 1, and for if there is difference, that means the correlation order is G, we can assume that correlation is like that, rho by G. So it is, and rho is the common correlation, and for independent, if observations are independent, correlation will be 0. So autoregressive first order type correlation can be given by this rho to the power G. Okay. So, and equicorrelation structure, where we assume that all the correlations are same, which is rho. So these three basic different correlation structures can be assumed in a block, observations present in a block. Okay. So in view of the above, let us assume the generalized form of dependency, which is that is we can say variance covariance form of the observations appearing or arising from a block, which is that is the capital sigma. Okay. So that is the generalized correlation, where in the diagonal elements the observation correlations are there, and in the off diagonal elements the covariances are there. Okay. Sorry, in off diagonal elements correlation of different observations are there, and in diagonal elements it is the one, because the correlation between an observation with itself is definitely 1. So here y is a n by 1 vector of observation, and sigma is a n by n positive semi-definite matrix of variance covariance between the observations within the whole experiment, and is determined from the correlation structure considered for all the blocks. So we have considered three defined correlation structures. The presence of outliers in the data is the most serious illness to the linear statistical model, and this is the fact behind the creation of work in the area of robust distribution and outlier testing. The analysis of data from design experiments is valid only when the assumptions are assumptions like normality, homogeneity, and error variances, and lack of independence of the observations from plots holds good. The departures from these assumptions may take place in the presence of disturbances like outliers. So, however, most of the studies so far conducted in design of experiments to detect outliers have been restricted to models having uncorrelated disturbances with constant variances. But it had been frequently observed that the dispersion matrix may not be spherical as discussed above. In such cases, it is necessary to develop methodology to detect outliers for valid analysis of the experimental data. So many procedures are available to identify single outlier in a linear regression model. If the dataset contains more than one outlier or influential observation, then it is likely to be case that in most of the data sets, the problem of identifying such observations become more difficult. Also, when there are many outliers, masking occurs when outlier is not detected because of the presence of others. Okay, so one
Sankalpa, I am not able to audible. You are not audible to
Yeah,
me.
it is the same here too. There are some network issue. Sankalpa, please continue. We were not able to hear you, so we left you in the last slide. Please continue from your motivation slide.
Is it audible now, sir?
Yes, sir. Yes,
You are audible now. You are audible
yes,
now.
we are able to hear you.
Please continue your presentation.
Sure, sure. So departures from these assumptions may take place in the presence of disturbances like outliers.
Slideshow mode कर लो इसको slideshow please made it slideshow mode.
It is
नहीं
there.
stop presenting नहीं. वो नीचे slide you please go to the PowerPoint slide.
Okay, yes.
अरे unshare हो गया. Slide view mode करना था. It is coming है. बस okay, it is visible. Please proceed.
Am I audible?
You are audible. Please proceed.
Okay. So as designs, sorry, where I left. Okay. The analysis of the data from design experiment is valid only when assumptions like normality, homogeneity, or error variances and lack of independence of observations of plots holds good. The departures from these assumptions may take place in the presence of disturbances like outliers. Okay. So before analyzing the experimental data, we need to apply the diagnostic procedures to detect outliers. So by various methods, we can identify outliers for further scrutiny. However, there is another way of handling outlying observation, particularly in experimental design, to adopt a design that is insensitive to the presence of outlying observations. Such designs are known in the literature as robust designs. Here, robust design means the design is insensitive to the presence of any kind of disturbance. So that is the design can resist the violation of a particular assumption. Robustness against missing observations and outliers has been studied extensively. Okay, no attention has been paid to robustness in block designs. The research efforts need to be made developing a procedure for robust block designs with correlated errors in the presence of. So I am sharing my research papers, some statistics for detecting outlier in block designs with correlated errors. In this paper, Cook statistic and epistatic has been developed for detecting any T outlier observations from design of experiments conducted using a block design with errors are correlated. So we have modified Cook statistic. So Cook statistics for design of experiment was developed or modified by Bhaur and Gupta in 2001. They obtained Cook statistics for a linear combination of a set of parameters in a general linear model setup for a model given by this, where assumptions of error observations are independent, and under this situation, Cook statistics developed by them is given by this equation dt. This modified statistic follows f distribution with t and n minus m minus t degrees of freedom, where m is the rank of the design matrix. So we know that in design of experiment, design matrix is not full rank. Okay. So now the second one is AP statistic for block design with uncorrelated error. So they have also given the AP statistics are for T outliers. So and given by this this formula Z star prime Z star or X star prime and X star. So X star is the design matrix for a particular set of treatment contrast, and Z star is the design matrix with T outlier. So here they have to interpret that small values of APT statistics are associated with deviant or influential observations. Theoretical development. Under this situation, we have modified the statistic under a correlated structure. So here we can see the epsilon, that is the error vector. So error vector has been considered in this capital sigma form, where each diagonal consists or considers the defined correlation structure of the observations coming from a defined block. K1, K2, Kb are the defined block size in a block design. So here the dispersion matrix is positive, definite and symmetric matrix. So here the design matrix can be considered as delta, that is delta prime, that is the block structure, block versus observation matrix, treatment versus observation matrix, and D prime is the block versus observation matrix, whether a particular observation is belonging to a particular block or not. Then theta vector is the vector of different parameters. We are mainly interested in treatment first, then general mean effect, and the block effects. Okay. So we are considering V treatment, B block. So under this situation, the normal equations for estimating the parameters of a design can be given by this. Okay. And if I consider there is T outlier, this can be represented by X star prime and X star into theta. And considering the partitioning according to block and treatment wise, this is the matrix structure. Now, sigma inverse is the inverse of the correlation matrix of defined observations, block-wise. We can also consider defined correlation structure for different blocks. So under this condition, we have developed C matrix for design of experiments, which ultimately helps us to get the treatment estimates in a particular setup or linear combination of treatment estimates. So a particular treatment effect of a treatment combination can be given by generalized inverse of C matrix and QT. So, and this is the linear combination of treatments. So, outlier model we are considered in this block design setup is that, okay, we are considering that out of there are B observations in a block, and out of the B observations T are outliers. Okay, T are outliers. So this is the outlier matrix where we are considering that from the beginning, from 1 to B, first T observations are outliers. I got disconnected. Just wait.
No, we are able to hear you.
Connected. You are connected. We are able to hear you.
Audible?
Yes, you are connected.
Okay.
Please please little fast. Okay.
The outlier matrix which we have to incorporate in the model for the presence of T outliers. So again, we have to define a U matrix. These are the defined procedural part. I may skip for convenience. These are the development part, most of the derivation part. So ultimately, this is the statistic for T outliers in a block design setup. We have considered for a equicorrelation structure. The statistical form, or the formula can be seen in this expression, by this expression. And for T outlier, if I consider for a single outlier case, then that this can be simplified by this formula, okay, or this expression. Similarly, for two outlier, if I consider that there are two outlier, then statistical form or expression for the modified Cook statistic can be visualized by this equation. Okay, so
Sankalpa, please, sorry to intervene. 2 more minutes, please wind it up.
The above expression of Cook statistics is obtained for a particular set of T outlier observation. In practice, we have to apply this statistic for all possible set of T outlier observations. T equals to 1 to n, because we can't in advance we can't fix or assume the presence of number of outliers in a data set. Okay, so for every case we have to separately derive these statistics. So here only we have derived it for 1 and 2 outlier, and we have also definitely given a generalized form for T outliers. So here we can see that because there are n observations, and from the n observation n error terms are there, so this is the correlation structure. So we are considering that, okay, different blockwise we have separated the correlation structure. So we are also given the generalized form for a different block size structure. These are the sigma K1 by Q1 is the correlation structure.
Dr. Sankalpa, please bind it up early. Please little hurry up. We are having 3 more speakers.
So let us assume disturbances for a AR1 model, autoregressive 1, that means correlation degree is 1. In that case, the correlation matrix for the error terms will be this. So under this estimation, we have to, under this situation, we have to estimate the correlation, and we can estimate the correlation which are present in the data for this is the estimated value of the correlation. Okay. So now for detecting outliers, we must know the distribution of Cook statistic, but this expression involves variance covariance matrix. Therefore, derivation of the distribution of this statistics is mathematically intractable. However, testing for outliers can be still carried out by using procedure given by 2K. So for the derived statistics, we have given a method to obtain the cutoff values for the
Dear Dr. Sankalpa, please, sorry to intervene. Please wind up because you have waited up most of the time. Please wind it up.
Okay, fine. So we have taken a experiment with 5 treatment and 4 block. So these are the grain yield under experimentation. So we have considered analysis of variance with this data, and we have seen that, okay, treatments are significant. Okay, then we have also tested for presence of outliers in the data set. So we have also obtained the correlation structure under the given observation or given data set. So we can see that we have obtained this type of correlation structure. From here we have seen that the first row and first column, second column, the correlation value is quite high. So we can assume that, okay, there is a chance of having correlation between the two observations. Okay, so ANOVA after fitting GLS, this is the output. Okay, here we can see that treatment effects are not significant. We have checked for presence of outliers with Cook statistic. Okay, so we have seen that there is no outlier at all. However, correlation was quite high, near about 0.5, 0.45. Okay. So now for theoretical purpose, we intentionally include an outlier by modifying some data, modifying some observations. Okay, and again we have fitted the ANOVA model, and we have tested for presence of outliers, and out of the 20 observations, we can see that 90th observations has been successfully detected outliers, because calculated DT value is 2, and the thumb rule is that if DT value is more than 2, then there is a presence of outlier, single outlier in the data. So we have then analyzed the ANOVA after deleting the outlier. So we have seen that instead of having correlated error data, we analyzed by applying OLS, and treatments effects are found to be highly significant. Then we applied GLS method for estimating parameters and analyzed the data, which results treatment effects not significant at 5% level. Also, the presence of outliers has been checked by test statistic developed in this investigation, but no outlier has been detected. Then value of one observations has been changed intentionally to examine the statistic obtained by us. This change makes treatment effect significant, and the outlier observation 19 successfully detected. Then we deleted this outlier and again analyzed the data considering GLS estimation, which showed treatment effects are not significant as like initial data with no outlier, but with lower probability levels. So thank you. So my presentation mainly focused on the development of statistics and its application, and we have tried to show that our statistics rightly identifies presence of a single outlier in a correlated error structure. Thank you.
Thank you, Dr. Sankalpa, for a nice talk. Even though I have a couple of questions, but I keep it for future discussion, because we are running short of time. I can now allow a maximum of one question if somebody wants to have a clarification.
May I ask one thing, sir?
Please,
Yes.
Dr. Arpan, please make it fast.
Dr. Sankalpa, you have taken one response at a time or more than one, multi-response?
One response.
One response. So is there any work related to multi-response also?
Two response I have considered in another paper.
Oh, okay.
And generalized form was given for any T response, but for every case, 2 response, 3 response, we have to develop the statistics separately in every case.
Okay, and you have checked the A efficiency and D efficiency criteria also, because in the presence of correlation?
I have checked, yes, I have also checked the efficiency, D efficiency criteria.
Okay.
Thank you, Dr.
Show here.
Thank you, Dr. Arpan. Thank you, Dr. Sankalpa, for a nice talk. I would like to invite the next speaker, Dr. Anindita Dutta. She will be talking on web generation of generalized low column design. So I'm not going to give an introduction this time, because she's having a vast expertise that worked a lot, several years on this topic, and she's a master of it now. So she will be starting it with a good introduction and proceed further. So with this, I invite Dr. Anindita to start with the presentation.
Thank you, sir. Good afternoon, one and all. Special thanks to chairman of this session, Dr. Arpan Bhaumik, co-chairman Dr. Eldovarghese sir, for inviting me or giving me the opportunity to share my
Eldovarghese sir is the chairman of the session. I am the session organizer. I am the session organizer.
Pardon me, sir. I want to thank the chairman and the co-chairman of this session for giving me the opportunity to share my works in this platform. So I'm sharing my slides. Thanks, sir. I have to. Sir, is it visible?
Yes, please proceed.
Okay. I will give the presentation on web generation of generalized row column designs. So to start with the talk, I will start with the basic introduction about what is a row column design is. So when heterogeneity present in the experimental material in two direction, then we will do two-dimensional blocking or double blocking to reduce the experimental error. And the designs incorporating such type of designs are known as row column designs. So these row column designs are mainly used in field and animal experiments. So this is an example, simple example of a row column designs. It was an animal experiments which was conducted to eliminate the variation due to 4 breeds and 4 age groups. So the columns represent different breeds 1, 2, 3, 4, and the rows represented different age groups 1, 2, 3, 4, and these numbers are the 4 different type of feeds. So the feeds, these 1, 2, 3, 4, these are the treatments to compare the effect of 4 feeds. So it is a simple row column designs where the rows are age groups and columns are the breeds. So here are some another examples of row column designs. Suppose for an irrigation experiments, we can keep the channels as the rows and the positions along the channels are our columns. Similarly, in greenhouse experiment also we can use the row column designs. It is popularly known as Uden square designs, where these rows are individual plants and the columns are the positions of the leaf. And the most of the row column designs developed in the literature having only one unit corresponding to the intersection of each row and column. But there may be situation when the number of treatment is substantially large with limited number of resources. So for that case, row column designs with multiple units per cell is used. And these designs are called here as generalized row column designs. Now we will define our generalized row column designs as it is an arrangement of V treatment in P rows and Q columns such that the intersection of each row and each column consists of more than one unit, that is K unit. So a GRC designs, this is the parameter. V is the number of treatment, P is the number of rows, Q is the number of columns, and Q is the number of units per cell. That means interaction of each row and column. Now, giving some experimental situation related to these GRC designs. So it is a real life experiments conducted by Professor Bailey in the year of 1992. So it was a food sensory experiment where 6 food items were to be compared. So these 6 food items are to be this experiment was conducted in a 3 session, and there were 6 panelists. So in each session, each panelist will taste 2 food items at a time. So this is the interaction, first row, first column, and there is 2 food items. So this is the 2 treatments coming in and cell. So it is an GRC designs with V is equal to 6, P is equal to 3, means number of rows, Q is equal to P is equal to 3, Q is equal to 6, and number of units per cell is K is equal to 2. Again, this is a real life experimental situation. It was conducted by Edmondson. The experiment was conducted to compare the color intensities of applesauce. So in these experiments, there were combinations of 12 blends of applesauce with 4 concentration of cinnamon. And these treatments were stored for 4 different lengths of time. So this is the layout where the rows represent the 4 different type of cinnamon concentration and the column represent the different storage time. So intersection of each storage time and cinnamon concentration, there is 3 blends of apple sauces coming. So it is an GRC designs with 12 treatments in 4 rows, 4 columns, and K is equal to 3. Now coming to another experimental situation, it is related to animal experiments. Here in these experiments, it is a dietary to compare the dietary treatments on mice or rabbit. So 2 sources of variability is here. First one is breeds and second one is age group, and the cage is available with 2 partitioning accommodating 2 mice of same parity in one in each partition. Hence, corresponding to each age and breed and age group, there are 2 mice each receiving 1 treatment. So these different classes of generalized row column designs are studied in literature in different names like semi-Latin square, Trojan square, semi-Latin rectangles, and these are the important some references related under this name. Then generalized incomplete Trojan designs and row column designs with multiple units per cell. Now coming to another concept in GRC design, that is structurally complete and structurally incomplete GRC design. So the definition of a structurally complete GRC design is, it is the a GRC design is said to be structurally complete if corresponding to intersection of each row and column there appear at least one treatment. Here it is 3 rows, 3 columns, and each row and column interaction, that is cell, there is 2 units. But if this cell is missing, some observation is missing, some treatments are missing in a cell, then it is called structurally incomplete. Now for this work, we have considered this following model for the derivation of the information matrix and the further analysis. So the model is this YLIJ. L is ranges from 1 to K, it is the cell size, I is the number of rows, and J is the number of columns. So it is the response coming from the Lth unit in the ith row and jth column. Mu is the general mean, alpha is the ith row effect, beta j is the jth column effect, and tau Lij means the treatment effect coming from the Lth unit in the ith row and jth column, and this is the random error terms. So this model is used for further derivation. Now coming to, before going to the web generation of this series, I want to highlight how these series are constructed. So this is the series 1, this is for structurally complete GRC designs. So this is for odd number of treatments. What we do, we have develop an initial column for this, for generation of these designs, and this is for 2 units, K is equal to 2. So V is equal to 2T plus 1 and K is equal to 2, and this is the way to generate the initial columns. First is 1 to T, and this is 2T plus 1 to 2T minus T minus 2. I have given one example for that also, and that will result in a GRC designs. Developed GRC designs is balanced for estimating all the treatment contrast because its information matrix is in this form. So here is an example. Suppose for V is equal to 2T plus 1, T is equal to 3. So for V is equal to 7, this is the initial column. So this is the initial column, and the rest column are developed cyclically. And this is the developed designs is having parameter rows is equal to 3, P is equal to 3, Q is equal to 7 columns, and K is equal to 2. It is fixed for this series, and R is equal to 6. And the information matrix for this particular example is given by C is equal to 3.5 I minus 0.5 J. Now coming to the second series of construction, this is for even number of treatments. It is also again for K is equal to 2, that means 2 cell size, and it is developed by using this initial blocks. Here I have given one, and this series is also a variance balance for estimating all the elementary treatment contrast because it's C matrix in this I minus J form. So this is the example for V is equal to 8. We have to develop this initial block and initial column, and other 4 columns will be generated automatically, cyclically. So here it is the developed designs is for V is equal to 8, P is equal to, P is equal to 7. 7 rows are there, 4 columns are there, and K is equal to 2. Then another method of construction for structurally complete GRC designs. This is for prime number of treatments. Here what we do, first we have to take moles V minus 1 mutually orthogonal Latin square and juxtaposing one after another to develop the array of this dimension. Let me explain through an example. And for the previous 2 series are for cell size 2, but for this series is having cell size 2 to V minus 1. So this is the example. Suppose this up to this one it is the first moles and this is the second mole. We are just juxtaposing this, and what we do, we just consider the first two rows for this, for developing the first row of the resulting design. This is 1 2 2 3 3 4 and finally this 5 2, and generating for the second rows we have to consider the consecutive row 2 3 3 4 4 5, like this way. So this also resulting in a variance balance GRC designs with this information matrix. Sorry, just a minute. Okay, now I have given some methods for structurally incomplete row column designs.
Anindita, please make it in a slide share view.
Yes, sir, some problem is there. I think these slides are in hide mode. Give me, sir, 1 minute. That's why it is not coming. So this is the method for structurally incomplete GRC designs. What we do, let me go to the example first. Here is the example. We have developed this series for odd number of treatments, and this is developed for using these initial blocks, which I have given here. This is the initial block, and this series can be extended up to V-1 cells. And this series is also for is also variance balanced. You can see in this series of design, one cell is missing from this each rows. It is diagonally missing here one, and the second is like this. Coming to the second series of structurally incomplete designs, let me come to the example. First, we have to take balanced incomplete block designs with some parameter structure. Here it is resolvable BIB design we have taken. This is the resolvable BIB for V is equal to 9, 12, 4, 3, 1. So this is the BIB. We have to arrange this BIB in a row column setup. So what we do, we start with this first blocks first set in the first row, keeping one cell blank. In the second row, we will leave the first cell, start with the second, and go accordingly. Now coming to the third row, we will start it from the third cell. It is 1, 6, 8 is coming here. Similarly, for the fourth row, we will start from the last. So it will result in a structurally incomplete row column designs with this parameter, and it is also a variance balance series. This series can be up to V-1. This is, for example, case size 4. Now, now coming to the web solution of this generalized row column design. So a number of GRC designs are available in literature. So for easy accessibility and quick reference of these designs, a software has been developed named as Web Generation of Generalized Row Column Designs. So this is the home page for this generalized row web GRC, and it is available in this. This is the URL for this particular software. This is freely available software. So under this software, we kept different tabs for it: home, about design, generate design, catalog, contact, and disclaimer. So if we go to generate designs, we kept the two tabs, that is structurally complete GRC designs and structurally incomplete GRC designs. So if we go to structurally complete GRC designs, we have added 4 series here. First one is for odd number of treatments, which we have discussed the development procedure also. Then the even number of treatments for series 1. Then again another for series 2, and this is prime number of treatment. So I'm just giving the demonstration how, and if we go to the structurally incomplete, this is the structure for the structurally incomplete. There also we have added 4 series. Now we are generating the generalized row column design for prime number of treatment. This is for structurally complete. So here, as in the theoretical development, we have seen that particular series is the k is ranges from 2 to v minus 1. So we have to enter only the value of v here and the k. So v should be prime and the value of k. Suppose I am entering 7 and 3. So this is the resulting design we are having. Okay, and the parameter is also showing it is p is equal to 2, q is equal to 21. We can also randomize our layout also by clicking this generalized generate randomized layout. We can also save as this file in the Excel file by clicking this option. Now this is for even number of treatments. If we enter here, we have to enter number of.
Dr. Arpan, please mute yourself.
So here the number of treatment I have added 8. I have put the input 8. So this is the design resulting designs for v is equal to 8, p is equal to 7, q is equal to 4, r 7, and k 2. We also randomize this design using this tab and save as these designs in the Excel file. And this is the randomized layout of this particular previous design. Now, if we save as, we click the save as option, this is the saving the Excel file for the previous design. Now we can also generate this design from using the catalog tab. Here we have catalog different parameters like v, p, q, r, and k. So choosing the suitable parameter, if we click this design option, the output will be this. And in the about design section, we have given the complete method of construction for each of the particular series. So you can see here method 1, method 2. If you scroll down, different methods are there for structurally complete as well as structurally incomplete also. Now, these GRC designs have application in developing the different mating plans. Now, what is a mating plan? Mating plan is this systematic procedure for producing the progenies. So, diallel clause is a set of all possible matings between several genotypes, which make maybe clones or homogeneous lines. So, it may be desirable to have large number of inbred lines.
Anindita, please bind up. Please bind up.
Sir. Well, okay, sir. Raise only a sample of all possible crosses among them is called as partially diallel cross. So we can use this generalized row column designs advertisement. We can use this generalized row column designs for obtaining these mating plans. So what we have suppose these GRC designs with this parameter v is equal to this p, q, and k, and k is 2 here. So this is the information mapping. Let me explain to an example. So this is the, suppose this is the GRC for an 10-5-5-2. So if we cross between these two elements, 2 units in the in a cell, so it will result in an PDC with this information matrix. It will follow an group divisible association scheme. We can also construct the partial trial cross also. So let me take, it is the same example as the we have taken for the prime number of treatments. There we have to give the 3 rows consecutively. So this is the GRC designs. So here the K is 3 and this is the resulting PTC for the previous GRC design, which is having a very lower degree of fractionation, means it will save the resources for the breeder. Now to summarize my presentation, so a web solution named Web GRC has been developed for the generation of GRC designs that will be highly useful to the experimenter. An application of GRC design can be discussed for construction of mating plans, and so which have a smaller degree of fractionation for that. So the breeder can obtain small and efficient diallel and triallel plans by using these GRC designs. And these are some references which I given in the presentation. Finally, thank you one and all. Thank you for giving me this opportunity.
Thank you, Dr. Anindita, for a nice talk. Now the topic is open for discussion. I'm expecting questions from our scholars, research scholars, if anybody is there in the group. So far, I could not get any questions from research scholars. If anybody is there in the group, please feel free to ask questions.
Please ask the questions. Any questions from the scholars, especially? Anyway, Anindita, nice presentation and on a useful topic, particularly in the area of experimental design, which can be used for agriculture, animal, and related experiments, especially. So you have developed one web solution freely available. So have you developed any R package regarding this? Because
No,
R
sir.
is more extensively adaptable. So
No, sir. We are planning to do that, sir.
it will be good because it will be more means publicized, right? If you do R package. So
Yes, sir.
adaptability rate will be more for this type of designs. Okay.
Okay, any more questions? Okay, and I just want to have a clarification, and not clarification, it's just a small question. I mean, in the sense that because we have explained several series of designs, especially the structurally incomplete, structurally complete, and structurally incomplete, and
Yes, sir.
unequal cell sizes. So, any combination of unequal cell sizes with the structurally incomplete designs have you developed?
We are having the series, sir. Here I didn't discuss that. We have paper in CSAB, sir, Calcutta Statistical Association Bulletin. In that paper, we have that series.
Okay, then. Okay, apart from that, what about your treatment is a sort of factorial combination? Because you have seen several cases where all your treatments are treatment itself. Suppose it's a sort of factorial combination. Can it be possible to get
Yes,
such
sir.
design, generalized problem designs?
Yes, sir. We have also constructed that type of factorial GRC designs with factorial treatment structure, and we have a good publication in that also in communication in statistics theory and methods, sir. There we have constructed confounded generalized row column designs, sir.
Okay, thank you, Anita. That's from my side. Actually, it was just to educate our scholars. They can take a problem. It's a very wider area. Those who are interested to work on this topic, they are all welcome. So thank you so much, Anindita, for
Thank you,
for a
sir.
very
Thank you for
nice
giving me this opportunity, sir.
So with this, we are moving to the next speaker. Next speaker is our session organizer, Dr. Arpan Baumik. He's, I mean, he needs an introduction now because he introduced all of us, not him.
Sir, already,
Dr.
sir, introduced, sir, already introduced, sir, in the past.
First of all, a great thanks to you for organizing a session like this, because in most of our traditional conferences, this particular aspect is, I mean, in most of the cases, is missing. So it is a great opportunity for all of us and also the youngsters to have a discussion and a learning experience. And I'm going to my job to introduce Dr. Arpan Baumik. He was working as a scientist at Indian Agricultural Statistics Research Institute. He's a very excellent researcher with a good number of publications in theoretical statistics journals. And also he's a recipient of several recognitions for his research contributions. So with this very brief introduction, I invite, because we are running short of time, so I invite Arpan to start with his presentation on a very important topic: two-level minimally changed fractional factorial run order in the presence of trend effects through algorithmic interventions. Over to you, Dr. Arpan.
Thank you, sir. My slide is visible?
Yes.
Okay, welcome from my side once again, and good afternoon to all of you. Here I will be dealing with two-level minimally changed fractional factorial run order in the presence of trend effect through algorithmic intervention. So briefly, I will introduce the topic in the context of factorial experiment first. So We know what is factorial experiment. That is more than two factors or more than one factor should be there. Each had more than two or more labels. And here the main advantage is that we can study both individual effect and joint effect simultaneously. So it is majorly used in many type of experiment: industrial experiment, agricultural experiment, animal experiment, many industrial, medical experiment. So many it is having profound application in different areas of research. But when the number of combination in a full factorial design becomes too large to be logistically feasible. So in that situation, what we do, we take a proper fraction of a carefully chosen subset of the experimental run, and we prefer our experiment. So those type of fraction are known as fractional factorial designs, or you can say fractional factorial run orders also. Both this type of factorial and fractional factorial run orders, they have found profound application in different areas of research. So generally, it is advisable that when we carry out the execution of factorial runs, it should be random, because randomization will ensure the biasness. Okay, it will reduce the biasness, and it will also reduce the influence of unknown factors also. So that's why randomization should be done in a properly way. That is always advisable. But however, sometimes it is not possible to apply randomization in factorial experimental setup, because randomization can involve large number of changes in factor level, which will make experimentation expensive and time consuming. So when cost and times are major important concern, so in that situation, randomization may not be preferable. Okay, so alternative measure we may have to choose. So the number of level changes is of serious concern to many experimenter in agricultural, post-harvest, processing, engineering, and industrial experiment. As in those experiments, there are many hard to change factor, we can say, or costly factors which will be involved in the experiments. As I told, as in such experiments, one may come across some situation where it is physically very difficult to change the levels of some factor. For example, changes of mold, radiation, soil moisture, temperature, etc., or that may require stabilization time after some operating condition. Okay, for example, temperature of an event. These criteria for the number of level changes for factors are possibly one of the most important element to consider when taking into experimentation process, as this can have significant impact on effort and cost necessary to carry out the experimentation. So there lies the main motivation behind our work. This is one real experimental situation which was carried out in Indian Agriculture Research Institute, New Delhi. These experiments deal with soil microbial diversity through biolog ecoplates, and the main purpose of the experiment was to identify the best treatment combination. So for that, the experimenter performed a factorial experiment with three factors. One is carbon dioxide, having two level, elevated carbon dioxide and ambient carbon dioxide, then fertilizer, organic
Dr.
and inorganic.
Sorry to intervene.
Yes,
please click on that hide button so that the slide is fully visible.
Oh, okay.
That hide button is there.
Okay. Now it is clear, sir.
Thank you. Yes.
Okay, and then variety is another factor. So two different wheat variety they have used. So this is a real experiment situation. You can see in this type of experiment, this carbon dioxide factor, it is very costly factor, very huge amount of cost involved. So for experimentation purpose, it is not possible to experimenter to frequently change the levels of carbon dioxide from elevated to ambient. So in this type of situation, when experiment involve hard to change factor, so the traditional practice is that you fix the level of the factor which is the difficult to change and randomize the level of other factor. For example, here they have used this type of layouts for carrying out their experiment. So where carbon dioxide level, they first fix the carbon dioxide level to the lower level, that is -1. So for this -1, these four combination, the first four rows, they have randomized, and then for higher level of carbon dioxide, they randomize the remaining combination of the other factors. But in doing so, you can see the number of changes. It is the total number of change if we add all the individual change of the factor as per the definition of change. Means what? Change means one changes in sign of means one level. For example, let us see the factor variety. Here you can see after the first two row, last one, that is higher level of variety, or in one variety is there. In third and fourth row, that is -1 and -1 is coming. So that means another variety has been introduced. So if you're doing so, in fifth row, -1 get changed, so another variety is coming, 1, that is the other level. Like that it is changing. So if you count it, number of changes here, so from here this first one is 1, here from 1 to -1, 1 changes takes place. Okay, no, I am not concerning about the runs of change or length of changes. We are focusing on the number of changes. Here 1 changes takes place in both this third and fourth row for variety, with respect to first and second row. Then in one other changes takes place, so total 2, then 6th row again, and 7th row again, and 8th row. 5 number of changes are there, label changes are there for the factor variety. Similarly, 6 number of changes will be there, and in carbon dioxide you see -1 will be in the first 4 row and 1 will be in the second last 4 row. So only 1 changes takes place from lower level to higher level. To add all these, it will become 12. So total number of changes 12. You can see for 8 run order, because we are having three factor, each at 2 level. So total we can get 8 number of factorial. So for 8 number of run order, number of changes 12, which is too much, and it cannot bear, means it is very difficult to bear the experiment in terms of cost, because carbon big lot of cost involved in operation. So if experimenter use this type, their cost of experiment will be increasing to a great extent. So another alternate, one can go for standard order. So this is the 2-cube standard order, and here total number of changes 11. Too much. But now see the right side factorial layout for 2-cube factorial experiment. It is a run order where total number of changes is 7. And it is the minimum number for a 2-cube factorial run order. It has been already proved in literature that for a means s to the power k factorial experiment, that is k factor each at s level, so number of total will be s to the power k minus 1. It is already proved in literature. So here you can see for this layout, changes is 7. So we can see once we are reducing the number of changes for the total in a run order, so the cost of the experiment will be greatly reduced to some extent. So here we should use this type of run order. Okay, but now the question is, minimally changed run order where the total number of change is minimum for a factor combination is not unique. There may be more than one minimally changed run order. For example, cube factorial experiment, this combination where for first factor in the left, 2 number of changes takes place, second factor 2, and third factor 3, total add up to 7. But layout you can see 1, 2, 4, so that is also adding up to 7. But number of changes are different individual factor wise, although total number of changes is 7. So this is a concern, because which layout we should then use, which is better. So because minimally changed run order is not unique, so here required the intervention, here required the algorithmic intervention, because through algorithm we can generate many number of factorial run order where changes will be minimum. So here lies the main motivation of our experiment, of our work. So for experiments involve hard to change factor, as I told, factorial run order with minimal level changes may be considered as an important alternative, as it is to less cost, since cost of experiment directly proportional to the number of changes. Minimally changed run sequence for a particular factorial and fractional run order may not be unique, and there may exist many, for each of which the number of changes is minimum. So for that, algorithmic intervention is required. Since we are doing minimally changed run order, and it is only possible when we means only one value at a particular row. If we change 2 values, it will not be minimum. That has already been proved. So already minimally changed run order is possible on one position, only one position in a row changes subsequent row. Okay, so for since that thing we need to keep in mind. So therefore, randomization will be hampered. And due to lack of randomization or restricted randomization, that run order bound to affect by an important noise factor that is known as strain factor, which may create biasness in the precision of the experiment. So that thing need to be measured also. So keeping this in mind, we have carried out our research work. So for that, we have the methodology we have used. First, we have developed a here mainly we focus on two-level factorial experiment, but initially we have developed a general asymmetrical factorial experiment. Suppose there are k number of factors such that ith factor is having SI level. So we have already proved that this total number of change for a minimally changed factorial order in case of product of SI factorial will be product of SI minus 1. That is 1 less than the total number of run, and that can be obtained only when we change means only one position in two consecutive rows with respect to the label. So therefore, for a 2 to the power k factorial design with minimal number of changes, the total number of changes will be 2 to the power k minus 1. So that is for factorial setup. 2 to the power k minus 1 will be for 2 to the power k run order. But we will be dealing with fractional factorial here, half replicate especially. So for half replicate, the criteria is little different. For example, if we want to obtain a half replicate of 2 to the power k factorial, so for that, first we will generate a 2 to the power k minus 1 minimally changed factorial design, and then the last factor will be generated. For example, here, if we want a half replicate of 2 to the power 4 factorial with minimal level change, so for that, initially we will develop a 2 cube factorial experiment. That is this ABC with 8 rows. They are the 2 cube factorial experiment with minimally changed. This portion, the first three columns produces the 8 run orders, which will be the minimally changed run order, and the total number of change for the first three column will be 1 plus 2 plus 4, that is 7, which is the minimum possible for a 2 cube factorial experiment. But we have to develop half replicate of 2 to the power 4, so one more factor needs to be added. So that can be added by taking the product based on the method of generator, by taking the product of all the individual column, and by doing so, in case of half replicate of 2 to the power k factorial, that with a minimum level changes, the total number of changes will be 2 into 2 to the power k minus 1 minus 1. So that is the formula we have derived, and in this example it will be 14. Okay, so now, as I told, these run orders are subject to exposed to lack of randomization because they are providing the minimal cost design or with respect to minimal change. So therefore, they are subject to be affected by the trend effect, which may have a great influence on this run order, and which may influence the precision of the experiment. So in order to estimate the trend effect in the model for this type of run order, sorry, what we do, we use this type of model y equal to f of alpha plus g of beta plus epsilon, where this f part is the factorial part and g part is the trend effect. Generally it is measured based on the orthogonal polynomial. Okay, so this g beta consists of the trend effect. G is the coefficient of trend and beta is the trend effect, alpha is the factorial effect, and f is the design matrix, you can say. So based on this model, one can obtain first d optimal criteria, that is nothing but the maximum of the factorial determinant of factorial part, that is f prime f. And similarly, in the presence of trend effect, Take and Van der Rohe define one criteria that is known as dt optimal criteria. That is a d optimal, but in the presence of trend effect. So that can be given by this formula. Now simply if you take the ratio, that is dt by d to the whole to the power 1 by p, where p is the number of parameter to be estimated from the model. So in the situation that is known as trend factor, this criteria is given by Take and Van der Rohe to study the effect of trend on a factorial run order. So we have used this criteria for our algorithm, and this criteria, these designs will be completely trend free if f prime g equal to 0, and in that situation the value will be this trend factor value will be 1. So that means higher the value of trend factor, it lies between 0 to 1. So higher the values of trend factor, the design is almost nearly trend free. Okay, so we have considered this criteria. So for that situation, as I told, our criteria is based on algorithmic intervention. So initially we have developed a exhaustive search algorithm. There we need to give the labels of the factor first, which will be separated by comma. It will first initially develop a design, and then based on the minimal of criteria, that is change in one position in subsequent rows, so they will generate the algorithm will proceed. This is the flowchart of the algorithm. We have implemented this algorithm by writing a program in SAS 9.3 under the Intel R Core TM this processor i5-3470 CPU, and where RAM 8 GB RAM was used and 500 GB hard disk was used. Because why I have mentioning these things, because this exhaustive search, it will take too much space, all those things. So sometimes it will take too much time also. So these specifications are very much required. So, and finally, once the design will be developed, for each design they will print the total design, number of changes factor wise, total number of changes, and DT and 10 factor value criteria. So we have first executed exhaustive search algorithm in case of half replicate of 2 cube factorial experiment. So that means half replicate of 2 cubes. So there the total number of label changes will be 6. That is the minimum possible for a half replicate of 2 cube factorial design as per the formula we have derived. And in total we got 24 number of designs which satisfied the minimally changed criteria in case of half replicate of 2 cube factorial design. And when we execute this algorithm, it is just taking 2.02 real time and CPU time 0.3 seconds. So that is but the main thing, so we have all these designs, all these 24 designs. You can see the factor wise label changes respectively in case of 1, 2, 3. 1, 3, 2, 2, 1, 3, 2, 3, 1, 3, 1, 2, and 3, 2, 1. All these for 3 factors. These are the factor wise label changes, and all these designs will be minimally changed run order. Total number of design for all the changes category will be 4, which add up to 24. But the these are the run order. That is, for example, first run order is C, B, A, B, C, and A. That is the experimental run order for half replicate of 2 cube for the experimental. Okay, so these are all the 24 factorial run order. But the main disadvantage of half replicate 2 to the power cube factorial run order is that in the last column you can see the train factor value is 0 for all the 24 run order. That means in case of half replicate of 2 to the power cube factorial experiment, all the 24 factorial run order, although they are minimally changed, but they are totally affected by trend. That means their performances is not good in case of trend effect. So they should be only used when only cost criteria is a concern. Otherwise, they should not be used. This minimally changed design should not be used. Any other layout should be used, but minimally changed design should be used for this situation, half replicate of 2Q, only when cost is a great concern. Okay, so now since exhaustive algorithm is taking too much time, we have tested it for other combinations also. So what we have developed a restricted exhaustive search algorithm. And in case of restricted exhaustive search algorithm, what is the algorithm actually? It first start with a layout combination for half replicate of 2 to the power k factorial, and then there we need to specify the total number of changes for that case, which will be minimum, and also we need to define an interval for the trend factor. So in that way, the restricted algorithm search has been developed, and it is working faster as compared to exhaustive search algorithm. We have tested it in case of many combination. I will highlight it for half replicate of 2 to the power 4. This is the flowchart of the algorithm. And program has been written using SAS. This is the SAS program, some screenshot of the SAS program. So initially, you see, we have to give an initial design. Based on that initial combination, they will generate the design. And in the second red box, you can see here, we have to give the total number of change for that particular half replicate of fractional factorial. So in our case, in case of half replicate of 2 to the power 4, it will be 14, and you need to specify the interval in which you want your design. So here I have specified 0.95 to 1, so 10 factor value. So that is one screenshot I have given. And this type of output you will get the layout, the number of changes, the DT value. DT here is for D value, dt train is for in the presence of train, the train factor value and total design. So within the interval 0.95 to 1, we are getting 384 number of design, all of which are minimally changed, and all the performance of the train factor is 0.95. So that means all these 384 designs are almost nearly train free, and they are also minimally changed. So very good criteria. So by doing this, we have obtained total 12 interval for half replicate of 2 to the power 4 factorial, starting from less than 0.45 to 0.95 to 1. So here you can see these are the frequency of the designs for each train factor interval we have mentioned, and we can see maximum number of design belongs to 0.65 to 7. So that is moderately train resistant. So that means 3072 number designs are there, which is the maximum number of designs in a minimally changed half replicate of 2 to the power 4, where the train factor value is around 0.65 to 7. So which is almost showing that the designs, these design maximum designs are moderate to higher train resistant. And you can see around 768, this 384 plus 384, this 768 designs. Yes, sir, yes.
Dr. Arpan, please wind up within 3 minutes.
Within 5 minutes I will finish, no issue. So 385, 4 plus 384, total 768. So we can see total 768 number of designs are almost nearly 10 feet, 0.9 to 1. So that is a very good criteria, because our designs, all these designs are minimally changed, and many designs are nearly 10 feet. So these designs can be used very effectively. So we have performed this situation for exhaustive search and restricted exhaustive search, and we have seen that total we got 13,824 design. This is the distribution, and among this total design, exhaustive search is taking the real time 52 minutes almost, whereas restricted exhaustive search is taking the real time 32 minutes. So almost 20 minutes we got savings. Okay, so that is so restricted exhaustive search clearly outperforms the exhaustive search in order to obtain all possible minimally changed run order for half replicate of 2 to the power 4. So I have randomly given 2 run order under each interval. So these are the 2 run orders in the left side you can see for each interval. So these are the graphical representation for 10 factor, and as I told, maximum frequency is there for 0.65 to 0.7. Maximum number of design lies belong to this interval. So now these are the in order to compare the performance of the minimally changed run order in terms of train factor, we have also obtained around 55 different run orders for different number of changes. Say here you can see we have mentioned this. So here you can see many for minimally changed total number of changes will be 14. So you can see even in case of 14, some other run order, the train factor value is 0.83, 0.75 like that. So but we have also got around 768 design where more than 0.9 train factor value is desired. So similarly for 16, say row number 10, this if you use this run order, this run order, although the number of changes is more as compared to minimally changes, so that means randomization is little bit more as compared to minimal change design, but it is totally affected by train effect because train factor value is 0. So you can see many situations, even for higher designs, you see total number of changes. In case of 44 number of row, 20 number of changes are there. It is too much. So completely randomization will be there. So it should be less affected by the train. But you can see it is also having 0.82 around value. But some of our minimal change designs are performing better as in the presence of train effect. So that is the purpose. So any designs which are minimally changed and performing better in terms of train effect, they should be effectively used. And in terms of randomization, as I told, many designs are there which are minimally changed. We got, for example, in case of half replicate of 2 to the power 4, more than 13,000 design we got, out of which around 768 are more than 0.9 having 10 factor. So any design you can choose randomly. So this type of restricted randomization can be performed to minimize the effect of the bias. So this is the summary as I have already told. So these are some of the references for the present work. Thank you. So some questions.
Thank you, Dr. Arpan. A very elaborative talk, the informative one, explaining the concern with respect to level changes in the factorial. So thank you so much for a very nice presentation. So now the topic is open for discussion. Quick questions, if any.
This topic is very interesting. Lot of recent works are being going on in different part of the world using under this area. So very interesting, especially for students. You can carry out this type of research work. Very good. We have done a lot of work in this area. Not only in this area, even some response surface area. Next speaker will also highlight that one. So many works are there.
If not, I would like to highlight one point that whatever results Dr. Arpan has shown, I think it is assuming that the cost associated with all the factors are the same.
Yes, sir,
that may not be true in reality. So if anybody would like to take up this research further, this can also be a component that what will happen if the cost associated with level changes of individual factors vary. So that is one point. Then another serious concern with respect to the analysis, because as you have seen that it is a restricted randomization, so our usual OLS estimation approach cannot be attempted. So we need to think of certain, a form of REML or modified REML, which can take into account of this restricted randomization for estimating the factorial effect. So these are some of the remarks. So with this, I would like to thank Dr. Arpan for a very, very beautiful presentation. So thank you, Arpan, once again.
Yes, sir. Thank you, sir. And as you rightly mentioned, the first part, that is the different cost part. Yes, for different cost part, we have to take transition and measurement cost also. And regarding the analysis, yes, it is a concern. Although ANCOVA type of model we can use, and you have rightly pointed out REML type of thing we can also use. So now the next speaker is the chair of the session, that is Dr. Eldo Varghese. So I request Dr. Eldo Varghese, sir, please share your skills and start the presentation.
Thank you, Dr. Arpan. Actually, I was planning to have a presentation on, exclusively on rotatability, but I could not find much time to prepare for that. So sorry for that. But what I will do is I will share some of the papers in which recently I worked on in the area of RSM. I'm having some slides. Let me share that with you first. Now I think my slides are visible. I hope my slides are visible. Is it visible to you all?
Yes, sir. Yes, it is visible.
Okay, thank you.
Please put in full screen mode.
I think now it is in full screen mode, right?
Yeah. Okay.
Thank you.
Yes, sir. Yes, sir.
So as I said, my topic of my talk was rotatable designs for fitting response surfaces. But I will be trying to cover, as I said, I could not cover most of the part with regard to rotatable design, but I will try to cover some of the recent work which you have done in the area of rotatable response surface design, especially for rotatable design for fitting higher order models. So briefly, we'll be touching upon the aspect of rotatability when we deal with response surface design. Then the higher order designs, we have done some work on third order rotatable design. The next will be on the concept of sequential design, then the asymmetricity, because when we talk of the rotatable design, most of the designs available are symmetric in nature. So can we construct asymmetric design? So then what are the ways out? So there are few methods available. We also attempted something to develop some third order designs which are asymmetric, which are having asymmetric levels. Then something on indirect effect, which are known by different names in literature. Sometimes you can find it like overlap effect, neighbor effect, competition effect. So many names are there synonymously being used. So we have used it like an indirect effect. So any effect which is other than treatment, may be due to treatment, but other than treatment effect directly. Then how can we model that effect in case of RSM? Then how the estimation can be done? Then just a slide on robustness of that design. Then a cost-effective concept also into third order designs. So this response surface design forms a part of the broad class of methodology, very popular methodology, which is known as response surface methodology. it has three parts. First part is the designing of the experiment, then building a model which connects the response and input variables. Then once the model is coming out to be a good fit to the data, then for next is the optimization part. But my talk is concerning with the first part only, the designing part. So the designs which are normally used for fitting response surfaces are known as response surface design, which are very extensively used in many practical applications, because we are from, as I said in my initial talk, that we are from the National Agriculture Research and Education System. There we do conduct several experiments, maybe related to fish nutrition trials, maybe to the feed trials, maybe to the optimization trials of any kind. There are these kind of designs are very rigorously being used. So to put it in, to give a mathematical flavor to the idea that let us consider a quantitative multi-factor experiment where V factors lying in a V-dimensional domain chi, then the response of that function can be modeled as given in this form. But the problem, the polynomial is the functional form we normally make use of a certain degree. We normally make use to model the relationship between the response and the input variable, which is represented by X. Among those polynomial model form which I mentioned, linear, quadratic, cubic are the most commonly used forms. So all these notation, what it represents is given below, like the Excel for the linear terms in a polynomial model. What are all the components there in that it's a vector. Then similarly, a quadratic model will be there. These will be the components. Then the cubic, and as well as each of these vector of parameters indicate. Now, as in a matrix notation, if you want to represent a response surface model with V input factors, it will be Y equal to X beta plus E. It is also known to all, where Y is the vector of observation, which is having some dimension. Here it is n by 1. And the ith row of X is represented by F prime Xi. Note that this Xi refers to the ith level combination of V factors. And the errors forms our usual error in the assumption we normally make in case of our linear models. So the X takes the form XL, XLQ, XLQC, representing on whether we are assuming a linear, quadratic, cubic regression of order respectively given, corresponding to the n level combination of the V factors. So these are similarly the parameters. So if it is a linear model, if the assumptions are met by ordinary least squares, we can get the estimate of beta as given in the form. The corresponding variance covariance matrix is also as shown here. So here in comparison to traditional designs, our interest is in estimating or estimating the variance of the predicted response. So that can be obtained here in this function, using this function. So when we talk of response surface design, even though orthogonality is being discussed with many design, even with our traditional design, but there are few properties which are very commonly or very prominently discussed when we talk of response surface design. So any design, either it is a response surface or our traditional block designs, any design that is said to be orthogonal if that X prime X, because X we have already defined is diagonal. So that indicates that the columns are mutually orthogonal. So that will facilitate the elements of beta will be uncorrelated, and we can easily estimate the parameters. So this orthogonality concept, like the X prime X should be orthogonal, that refers to the first order orthogonal design, because it is clear from the definition that, because if you must have noticed that the order forms or the model forms of second and third order model, there are some quadratic or cubic terms comes into picture. So if you take any X prime X of those kind of models, that will have some off-channel entries where the quadratic terms will be coming. So any restriction will not yield you to get X prime X which are of diagonal. But it is possible if you are making use of orthogonal polynomials. But the moment you use orthogonal polynomials, the model will be highly depending on the design. Then another property associated with response surface design is that the rotatability. A design which is said to be rotatable if it has a constant prediction variance from all the points which are at equal distance from the design center. So this property is being discussed since 1950 onwards, at the time of inception of this kind of concepts. And after this introduction of this rotatability, there were several variant forms of the concept of associated rotatability has been derived. And also in 1996 or in 1988, Curie introduced the measure for assessing the rotatability of a design. So that measure gives a value from 0 to 100 as a percentage measure. It helps to find the extent of departure from the rotatability so as to repair a non-rotatable design into near rotatable by addition of some experimental runs. So there are several literature available on that, on the concept or the measures of rotatability. So my focus in this talk is strictly on constructing rotatable design, not of any near rotatable design. So when we talk of rotatable design, there are certain conditions to be satisfied by the design which we take for experimentation. So these are the 8 conditions given. Here you can see that the condition 5 and 6 cannot coexist, because this 6th condition is being introduced to introduce another class of design, rotatable design, which is known as modified second order rotatable design. So any design satisfying the condition 1 to 3, which are termed as orthogonal design or first order rotatable design, and likewise for several types of designs which are available in literature. So these are the general conditions available. So for any third order design, the design must satisfy condition 1 to 8, excluding 6, to be set as a third order rotatable design. And we have prepared, we have made an attempt to make a compilation of the theoretical developments done in the area of response surface design since 1950 to 2020, and we have come up with a publication. And there we have given a tree diagram to have a, to get a better idea of the theoretical development happening in the area of RSM. That is now available. I think it is published in 2022 in Communication. So this will give you an idea what are all, at least we tried to cover some of the major works done in the area since 1950 to 2020. Now coming to the concept, when we talk of third order or higher order design, this concept of sequential design is very much important. Sequential design otherwise also is very popular in the theory of design of experiments, but here our talk is very much restricted only to the third order response surface design. So what will happen the moment, if you look at if you recall the number of terms available in the model, especially in the case of polynomial, as the model increases, the order of the model increases, the number of terms will also be large. So that will be will ultimately resulted in a large number of runs so to be performed. So that is really very much expensive. So when you talk of any higher order model and the design for fitting in such a higher order model, we normally go by a sequential kind of design, where with any design which facilitate a fitting of second order model at the initial phase, then if after fitting the model it is found that the lack of fit of the model or the model fitness is coming out to be non-significant, or even the lack of fit is coming out to be significant, then we need to we need to try a higher order model with the experiment, whatever we have attempted. But that is not possible, because the moment you change the model, there will be a lot of issues. There will not be sufficient observation to fit a higher order model. Then apart from that, if you use any design with some addition of experimental runs, what will happen? That will affect the rotatability property. So we need to have a design which must be second order rotatable at the first stage. Then if you add few more points to the existing runs, it should have the property of third order rotatable design. So then it will facilitate fitting of design at first stage, the second order model, fitting of second order model at first stage. Then without discarding the initial runs at the initial phase of experimentation, add or conduct the trial for taking few more runs, then merge it together, then fit a higher order model. So it is really cost effective. So that is the major advantage of sequential experimentation approach with respect to non-sequential approach. There are a lot of literature available. Those who are interested, they can very well go through that. So that is one part with respect to the third order rotatable design. But the major issue which you have faced is that if somebody wants to conduct an experiment by taking into considering, a kind of third order design, most of the designs are symmetric in nature. So, but the major problem is that sometimes it is difficult to find or to conduct a trial with all the factor levels are equal, in the sense that, because sometimes what happens if you are able to explore the points from the entire design space, which are widely spread, that would be more informative. So if any experiment need to be performed where asymmetric levels of factors are desired, then designs are not available. So what we have attempted, we have made use of a methodology by which any second order designs or which are rotatable in nature can be transformed to a asymmetric design. But it is to be mentioned here that it is not a general approach that any rotatable design cannot be converted to the asymmetric form, but we can get some classes of design which are very popular and very popularly being used for experimentation. Those classes of design which are rotatable in nature can be converted to asymmetric type by making use of an orthogonal transformation. So that is the transformation is given here. Like XU is an existing second order design with symmetric levels, and A is the transformation matrix. If A is taken in such a way that it's an orthogonal matrix, in fact, so that the structure of A will be the AA represents the elements of A, then the square sum of that element should be 1, and their cross product should be equivalent to 0, either row wise or column wise. Then if you multiply it with the XU, it will be resulting in a matrix or a design ZU that will be having all the desired properties required for a rotatable design, but with the asymmetric levels of the factors. So, but how will you decide upon what should be the elements? Even though we said that it is orthogonal design, but here we have defined a structure for that matrix, because here C1, C2, Ck are the individual submatrix for which, say for example, these represent the pairs of factors, or matrix corresponding to pairs of factors, and R factors if we need to have the original levels to be maintained. And the suppose K pairs of factors, we need to have some changes in the levels. Then we can make use of a matrix of this form, where Ck will be, each of these Ci's will be taking a particular orthogonal matrix. Accordingly, you will be getting a resultant matrix with some changed levels. Wherever you have kept this IR, it's an identity matrix of order R, then the corresponding factors will be getting the level which are exactly as the initial level. So these are some of the examples with which we can make use of that transformation, and we can get the asymmetric rotatable design. So this is with respect to constructing a second order design. In a similar way, if you make it, there are some of the examples given for different factors of, different number of treatments or different factors. These are different orthogonal matrices given. Here it is for 2 factors which we need some different levels, and these are the factors which we want to retain as the original levels. Then if we this is one of the popular rotatable design available in literature. If we multiply this rotatable design with this orthogonal transformation, it will definitely lead to another design which are having the asymmetric levels with the property of rotatability being maintained. And in a similar way, and we have checked it for, I'm skipping all these theoretical derivations, we have done it for several classes of designs and developed several asymmetric second order rotatable design. And making use of these asymmetric rotatable design, we could see, and we have checked all the properties, all the required conditions, whether it is being satisfied or not. And for ensuring the non-singularity, ensuring the estimation of all the parameters, we need to have for this class of design, this lambda 2 by lambda 4 by lambda 2 square should be greater than 3.3 by 5, and all our design is having that value above 0.6. And to construct a sequential design, sequential SATODs, sequential asymmetric third order design, we have taken 2 such classes of ASODs and merged it together with such a transformation. We have got design which are at first stage will behave like asymmetric second order design, with satisfying all the rotatability property, and at higher level it will be satisfying the third order all together. Both the block 1 and block 2 taken together, it will be satisfying that third order rotatability property. So, and we have developed a few more classes of design, and if you have a quick comparison between the 2 classes of design, the earlier one was requiring large number of runs. You can see 50 runs were required, taking both the stages together, but it was quite less. But there are some compromise with respect to some of the properties defined. But even though both the designs are rotatable in nature, here it requires only just 34 runs for fitting a third order rotatable design. Here it requires 50 runs. Here all the moment properties are being satisfied. Here some compromise is there. And these results are available in the papers which I have given here. Now, another concept is with respect to the indirect effect, which I was talking about in the initial slides. That in most of the studies, we assume that the response which are received from a particular plot will not be affected by the neighboring units. Or sometimes, like Dr. Sankalpa mentioned about some concept on errors are correlated. So we have attempted these in this response surface case, and we have defined some models how to incorporate that neighbor effect into response surface model. If you recall, effects use our linear, quadratic, or cubic the response.
Sir, please bind it up in 5 minutes, sir.
Yeah, please. I'm going to do that. So this is the functional form. Different variants of these forms are also available. How these will affect our estimation and what will be the structure of this neighbor effect when we consider the response surface model. Those things are all discussed, and you can find all these results related to what we have attempted with respect to the neighbor effect or the indirect effect in response surface, which are available in these papers. Then the last but one part is the robustness aspect that also have been attempted because it is again, if any observation is missing in an experimental situation, any response is missing, it will have an adverse effect on the properties associated with the design. So any design that guards against such effects is known as robust against missing observation. So that also we attempted in case of third order design. That is also available, and those who are interested, they can go through this paper where this is given. And the last one, which I wanted to discuss with you about the minimally changed run sequence, Arpan has already discussed with you. That is which we have attempted published recently in case of third order design, that is also now available. So with this, because I have got very less time to discuss all the topic which I planned to discuss, but anyway, thank you all for giving me this opportunity. With this, I'm stopping my presentation here. So, and I request anybody who would like to discuss something on this. Thank you.
Thank you, sir. Now, quick 1 or 2 questions from the house. Although nobody have asked any questions, that is not good. Actually, we should have asked at least some questions, especially the students. Questions or any suggestions, anything you can give.
If there are no more questions, it's my responsibility to wind up the session.
Yes, sir. First of all, thank you for very nice presentation and highlighting a lot of important aspects in the area of rotatability, especially. So now please wind up the session. Then I will finally give one vote of thanks, sir.
Thank you, Arpan. I could not give full justice to my topic because it was too vast. I could not cover in that given time. But anyway, thank you so much. And regarding this session, we were having 5 speakers, and we had a very good discussion. We had a very good presentation on the topic mentioned. But I request all the participants that these are not the limit of whatever research is being undertaken in the area of design of experiments. There are many more things that are being done at various institutes. If you look at Indian Institute of Technology, Bombay, there people are working on design of experiment, ISI, theoretical and applied units. They are working on design, and ISRI people there from Delhi, and some of them have joined now here for this talk. They are all doing very excellent work, and I personally would like to thank all the speakers, including Dr. Mandal, Dr. Sankalpa, Dr. Arpan, Dr. Anandita, for enlightening us with this recent research which is being undertaken in the area of design of experiment. And thank you so much, Satish sir, for giving us this opportunity. Actually, it is really pertinent in the sense that, as I said, in most of the conferences we have seen, especially being done by traditional universities, that this particular component is missing. And you have given us this opportunity to have a session on this, and a special thanks to you also. And for a special thanks to Arpan for giving, taking effort to organize such a session, and it is not easy to, coordinate such a session by inviting people. They may tell so many excuses for not coming for such a program. They may be busy with so many official engagements, but even after that, he could manage to call some of the good speakers for this session. And I am really thankful to you and all the participants. They were there for very keenly listening to it, even though we could not have much interaction. But I hope that all the speakers were shared their email IDs. Probably in future, they will be having some fruitful discussion. And thank you all the speakers once again. And thank you the entire Department of Statistics, Kerala University, for making especially a session on design of experience here. Thank you so much.
Thank you, sir. Thank you very much for organizing the session so nicely as a chair. And towards the last, we are towards, sir, I think we are only 11 minutes extra we have taken. So we are almost on time due to some internet issues were there. And it happens because nowadays many people, although some advantages are there and some disadvantages, both are there. But it is good that you have organized the conference in a so wonderful way. A lot of good sessions are there. So I personally like to thank Dr. Satish Kumar sir for giving us the opportunity to organize this session. And I would like to also extend my sorry thanks to Dr. Eldomargi sir for gracefully agreeing to chair the session and also delivering one talk. And I would like to also thank all my speakers, Mandal sir, Dr. Arindita, Dr. Sankalpo, for presenting their talks. All the participants I have seen throughout the session, almost around 27 to 30 participants are there. So that is a very good because in the holiday and after lunch this session is taking. So that is a very good attendance. Thank you, sir. Thank you, all the speakers, and thank you, all the participants. Thank you very much, sir.
In fact, watching your sessions via our YouTube channel, YouTube Streamline, in fact. So more than that, first of all, let me to congratulate Professor Arpan Bhaumik for organizing this session.
Thank you, sir. Thank you, sir. Thank you.
Congratulate Professor Arpan. And also, Professor Eldoverghese has managed this session in a very wonderful way. Involve active participation, active deliberations in between the talks. Very, you have done a fantastic work, very excellent work. In fact, earlier times, Professor D.K. Ghosh usually organized sessions on design of experiments with this. This time, I think he has some other problems, and he given a talk, but not in the organizing session. But that task this time, Professor Arpan has done. And we are very much grateful to you, Professor Arpan Bhaumik and Professor Eldoverghese and other speakers, especially all the speakers who have done excellent work. We are grateful to you, Professor, for your support and for your active research involvement through this in this way. We expect your similar type of support and active participation in future also. Thank you so much.
Thank you, sir. Thank you, sir. One request, because Eldo sir my name was repeated in two places in the schedule. If possible, please rectify, sir.
In fact,
thank you, sir. Thank you. We have enjoyed the discussion thoroughly, and I am also attending some other session in between whenever possible. So that is
usually we go in this way. The organizer is the chair.
Very nicely organized, sir. Very nicely organized.
But you have done given the chair, and he's also very active. And
he's very active, sir. And I generally used to follow him. Actually, we did a lot of works together, and even we are doing. Although now we are in different places. Earlier we were in the same places in ISRI for some long time, and we did a lot of works together. Still, we are doing a lot of works together. But some other works we are also doing simultaneously. So he's very active, and he's one of the, I can say, in young generation, he's one of the, means you can say, future pillar in design of experiment. You can say. It's a very.
On behalf of the organizing team, we extend our gratitude once again to each one of you, Professors, and let us give a big clap to all the speakers.
Thank you, sir. Thank you.
Now let us move to the next session. Some professor is calling. Just so please. Professor is just starting. Okay. Can you hear me?
Yes, sir.
Yeah. Can you hear me? Okay. Now let us move to the next session. Tajunisa?
Yes, sir.
Yeah. Please introduce the chair and please support him for whatever in what way to run this session in a smooth manner. Please.
Okay, for sure. Warm greetings to all. Now we move on to technical session 15 of ICSTC 2022. The plenary session.
Just a minute, sir. Professor Narendra Kumar is here in the group. He is calling. Whether any problem with him, I don't know. Yeah, Professor. Okay, he is also there. Professor Narendra Kumar and the Ashok. Okay, we can. Professor Narendra Kumar. Professor Ashokan Variat. Ashokan Variat has in fact to join the, because he's in Canada. It's better he suggested after this time, but I don't know whether he has joined the meet or not. Just to check.
So both the speakers haven't joined here. Sir, both the speakers haven't joined.
Okay. Let me to just call them. Okay.
Sir, I think you have to send the link to Professor Narendra Kumar.
Okay. I shall check. Okay, please.
It seems like that.
Yeah, Professor Narendra Kumar informed he is trying, but there is some network issue, probably the week. Let us wait 1 or 2 some time.
Okay, sir. Okay. So we can wait. Actually, this session is having only 2 speakers, right? The plenary session. Hello, sir. Professor Ashokan is ready to give talk.
Hello, good evening.
Yeah.
If Professor Ashok, he's trying to join because some network issue probably. Professor Ashokan, if ready, we can start. Okay.
Okay.
Yeah, I can start now, no problem. Yeah.
Yeah. Then Tajunisa, please introduce the chair and let us go ahead. Okay, please.
Okay, sir. Warm greetings to all. Now we move on to technical session 15 of ICSTC 2022. The plenary session will be chaired by Professor S.M. Sunoj, Faculty of Department of Statistics, Cochin University of Science and Technology. He was the first rank holder in MSc Statistics in 1994 in University of Calicut. He was awarded PhD in Statistics by the Cochin University of Science and Technology in 1999. He has more than 2 decades of teaching and research experience. Dr. Sunoj received Matrix Fellowship SARB India in 2020. His research interests include distribution theory, information measures, non-parametric estimation, reliability modeling, and analysis. Professor Sunoj has published several research papers in refereed journals and is a part of various national and international research collaborations. Dr. Sunoj is an elected member of International Statistical Institute, Netherlands, and he is also a life member of International Indian Statistical Association, Indian Society of Probability and Statistics, and Kerala Statistical Association. He is an associate editor of the Journal of Indian Society for Probability and Statistics, Printer, India, since February 2021. Once again, I humbly invite Professor Sunoj with immense pleasure to chair the session. Over to you, sir.
Okay, thank you for the nice introduction. In fact, let me first extend my thanks to Professor C. Satish Kumar for inviting me to chair this session. This conference is an important international conference because it's being, this is a series of, this is in continuation of the previous conference of the same name, and I have physically participated 2 or 3 conferences in Trivandrum, and every time this was organized in an excellent way. And this conference, the present conference is also started yesterday, and in fact I couldn't participate the sessions because of the because as you know, we are all in the preparations of the ISPS conference that is to be held in Cochin during January 4 to 6. So let me go to this session. This session is a plenary session. We have 2 eminent scholars. One is Narendra Kumar from Punjab University, India, and another speaker is Professor Ashokan Murle Vaidyath, Memorial University of Newfoundland, Canada. And in fact, Professor Ashokan is quite familiar to me and our department. He frequently visits our department. So it is an immense pleasure to introduce Professor Ashokan to this audience. And he'll be talking on assessing a binary measurement system with an underlying continuous measurement using targeted verification. I think since it's being the plenary session, the time is allotted to 35 minutes or 40? Sir, 40 minutes.
35 minutes for presentation.
Okay, 35 minutes for presentation.
5 minutes.
So I request Professor Ashokan to deliver his talk. Over to you, sir.
Okay. Good evening. I'm very happy to be part of the international conference. Happening from yesterday onwards, and also for the last 3 days. Also, we have a workshop, and I'm also able to participate in the workshop by giving a talk in that. So it is always nice to talk to the audience, especially the Indian audience. And it is also a learning curve always. Every time we talk in our discussions and everything, we can always get something from us. Okay. So basically, I'm from Trichur, and I used to visit Cochin University. What Sunanji was talking about that, and I studied in Calcutta ISI as well as for my post graduation, and after that I worked in ISI also.
Please,
okay. Is it an issue or no? Because
no problem, Professor.
Okay.
There is
Please proceed, sir.
yeah.
Please proceed.
So it is happy to know. So this is the area where I was working as industrial quality control. So in industry, when you go, we have a lot of consultancy activity I used to do. And most of the time we use specifically quality control techniques, but also we use other techniques like design experiments, survival analysis, or reliability analysis and all. So this particular talk I'm going to give you on the measurements. So I think I will start my end screen. Let me see how it is coming. Yesterday I have a problem.
Just
is it coming something?
No, not Professor.
No, not yet.
Yeah.
Can you see the slide now?
No, sir.
Not yet?
Not yet.
So I put
from your side, you have already uploaded it through the present now?
Huh?
Yeah, you have already started uploading it. But in your computer, it is showing this presentation?
Yeah, I click on present entire screen or window or tab.
So that has to be shared, in fact. But that is,
yeah, I put the entire screen. Now I have to put a share also, right?
First you open the presentation and then use the entire screen. Then share.
Is it coming now?
No, sir.
I'm not sure why it is not coming. No, I opened the file. So
Actually, you have to press the present now button in the Google Meet.
Yeah.
And then.
Oh, okay. Maybe I join with other one. Okay, so maybe I will go back again. Okay.
Yeah. You have to.
Okay.
Yes, now it is coming. Yeah. So please make it full screen, sir. Okay. Okay.
It is okay.
It's okay. It's okay. You can start. Now we cannot hear your voice. You have to unmute.
Am I audible?
Not audible.
Hello.
Yes, sir.
Oh,
So actually,
okay.
we have already started the second talk now.
That's fine. That's fine.
Okay.
Just go ahead, sir.
Yeah. Professor Ashokan? We couldn't hear your voice. Hello, Professor Ashokan? Hello, sir.
Excuse me, Professor Sunaj.
Yes.
There is an audio issue. We are talking about that.
Okay.
Just solve it soon.
So tell him to disconnect it and then try to join it again. So it may resolve it.
That is fine. Yeah.
So I think he is whether is there any problem of this companion mode? I'm not sure.
Presentation is okay. Fine. Presentation is fine.
So yeah.
What about the audio?
Audio, in fact,
not.
No. I can hear you from the
mobile. That's all. So, why you are joining in this companion mode, sir? Whether that is necessary?
No problem. You are joining in the companion mode.
Oh yeah, companion mode is coming there.
Yeah, that is why. That's why.
That may be one reason. I don't know, but
yeah, that's maybe. Okay. Yes. That may be the reason, probably. What can we?
He is trying, I think.
What is the best?
Yeah. Let us wait a few minutes, and otherwise, Professor Narendra Kumar can.
Yeah. If there is difficulty, we can start the other.
Yeah.
As scheduled earlier. Okay.
Yes.
So other join. Well, I'm not joining as a companion also. I was getting this and.
By default, it may be coming that way. Oh yeah, still that is, but it may not be the reason.
Probably
I probably we can ask him to share it to you, Professor.
Yeah, he's talking with this matter.
That is also possible. Professor Ashokan can send the file to either to me or Sadish sir, and we will present the material from here, and you can speak based on the presentation. So because
Can I start? So because some issues are coming at his
yeah,
part.
Professor Sadish sir, Sadish.
Okay.
So for the timing, let us keep pending the Professor Ashokan's talk.
Yeah, better.
So,
Professor
please convey this message to Professor Ashokan. So let us start.
Just a minute.
The first talk.
Okay, please. Okay, please.
Yes. So I'm happy to introduce Professor Narendra Kumar, Punjab University, and he has published many papers, many international, many reputed journals, international journals, and he's a senior professor in the Department of Statistics, Punjab University, and he will be talking on comparing several variances with a control in direction mixed families of hypotheses. So I request Professor Narendra Kumar to present this talk in about 35 minutes of time, and after that we will have some discussion. So over to you, sir.
Right. Thank you so much, Professor Sunoj, for the introduction. So at the outset, I would like to thank the organizing committee and especially Professor Satish for giving me this opportunity to be amongst you all. Because I also apologize for being late because there is some issue with the connection parts. One email was not working. So all the time it was coming, video is denied. So video call is denied. So join from the different email. So that's way the time lag was there. So without losing time, let me share my slides so that I can go ahead. So as we see, the title of the talk is comparing several variances and direction mixed families of hypotheses. So this is a joint work with Professor Parminder Singh and Dr. Chauhan. So Professor Parminder Singh is a professor at Guru Nanak Dev University, Amritsar, and Dr. Chauhan is a biostatistician at Canada. So the roadmap of the talk is into 6 parts. It is the introduction I will be talking about in the beginning, and then the main results, then the applications of the results which have been worked up, and the simulation study. Then a illustration has been given in the form of a data set, that how the procedure which is developed works with the help of data set, and finally the references. So as said that firstly I'll be taking up the introduction part. So one-way model is the usual one-way layout model is taken, where the response is the jth response of the ith treatment, which is xij, is related to the ith population mean with the relation xij is equal to mu I plus the other components. So and epsilon i's are nothing but the random errors, so which are normally distributed with mean 0 and variance sigma I square. Usually it is considered for one-way layout design that variances are same of all the populations we have in hand, but here we're considering that they are unequal. So heteroscedasticity is there. So, or in other words, I can say that the K+1 population I'm considering, they are normally distributed with mean mu I and variances sigma square. So variances are different, and the means may be known or unknown. So in general, I'm taking unknown. So the population which is related to, which is corresponding to 0 suffix I is equal to 0, so that is being called as a control population, and the other populations which are K populations 1 to K, so they are being called as a treatment population. So generally it is of interest to compare several variances with the control. So because there are so many situations in real life where experimenters want to compare the variability of the treatments with a control, whichever is available, the control variance or the variance of the control treatment. So this is of general interest, which we are trying to consider. So in industry, one may be interested in comparing certain manufacturing lines which are new with that of the standard one. So with respect to variability, and the standard one is a control. So likewise in environmental study, our interest may be to compare the variability of the pollutant concentration at K different, which are at distant levels from the source of pollutant, with the variance of the pollutant concentration at the source of the pollutant. So means to say that there is variability of the pollutant concentration at the source, right? So and there are certain concentration at distant levels. So it's always of interest to see how they vary. So in such situations, one may take concentration of pollutant at source as a control population, and which are at different distances or distant levels are there. So they may be called as the K treatments. So the most common, the multiple comparison procedure, because I'll be talking more on the multiple comparison side. So the problem which are being dealt in the literature in MCPs, multiple comparison procedures, are of 3 types. So they are of these 3 types. One is all pairwise comparison. So when there is no control, so interest may be to compare the variances of the population among themselves. And if there are, say, 3 populations, so 3 combination 2 pairs will be there. So other type of problems are multiple comparisons are best. So if out of many populations which are available, so one is being regarded as the best. So bestness will be defined in well-defined sense. So in terms of variability, it may be the one which has the least variance, which may be known or unknown. So an interest is then to see that populations with other variability are at what distance from the best, right? So that is other type of second type of problem. So third type of problem is of multiple comparisons with the controls, which with which I'm dealing now. So our work is focused more on in this part on multiple comparison with the control. So the literature is available for other 2 types, which is all pairwise comparison as well as the multiple comparison with the best. So even in MCPs, when I'm talking about multiple comparison with the control, so again focus will be on the direction text family of hypotheses, which I'll be defining during the talk. What exactly it is. So literature, now some surveys there. So Dunnett was the person who started with the multiple comparison procedures. So when there are K normally distributed populations, so they have the mean mu i's and variance is sigma square, and the control treatment has normal with mean mu 0 and sigma square. So what they have worked up is of looking at whether ith population mean is equal to that of the control population, or that's for all populations simultaneously, and alternative could be greater than par. So they are called as a one-sided problem, and this is a two-sided problem when it is not equal to. So these type of problems they have taken. So and they control the the probability of the family-wise error rate they have taken to be equal to. So they tested simultaneously, not individually as such, right? So they try to work up, or they were rather worked up the critical constants which are there. One needs to accept or reject a null hypothesis which are there. So so that the probability of the acceptance region is equal to 1 minus alpha, and the family-wise error rate is equal to alpha. And simultaneous, this is sort of a simultaneous comparisons. So this is what the Dunnett procedure is. They have given the tables for D1 and D2, one-sided and two-sided situations. So remember, so all the alternatives are either one-sided or all the alternatives are two-sided. So these two different problems could be there. So either we are testing for whether mu I is greater than mu 0 simultaneously, or mu i's are not equal to mu 0. So then they had inverted the procedure to obtain the simultaneous confidence intervals in both situations, one-sided and two-sided, so that one has the maximum information that population means are at what distance from the control mean. So they were the intervals for the one-sided case, and these were the intervals for the two-sided situation. And their tables were given by Dunnett in their 64 paper for certain values of K, number of populations, then this degrees of freedom, alpha and rho. So then after that, Chen was the person who took up the case of two-parameter exponential distribution, and he dealt with the case of the location parameters or the guarantee lifetimes, and with the common variance. So remember, even in the Dunnett case, they have considered the sigma square to be same for all the populations, and even Chen in the it is 82 paper, not 84. So they also focused on the location parameters, but with the same variability of all the populations they have. So these are the estimators of sigma and of mu i's. So and their intervals again were, because they didn't talk about the controlled population and all that. So it was a case of multiple comparisons among the pairs. So these are their confidence intervals, and the family-wise error rate is, this is a family-wise error rate when simultaneously we are looking at the population's means are equal, and this is the critical region, and error probability is alpha. So so since the pioneering work of Dunnett, so many different versions have come up. Beckhofer was the person who talked about in terms of course, for the normal population, for the two-way layout. Then Spurrier in 1992 was the person who talked about certain optimal designs for one-sided and two-sided multiple comparisons, but they talked about not of means but of several variances with the control in normal settings. So again, of course, certain other variations were there, but Bofinger was the person who talked about two-sided simultaneous confidence intervals for location parameters of several two-parameter exponential distributions with a control, right? So remember, this is a sort of Chen procedure. Chen talked about all pairwise comparisons. Chen talked about all pairwise comparisons, but Bofinger was the person, in 92 again. So, but he talked about K exponential populations with different means, and they took a control population anyway. So, results were taken from, with support from there. So then the non-parametric versions of this are also available when the underlying distribution is not normally distributed. Steele was the person who started with that work based on Wilcoxon statistics or rank sum statistics. Extended the work of Dunnett. Spurrier, again in 92, there are two papers of Spurrier. So other one I talked about, and this is also a paper again in 92. This is a non-parametric side. So they extended the work of Steele to, one-way classification. Then different variations keep coming, because here they talked about Wilcoxon scores. So they took normal scores and all that. But work is there in the non-parametric side as well. But remember, in all the procedures, alternative was taken as either one-sided or two-sided. So all were either one-sided or all were two-sided. So most of the, as I said, most of the procedures which are there already available to us, they are all either one-sided or two-sided. Sometimes it may be desirable to consider some of the hypotheses in inferential families. So where some of the alternatives are one-sided and others are two-sided. So I'll give you certain situations also where all the hypotheses may not be one-sided within the testing itself. Some are one-sided and others are not two-sided. It's a mixture sort of thing. In such a situation, one will have to one will have inferential family consisting of a mixture of one-sided and two-sided. So and the earlier procedure in that situation will not be suitable. So such inferential families are called the directional mixed family of hypothesis. So where our focus is. So, so an example for that is in certain clinical trials where one is comparing various treatment to a placebo. And if there is a prior information that some of the treatments, which are existing treatments, so they are better in terms of their effects than the placebo. And on the other hand, there is no prior knowledge about the other treatments. So in that case, those. So where certain information is available that one is better or worse, then one-sided situation is there. And where there is no information available, in that case, two-sided alternative is there. So, and we are all in this case or the other case comparing with the placebo, which is a control treatment. So in such a situation, one will have situation of mixture of one-sided and two-sided, and we call it the direction mixed family of hypothesis. So we want to, in this case, also control the family-wise error rate to be equal to whatever is desired, say alpha, and so that both kind of such things are tested simultaneously within the setup. So under such families where we are interested in the direction mixed, so Chen was the person in their paper in Statistics in Medicine. So they talked about such family. So we were trying to test whether so they again talked about normal means only with the common variance. So we're trying to test mu I is equal to mu 0, population mean of the ith population is equal to that of the control, versus R out of the K are one-sided, and the remaining K minus R are two-sided. And we want to control the family-wise error rate to be equal to alpha. So up to R are one-sided and remaining K are two-sided alternatives. So, since he's working, so, certain other procedures have come up, but anyway, so what is his procedure? Let me let you know. So, and then again, Kuang was the person, he also talked about certain other phenomena in this direction family of hypothesis. Two papers are there. So, let's, see what we are doing. So, if we look into our situation, so we are considering that a sample of NI observation is taken from the normal populations, which I told in the beginning also. So, this is the sample mean of the ith population, and this is the maximum likelihood estimator of the sigma, so which is well known to us. So, we are interested in looking at, whether the variability of the ith population is equal to that of the control treatment. So, ratio is 1. So, where R of them are one-sided, so, and the remaining of interest to us is that K minus R are two-sided. So, which experimenter will be aware of, IS treatment is equal to that of the variability of the IS treatment is equal to that of the control treatment or the placebo, the variability for R of the populations, and the remaining it is two-sided. So, we are focusing on the variability part. So, and this is what we want, the family-wise error rate to be equal to alpha. So, the test statistics were, in the usual statistics, we are just taking the ratio of the sample variances of the ith sample variance to that of the control sample variance. So, and the proposed procedure for us is that we will be rejecting our null hypothesis in the one-sided case to that of the because as I said that R of them are one-sided. If this calculated value Fi statistics value is less than or equal to some value, because if we have this thing, so because sigma square is less than sigma square, so we will be having a decision in favor of this if smaller values are there of the statistics, right? So for smaller value of this, we'll be rejecting the null hypothesis of Hi0 against the HIC. And for the other case, when two-sided situations there, we'll be rejecting for large values as well as the small values for J's from R+1 to K. And we want to control the family-wise error rate to be equal to alpha simultaneously. So it's a simple statistics in the sense that the distributional will be easy to work it up, because if we divide it by the corresponding degrees of freedom and all that, so they will have chi-square and the ratio will be half distribution. So, and if we invert this procedure to the simultaneous confidence interval, so the simultaneous confidence interval for the ratio of ith population variability to that of the control variability, it will be this much. So, and for that of the remaining, which are n minus Rn numbers, the two-sided interval will be there because the two-sided hypothesis is there. So distributional theory is this. So the probability of accepting all the null hypotheses under the equality of the variabilities of all the k+1 population. So it is the critical regions we have, except if because if we're rejecting for the small values of fi. In the one-sided case, of course, we'll be accepting it for the large values, and if fj lies between these two, we'll be accepting, because we're rejecting for the large values and accepting for the small values. So it means if it lies between them, we'll be accepting, and adjusting the degrees of freedom and dividing by the corresponding standard deviations and all that, and they are equal, doesn't really matter. So we'll be able to get to the equation which is equal to this much. The major question was that from where to bring up these critical values, because they are not available as such, under the equality of the parameters, so under the null hypothesis. So this is the equation which we people have to solve. So we want to, for a given value of kr and the degrees of freedom nu1, nu2, nu_n, so which is n1 minus 1 and nu_n is equal to n. This is nu k. So we want to solve all this. This will be nu k. So we want to solve this equation so that this is satisfied for C1 and C2. So I mean, what should be C1 and C2? So this equation is satisfied for given choices of alpha, kr, mu1, and this. So this is not easy to work it up. So anyways, let me first take into account. So for any given value of this, these parameters, all that, so there may be several values of C1, C2 which will satisfy this equation. So but we wanted to work up a unique solution of this equation. So it means some condition has to be put on C1 and C2 so that we get a unique solution to this equation. So we have discussed in that context a certain optimal criteria to compute the unique pair of critical constant for the given configuration of alpha and these nus and k and r, where r is the number of how many are one-sided, and these are degrees of freedom, and this is alpha. So we have the concept of minimum expected allowance procedure. In fact, this is based on practically on any confidence interval is better when it is of the least length, right? So we exploited that criteria, and a reference to that is available in Kasila and Berger book also. So what it says is, in fact, this Fourier and Nizam has also talked about the expected average allowance. So because they were referring to more on one-sided and two-sided situation confidence intervals. So, but they were more on the side of that how much optimal sample size be taken, so that expected average minimum of expected average allowance is there. So I mean minimum of the length is there. So in Cheng, which I referred to earlier, so he also used this to find the shortest intervals for the simultaneous comparison of the mean and with the control population, but in the context of means. So this is what I'm defining. So this is expected allowance. This is expected, this is what this is there, expected allowance, how much it is being done. So because if one go back and look at the width of the interval of which is based on one-sided, it was nothing but C1 into Si square upon S0. So expected value of that have taken, and this is the proportion of one-sided out of the k, r upon k, and this is the k minus r upon k minus k is a proportion of the remaining which are two-sided, and the length of the C2 into this minus 1 minus C2 into this. So what we want to do is that we want to choose our C1 and C2 on the basis of the previous equation I referred to. So we want to choose C1 and C2 because there are multiple values available which will be satisfied for the given value. So, but we want to choose only that value which minimizes the expected error, expected allowance, expected average allowance, right? So we did it numerically and for different values of all these parameters, but again, only for the when degrees of freedom are equal for the control and the treatment population. So again, a restricted choice, because for different sample sizes, so for each different pair of sample sizes of the control and treatment populations, we will have very different tables. So just for doing or making tables, so one has to give the tables for the equal, just for understanding also and for using practically. So we've tabulated for KR new for different values of alpha. So am I audible? So because
yes, sir. Yes, sir. Yes, sir.
right. So then these are the tables which are being made up. So for different degrees of freedom, because sample sizes are same, so only one set of degrees of freedom will be there. So for different samples, for different populations, and these are R's. R basically represents the, as I said, so if R is 1, it means one of them is one-sided and the second one is two-sided. So upper value gives the the C1 value and the lower value. Upper and lower means not the upper confidence interval and lower confidence interval, but value. But upper value basically means for the one-sided situation, and this is for the second two-sided situation. So, and again, this is for one-sided. This is 1 out of the 3 is one-sided, and this is 2 out of the one-sided are 2 out of the 3 are one-sided. So these are the critical values which have been given. So for different values of alpha, alpha is 0.1, and then for 0.05, and then lastly for 0.01. So so from here one can implement at least the procedure, but with a lot of restriction as I've given. So sample size be equal, and then expected average allowance should also be minimized, so that to have a single value. Now the problem can also be applied to the exponential probability model, both for uncensored data and type 2 censored data, because more or less they behave in the same manner. So as we know, it occurs in clinical trials and other life testing experiments. So n items are put on test, and if a specified number fails, we stop the experiment, and the components which are still working, they are called the censored observations. This is type 2 censoring. So so again, K control populations are there, K treatment populations are there, and 1 control population is there. All are exponential. So this is exponential family. So and with the locations as Zi and the scales at theta I. So we know that the maximum, because as I'm interested in the scale parameter here, so theta I, so maybe Z's are unknown or known. So let's say they are unknown. So so in that case, we know that the maximum likelihood estimator under type 2 sensor data is this much. So this is total time, on test statistic. This is triple TI minus, because it's sensor data and XI. This is well-known estimator, and as it is chi-square distributed, so we all know that this estimator has a chi-square distribution or maybe gamma distribution, and properly standardized, with this multipliers and divided by the theta I. So this is a chi-square variant. And because there also SI square, which I took SI square upon S0 square. So similar kind of thing can be done here, because if we divide it by, the corresponding with a control, estimator theta 0. So m minus 1, m minus will cancel, and you will have, in a way, statistics based on SI star divided by S0 star. And Si0 star is chi-square, S0 star is also chi-square. So same tables can work up. Only thing is, nu has to be now 2 into m minus 1, which are here. So where wherever for a given value of m, so which is the number of censored values, so you can one can move ahead. I mean, so whatever tables have been worked out for the normal distribution variances, so same can be used for the exponential family as well, for working out the confidence rules for theta I upon theta 0 in the one-sided and two-sided together. It can also be applied to gamma probability model for the scale parameters, with say alpha known. So this is the gamma probability model, and the sample of size say n is taken from all the populations. So here also we know that the maximum likelihood estimator is xi bar upon alpha. So again, xi bar has a gamma distribution. So because it has a gamma distribution, so we can, if our interest is to test beta is 0 upon beta 0 is beta upon beta 0 is 1, versus r of them are one-sided and the remaining k minus are two-sided. So one can easily make a test if this ratio is lesser than this, and for one-sided, so we reject it, and if for the two-sided situation, if we are rejecting for large values as well as smaller values. And these are the critical constant with family where the rate is equal to alpha. So because this is chi-square, xi bar is chi-square, x0 bar is also chi-square. So again, those tables can be applied with the appropriate degrees of freedom, which can be chosen from there depending upon the degrees of freedom of xi bar and x0 bar. So the simulation study is also being carried out. So and it is being compared with the Spurrier 1992 procedure. So wherein all hypotheses are tested using the two-sided confidence interval. So ours is a mixture of the two, and it is only for the two-sided situation. So and we wanted to see that how much gain is there in the efficiency if we have the prior knowledge that R of them out of the K populations are one-sided and remaining are two-sided. So if each repetition, in each repetition of the simulation, so from the ith sample, NI observations are NI observations are there. So ith population is assumed as normal with mean 0 and variance sigma square, and the control of some size n0 is being assumed as well. Again, of course, mean is taken just for convenience, mean to be equal to 0 here. Situation in both situations. Rather k plus 1 situations, and variance here is sigma square, here is delta into sigma 0 square. So we're taking sample sizes to be equal again, and even the variances we are taking to be 1. So in a way, the difference is only of just a minute. Difference is only of that this is standard normal, data is being generated from standard normal, and here data is generated from normal with 0 and delta. And delta, depending, we will keep changing the delta and see what happens. So any pair power probability of rejecting at least one HI0 is estimated for the proposed procedure by. Hello.
Sir, please conclude your talk within 5 minutes time.
Sure, I will. By the proportion of time, at least one hypothesis is rejected among this 1 lakh repetition, 100,000 repetitions. So as we know that power is nothing but because once we know that we have deviated from the null hypothesis, so how best the procedure is able to, or the critical region is able to look at that. So how many number of time it is able to do that. So, and we just count that proportion, and that is the power of the procedure. So in figure 3.1 and 3.b, so we present the percentage increase in the average power when our procedure is compared to that of the Spurrier procedure with, say, sample size of, say, 16, because 15 I'm taking the degrees of freedom, sample size, say, 16 taken, 3 is there, the number of populations, R could be 1 and 2, and K is equal to 10, and then R is differently taken, 3, 5, and 8. The percentage gain is power is plotted against delta, for delta from 1 to 5. If delta is 1, it means there is no difference. So look at this. If we look at this, so delta, changing of delta means that control variability is changing, all of the treatments in fact have all the variability, right? So this is the percentage increase. So if delta is equal to 1, it means control and treatment populations have the same variability. So it means not much of gain is there. So as delta increases, and R is also, if R is equal to 1, R is equal to 1 means one of them is one-sided and others are two-sided. So out of the 3, 2 are two-sided and 1 is one-sided. So there is a gain. The gain starts. So as it goes to maybe up to here. So gain is there, but after that, not much gain is there, right? But of course, gain is there, but it stabilizes as delta increases. So even for R2, it is more. So similarly, we have done it for K10 and U15 for different values of R. So what we see is, as delta becomes larger, both procedures have approximately the same power, but specifically if I look at one case, we have to conclude as I've been asked. So if K is equal to 10, R is equal to 8, and delta is equal to 1 by 4, the increase in power is about 15% that of Spurrier procedure, where Spurrier is two-sided, ours is one-sided. So I've taken a numerical example also of the data taken from Lee in their paper. So where they have the data of testosterone levels measured in microgram per deciliter of men in 4 different groups, classified according to their smoking habit. So populations are being labeled as Pi 0, Pi 1, Pi 2, and Pi 3. Smokers data is there. So this is the data. So they are the testosterone levels. Non-smokers, former smokers, and light smokers, and 4 populations are there. One control one is non-smokers. So 11 tests were used to look into their variability, that it is same for all the 4 populations or it is different, and it has been looked at that p-value is 0.044. So it means we are rejecting the null hypothesis. So they have heterogeneity among themselves. So in the light of this inference, one may further wish to know which treatment group has variance significantly less than the variance of the control. So thus it is reasonable to believe that smoking decreases the variability of testosterone level and further variability of non-smoker group and former smoker group. So what we are, let me brief up that. So because it is generally seen or could be thought of that former smokers, because they're former, right? So it could be believed that non-smokers and former smoker have more or less the same variability. So of comparing former smoker with non-smoker could be taken as a 2-sided alternative, but with light smokers and non-smoker with that of non-smokers and heavy smokers with that of the non-smoker could be considered as a one-sided case. Because that's what pre-information if we have. So this kind of hypothesis could be certain that for I is equal to 2, 3, it's a one-sided situation. Variability of the light smoker and heavy smokers is light smokers is lesser than that of the non-smokers, and the heavy smokers is also less than that of the non-smoker. But of former smokers and no smokers, it is not equal to it. I mean, so it could be either way. So we have run it on this data set, the procedure, and what we see is 95% simultaneous confidence intervals are of our procedure are because first was two-sided and the remaining were one-sided. So these are the intervals, and for Fourier procedure, these are the intervals. We can clearly see their lengths have got decreased, but information is the same. So all the intervals length is smaller than that of the corresponding Fourier procedure, and decision has not got changed as such. If we look into this, one is included in this, one is also included in this. It means we are accepting these 2 variabilities of the control of the first one. Treatment first variability is same as that of the control. Second treatment also has a variability same as of this, but in this case, because one is not included, so it means third population, which are heavy smokers with that of control, is not included. Is not equal to that of the sigma square of the control, which are non-smokers, which are non-smokers, and same kind of decision is there. So so this is already I have said. So these are some of the references, please. Thank you so much.
Thank you, Professor Narendra Kumar. Actually, now it's a time for discussion. The platform is open for discussion.
Sorry, I've taken a little longer. It looks like.
No problem, sir. No problem. Actually, it was a wonderful talk, and you have nicely presented this fundamental problem of inference. And I think there are many more problems to work out, like the non-parametric type problem, as you mentioned.
We are working on that. We're working.
Okay. And also, I think in the simulation study, you have mainly concerned about the primary problem. And what about the censoring problem that you mentioned, the type 2 censored case that you have in the considered?
Yeah, so application-wise, I've discussed, but not in general.
I see. Okay. Any questions or queries? Okay, if there are no queries, let me thank once again Professor Narendra Kumar for the excellent talk. It's a very fundamental problem that you have presented here. And on behalf of the organizing committee, I once again thank for presenting this talk in this conference. Thank you, sir.
Thank you so much. Thank you so much. Thank you.
So now let us move to the next speaker. we have already invited Professor Ashokan to this platform, and because of some technical reasons, he exited from this video, session. Now, I think everything is okay, your audio and the presentation. So,
I don't know. Anyway, let's see.
okay.
So the problem is it's coming companion mode, and I think
now the sound is okay. Your sound is very much clear.
Yeah.
Here.
So I think your side is going to be present there, and I will only talk from here. That's the way.
No. You can continue now. Now the presentation slide is okay here. So please, over to you, sir.
Okay. Thank you for giving an opportunity to give a talk in the ICSTC 2022 conference. This talk is based on a specific situation where, the binary measurement system, where we have a continuous measurement. So that is a interesting one in an industrial scenario. So without much delay, I will go to my talk. Can you go to the second slide? Okay. So as an outline of this talk, I'll give you a basic introduction of the measurement system analysis. Then we will a little bit on what is the existing methods available in the attribute measurement system analysis, measurement system analysis. Then I'm talking about the particular situation where we have this cost-effective binary measurement system model, what we are proposing, and two-phase partial verification plans, and I conclude. Next, please. Okay, so the main objective of any quality improvement program in an industrial scenario is to produce the product that satisfy the customer specification. So customer has some specification, and the plan is to have produce a high quality product as per the specification. So a lot of activities like a quality management principles are using there, producing the items that are close to the target. So the main thing is we have a product and we identify the quality parameters and we want to achieve that. So the target is very, very important. And once you try to achieve the target, as a statistician, we know, or it is impossible to make exact value. So we want a minimum variation around it. So that is the two things when you look at an industrial problem. So hit the target with the minimum variation around it. And especially main industrial scenario, in the statistical analysis is we estimate the mean. Then you say the target, then we estimate the mean and see the target value and see normally the difference, what normally we call the bias. And we look at the variance also and monitoring over the time. So we want to observe this over the time and see that everything is over control. That normally we use a lot of control charts and other procedures to achieve that. And one thing is very easy to achieve the target because we can easily to control it, but the variability is very, very difficult. So reducing the variability is very important, but it is not easy. So a lot of techniques can be used there in the industrial scenario, like a design of experiment also you can use for finding out a best combination of the parameters that give you an output with the minimum variance. Okay, next slide, please. So then how do you approach this type of problem? So we observe this, the process, that is the process from which the products are coming, as a combination of men. That is, men means just employees or workers or anything, they're not necessarily men or women also. Okay, so the workforce, because they have combination, a lot of activities are coming from the operators, and the machine is a part of that. Material is there, methods are there, and measurement also, and environment. So all these activities or all these factors affecting your process, which results the variation in the product. And if you look at that way, it is easy to assess the process variation separately. So how much is the variation because of the operators? How much is because of the machine-to-machine variation? So how do you reduce it? Or within machine variation? And material, the suppliers are coming, different suppliers are there. Then the different methods they use. And one component we are very, very important is the measurement. So that is what we are going to talk more on that today, and the environment in which the process is going on. So the variation due to measurement systems play an important role in the overall variation. So when we look at the overall variation of the product coming from this process, we want to know how much it is due to the measurement. So the measurements. So in a thumb rule, I can give you in general what the industry use is a 10% of the variation could be from the measurement. So, so when the industry, they use the specification means the allowed by the design people. So if you have a measurement like a 5, then they give plus minus 0.01, that is 0.1. That means we can allow the value from 4.9 to 5.1, then the product will be good quality. So that plus minus 0.1 allowance. So the design people make that measurement, that 0.2, the difference, that is maybe because of the material, method, and everything like that. So in that allowance is normally given 10%, that is because of the measurement. So it is important to conduct a measurement system analysis to know how much the measurement variation contribute to the total variation. So if it is much more than 10%, then we need to understand why it is coming, what is the problem, and try to reduce one component of that variation. Okay, next please. So normally when we take the measurement of any study or in statistics, we normally when we take a measurement, we always think that it is the correct measurement. And we may able to measure the true value of the product quality characteristics. That is the assumption we always make. So we get a 4.235, we think that that measurement is correct, but it's generally not true. So there are variations are coming, and the way, for example, if you look at a clock from one side or another side, or from the bottom or from the top, we can see the times are different. Okay, so the way you look at it and the way you measure it, very, very important. So the variation due to the measurement system play an important role in the overall variation. So we need to know its contribution to that. Okay, so can you go please next? So when you look at the measurements, now there are different types of measurements. We can say most of them we normally come across is the continuous measurements, and the measurement system analysis is well developed for the continuous measurement, like temperature, pressure, length, weight, height, those things. Okay, so most of the measurements, so it's very easy to do it, and there is a measurement system analysis available. Standards are developed, and I think it's the QS 9000, the quality system 9000, especially made for the automobile industry. There's a standard is there how to conduct these studies over the time and everything. So this is very, very well established one. For a continuous measurement, we can estimate the measurement variation components as a bias, what is the stability and the linearity and repeatability and reproducibility. So from that measurements, we can find out what are the causes of this high values of this measurement variation. So it may be due to the bias and stability, linearity. I'll just give you a simple idea about what is each component of that. Next, please. So the bias, because if we have a process and we have a measurement system there, so we can estimate these components. So the bias is the difference between the observed averages of the measurements and the reference value. So that is means we have a part and we know what is the reference value. So we can get these different measurements and take the average and the reference value. So this difference is what normally called the bias. So the reference value, what in statistics normally say the parameter value, the true value, but most of the time it may not be available in industrial scenario. So what they normally do is they send it to a laboratory and get the value of the measurement. Okay, so then this measurement, the product can be measured by different people, and if so many things can be done, and you can average of these, then you can get the bias. So there's a procedure how to conduct the study to estimate the bias. And the stability. The second component is the stability is the total variation in the measurement obtained with a measurement system on the same master or the part, or master means the true, what you can say that, for example, the weight, so 2 kg or 1 kg or something, the masters are available. So you can do the test on the master because we know the true value. Or you can have different parts with a single characteristics over the extended time period. So when you measure it over the time, okay, so over the time means today you do, and after 1 month you do, and 3 months you do, like this, and over the time, how this variation is coming over the time. So that is the stability. So because you know that in the industry, we normally do this calibration and all, after some time, the wear and tear of the equipment and everything. So that is the one type of estimation we do as a measurement analysis. Here is stability. So how this equipment and your measurement system works over the time. And the linearity is the difference in the bias value. So bias means the first one you talk about, and through the expected operating range of the gauge. So for example, if you have a weighing machine, so it can measure also maybe 10 grams, also we can make 500 grams. So how this bias over the operating range of this. So that is the linearity, we can estimate that. And the two other important one is the repeatability and reproducibility. So the repeatability is the variation in measurements obtained with one measurement instrument when used several times by an appraiser while measuring the identical characteristics on the same part. So we have a same part and same type of measurement you do by the same operator repeatedly. So if you do the same person did 10 times, so what is the variability is coming? So it is more on the repeatability or the repeatable quality of the individual who measuring it. So when you talk about the reproducibility, is the variation of the average measurements made by the different appraisers using the same instrument when measuring the identical characters on the same part. So when you do the repeatability and you get an average of the values, then you repeat the same thing with another person, another inspector like this, then you find out the difference in the averages of that. So that is called the reproducibility. So the repeatability is very important and reproducibility is important. So there is some standards are available for how much it can vary. So for example, I have involved in a study where the laboratory study where the repeatability and reproducibilities are compared. So we are part of the study in the US where we conducted a study with a large number of laboratories, and we made a sample and sent it to top laboratories, and starting from the preparation of the sample, and you can see that shipping it, then they tested it. A lot of conditions are there. See the system, the measurement systems are not that easy. Sometimes you can see measuring a length or weight or something that is very, very simple, but a chemical experiments and all, the measurements are not easy. So identifying the protein and the genetic values of those things, that's not complicated, very complicated. So they have to follow the systematic procedure, a set of rules and regulations. Then based on that, if you do otherwise, you won't get this repeatability and reproducibility. So the consistency in the measurements are very, very important. So these are all very easy to do in a when the measurement you have is a continuous and well-established methods are available. Okay, can you go to the next slide? Okay, so now I'm talking about the attribute measurement system, where we are not going to get exact measurement. Either you can get a a finite number of categories is getting. The measurements are like that. The attribute, because attributes are very, So as I can say 0-1 category, a binary, the measurements are go and no go, or fail or pass. So that type of situation. Or we can say the other category could be very good, good, average, poor, and very poor. So when you do a measurements on the clothes, fabric, so we can see that quality of the one, we can say very good or good, average, you can do it. Otherwise, we say reject or accept. So 2 categories. So when those measurements are coming there, how do you do a measurement system analysis in that? So this is a quantifiable risk when using any measurement system here, making decisions. In this case, the largest risk is at the category boundaries. So when it is coming on the boundaries of these very good and good, where the numbers are coming, then this risk is coming. So most commonly used method in the attribute measurement system is the cross-tab or kappa method, which I will explain in because I don't want to go for too much detail about that. I'll give an example and give you an idea. Okay, next please. So I don't know if you can see this or not. So this is an attribute measurement system. Like we have different parts, and A1, A2, A3 is given as attribute. Appraiser 1, again second measurement, third measurement, and second is B. Second appraiser, measurement 1, measurement 2, measurement 3, and like this. So that means if we conduct a study, we have a part, and inspector is going to measure first and see the measurement is pass or fail, 0-1 category. Again, measure it again, 0-1 or whatever it may be. So you cannot expect always you get 0-0-0 or 1-1-1. Sometimes you get 0-0, then next one is maybe 1. So that is the way the attribute is coming. Because for measurement, you can say 2.42, 2.43, 2.42 again. So 3 measurements. But attribute, you can go as a 0-1. Because if it is very good and it is very close to the, not in the boundary, you always get 0-0 maybe. But if it is in the boundary, very, very difficult to get the same answer. So we have to see how this is going to work out. So I will explain this kappa method using this data set. And can you go to the next one? Okay, so the method, consider the attribute measurement system study where we have 3 appraisers, each repeat measurement 3 times on 50 parts. So out of the 50 parts, 34 are go type, referred to as 0 or 1, as 1 and good. And the remaining 16 are no go type, that is referred as 0 or bad. Okay, so if you take 2 appraiser A and B, we can construct a 2x2 table like A and B and 0. So A is saying 0, B is saying 0. That means both are agree, 44 cases. But A is saying 0, but the B is saying 1. That is 6 cases that disagree. And you can say 2x2 contingency table. Okay, so we have 150 there. Then we can see that these measurements are coming there. So
this is basically the test for homogeneity, right?
Yeah. So this is but the way this calculating is how A and B are agreeable or not. The same decision is coming, and B and 0-0 means both are agree to the same decision, but 1 and 1 also same. But if they disagree with the other 2, so we can find out expected count in each cell also is a normal way, and you can appraisers are independent normal. Independent. Sorry. Can you go to the next one? So to determine the level of agreement of appraiser, we can use the Cohen's kappa, which measures the agreement between the evaluation of the two rates when both are rating the same object. So when both are giving the same rating on the same subject, then we can measure this one. So a kappa value of 1 indicate the perfect agreement, and value of 0 indicate the agreements is no better than chance. So the kappa is only available for tables which both variables use the same category values and both variables have the same number of category. So kappa is a measure of the inter-rater agreement that tests if the counts is the original diagonal cells, that is order agrees, the same rating, differ from those who are expected with chance alone. Okay, so this is the existing method available, and you can get. Can you go to the next slide? So this is available in the literature, and you can always refer those. So I just give in explaining you how we can. What is the current way people are doing this? Let P naught be the sum of the observed proportions in the diagonal cells, and PE is the sum of the expected proportion in the diagonal cell. Then we can define the kappa as P naught minus PE by 1 minus PE. Okay, so you can get this value of the kappa, and it is here is 0.87. So if you take A and B, you can get a 0.87. So either one is good agreement, otherwise, So we can, around the points, a general rule of thumb is that kappa is greater than 0.75 indicate the good to excellent agreement with a maximum value of 1, and the value less than 0.4 indicate the poor agreement. So the idea here is get some how these two appraisals are agreeable or not. If it is not there, the way they are looking or the way they are measuring is not correct. So we need to have a proper measurement system, and they need a better training and everything. Okay, please, next one. So we can also compute the effectiveness of the measurement system also by effectiveness is the number of a correct decision divided by total number of opportunities for a decision. Okay, so that also you can easily do that. Okay, so we can see that the true way, it. So how much is the calculate the score for each, and you can find out the confidence interval and everything. Okay, next please. So so system score and effective score, also we can see the reference value, also we can see the overall, we can also calculate that. Okay, next please. So now this is the existing people do this way, that is we have already a measurement system, attribute system, then you can kappa, you can calculate it, then how much agreement both people are doing it. So we can do it comparing A and B or combining A with the standard only. So now we considering a particular situation, because most of this measurement we talk about attribute, we can only say yes or no, but we cannot measure it. But now we assume that we have a continuous characteristics that can be measured by an accurate but expensive one, time consuming or a destructive measurement system. So we can measure it, but it is very, very, very expensive. So instead, then for that system we call the gold, it's a gold standard. So we can measure it, but it's very, very expensive. Because of those limitations, the cost of using the gold standard is very, very high. So we can use a binary measurement system that classify the parts as pass or fail. So we are assuming here we can measure the parts as an attribute where pass or fail, but we can have a measurement, a continuous measurement. It is expensive, but it is possible to measure it. And for example, a go, no go gauges may be used to check the hole diameters instead of coordinate measurement machine. So there are expensive measurement systems are available, but you can use a go, no go measurement system. We can use it, I think say we can say yes, pass or fail. But we can also expensive machinery to do that, but it is expensive. Okay, so we don't want that. So in this study, what we are trying to do is we are trying to make use of both and see how we can go ahead. Okay, can please next one. So the BMS, the binary measurement system, makes misclassification error in this case. A good part may fail or a bad part may pass. So that risk is always there, just like a testing a hypothesis. We just reject the null hypothesis when it is true. So that case like that. So in the binary, there's an issue also we can consider where a good part may fail or a bad part may pass. So if the measurements are continuous type, we can use the gauge RR and study and we can use it. But here, the same is not true for the estimation of misclassification error in the binary system, since the large number of parts and measurements are required to get the estimates in a good precision. So in this case, we need to have a large estimation is needed and large parts are required. So our main objective here to propose a new efficient BMS measurement plan that provides estimates and standard errors for both misclassification and right. Okay, so the idea is to find out what is the misclassification right and how we can utilize that using a efficient binary measurements assessment plan. Next, please. So the assumptions here, so for each part, there is a continuous variate available, okay? So we have a measurement, a part is available. We can measure the quality of the product, and which is a continuous variate with a one-sided specification C. So we can have both, but for this particular study, we consider only one specification. So for example, normally we say, 4.9 to 5.1, you can accept. That means the two-sided specification. So here is anything more than 4.9 is acceptable. So there's a one-sided here, we consider. And X can be determined without error by a gold standard. So that is another assumption we are making. So we can find out this measurement of this product or part by a gold standard. That is the correct value you can find out. And for any single binary measurement, we define y equal to 1 or 0. So for the same part, we can also measure, and we can, binary measurement, we can make the go, no go, 1 or 0. So we can inspect the part repeatedly without affecting the value of the X. So that's another assumption we are going to make. That is, we can measure a continuous value. Also, we can repeatedly do the binary measurements, that is pass or fail, without affecting the value of the F. It means some tests are like that. When you do it inspection, it may damage or slightly damage or something. But here we are assuming that no, we can do repeatedly the binary measurement system, so its value will not change. Like if you look at a cloth and it's a good or bad, so again you do the same thing. But over the time, if you do 10 times, the qualities remain the same. It won't affect anything, the value of the underlying variable X. Next, please. So what we are trying to see here is we can, we have a system where we can have both X, the continuous measurement, also a binary measurement, but continuous measurement is expensive. So we are trying to use both. So let X be the value of the gold standard measurement.
You have to conclude. You have to conclude it by 5 minutes time. Next to 5 minutes time.
Sorry.
You have already elapsed about 30 minutes. So 5 more minutes.
Oh, okay. So X follows the normal distribution. So continuous the variate is following the normal distribution with the density. And Y is 1 is a randomly selected part passes, and the inspection Y equals 0 otherwise. Okay. So we can, for a given part, given X value, we can find out the probability P Y equal to 1 given X, the QX, the exponential form. Okay. We can also use the Y equal to 0 given X, 1 minus QX. Okay. Next, please. So for our repeated measurements with the binary system on any part, we assume a conditional independence here. So Y equal to Y1 equal to Y1. So we are repeating the measurements for a given part, we can conditionally they are independent. So measurement with the BMS on a different parts are independent also. Okay, next please. So based on this modeling, we can define the false acceptance probability as probability y equal to 1 given x less than c is the probability that out of specification, the bad part passes the inspection. And the same way, we can also calculate the false rejection probability, FRP, as y equal to 0, probability y equal to 0 given x less than or equal to c is the probability that the inspection, the good part, failed the inspection. Okay, next please. So based on that model, we can estimate, we can write the misclassification probabilities in terms of the parameters of the model. So we can define the FRP and the FAP and the probability that x greater than or equal to c. You can define because we have this probability, conditional probability, and we can all do this way. Okay, next please. So note that once we have the estimates of these 4 parameters in this model, alpha, beta, mu, and sigma, we can derive the estimate of the FRP and FAP and the pi, as well as the other characteristics of interest, such as probability x greater than c given y equal to 1, a measure of the quality that we are giving the customer receiving. Okay. So what we did, we used the maximum likelihood method here for the logistic regression to estimate these parameters. Okay, so I'm not going to detail about this MLE estimate and modeling of that. Okay, can you go please next slide? So what we are suggesting here is our proposed 2-phase plan is the phase 1, select n parts at random and inspect each part r times with the binary measurement system and place these parts in bins identified by the number of passes s equal to 1 to r. So for example, if you have a part and you repeatedly do r times, then you say how many passes are there. So it's a binary, okay? So you can say maybe 1 pass or 2 pass or r pass maximum. So ns is the number of parts in the bin, yes. So in the phase 2, what we do is we select ms parts at random from the bin s and measure each selected parts with a gold standard. Okay, so now combining these both phases information, we can write the likelihood. So this is a paper you can always see. This is available. If anybody wanted, you can send this copy of this one. Chen, Steiner, McKay, and Barry, 2022. It is next slide, please. It is in the Communication Statistics journal. Okay, next, please. So I give you an example here and try to go a little bit faster because I don't have much time. So the diameter of the hole as a machine product and the cutoff value is 3, and this is a no-go and misclassification can occur. Okay, can you go to the next slide? So we can assess the binary measurement system here. I applied the proposed 2-phase plan. So phase 1, we selected 200 parts randomly from the production process and classified each part r equal to 4 times. With the BMS, the data is given here. So the bin number and number of passes, how many parts are passed with the or 0 or 1. Okay, next slide. And in the phase 2, we selected 20 parts, 6 from bin 1, 8 from bin 2, and 6 from bin 3, and measured the hole diameter for each part with the gold standard. So these are the measurements from each bin. And we didn't take any sample from 0 and 4, that I will tell you later why. Okay, can you go next slide? So using the data from the phase 1 and phase 2, we find the maximal likelihood estimates for the 4 parameters and by numerically maximizing the log likelihood. So we get the alpha, beta, mu, and with the standard errors are in the one. And the false FRP is 0.158 and standard deviation is 0.023 and FAP is 0.03. Okay, okay, please next one. So one of the assumptions we made is the continuous measurement Gaussian distribution. So we can also see a QQ plot and see that assumption we can verify. Okay, next slide, please. So the proposed two-phase plan has a number of design parameters, number of parts in the phase 1, number of repeater measurement R, number of parts M selected from verification in the phase. So these are the parameters, and how do you go about that? So we can explore these possible choices, the design parameters to estimate the misclassification rate, FAP and FRP. And to calculate the standard error, we use the Fisher information also in this case. Next one, please. So what we did is we took a two-cube factorial experiment model here. So what is the value of the FAP can consider 0.02 and 0.01, and FRP is 0.2, 0.1, and the pi equal to 0.97 and 0.9. So we take, then we can see 2 cube means 8 experimental scenarios can be given. So we can, assuming a value mu equal to 0 and C equal to 2 without any problem. So we can combination value, we can determine the corresponding values of the alpha, beta, sigma. So given this value, what is the corresponding the parameter value, we can estimate using the formula given earlier. Okay, next one. So this one, you can see that we have FRP and FAP. So the two plots will give you the scaled standard deviation. So that means the maximum is going to be 1 standard deviation there. So we can see that when the number of repeated measurements are increasing, the scaled and the FAP value we can see is then we can stabilize there. So that way we can see that the number of the repeated measurement can go somewhere around 4 sample. Okay, so that's the one conclusion there. Okay, next slide, please. And giving that fixing the R equal to 4 and we fix the sample size 200, the problem is to choose how many samples from each bin. Okay, so we consider different scenario A, B, C, D, H, different plans, equal bins. Sometimes we see all we are taking sample from each bin 20, but otherwise you take a lower 2 and upper 2, in between increasing. The middle one we get more samples, and the plan C, this is the important one. So first lower bins we didn't take anything, upper bin we didn't take anything, 6, 8, 6. So we consider the different scenario and see how it is performing. Okay, next slide, please.
Okay,
so we can see
sir,
this,
please conclude.
Yeah, okay, I'm going to yeah. So, so we can see that, how the FRP is performing for different plan A, B, C, D, H. So we can see that the plan C seems to be better here because there's low variability in that and the plan C. Okay, that's what we suggested in that. Okay, can you go to the last slide? Or just one more, yeah. So I just concluding here, this from figure we can see the C is better than other plan because there was standard deviation, and plan B is almost as good as the plan C. So this suggested that sampling from the middle bins provide more information. Okay, so if you have any more detail about this, and there are a lot of other information, so you can refer this paper, the communication statistics, the case studies, data analysis, and applications, published in 2022. Okay, thank you.
Okay, thank you very much, Professor Ashokan, for the wonderful talk. Actually, he gave a nice applied problem to this audience, and I think this will be useful in different contexts, not only in the industry, but in different other situations. And I think you have used this binary concept and the continuous or the less information and the nominal and real data mixing, or real metric data, okay, metric scale. So you are actually considering this continuous measurements, but without using much of the, maybe this continuous measurement may be most costly than the binary measurements, and most of the times this continuous measurement may not be available. So this will be quite useful because most of the time you are getting this categorical data, and you are selecting some of the data, some of the bins, and then selecting the actual information from the bins. So this is an interesting method of this assessing measurement, binary measurements along with the continuous value. So thank you very much, Professor Ashokan, for the nice presentation. So I'm not going for the audience queries this time because we have already taken 15 more time compared to the, with respect to the allotted time. So now I think this session, it was a wonderful session, and both the speakers presented nicely. The first speaker, Professor Narendra Kumar, he actually presented the fundamental type problem, inference problem, and now the Professor Ashokan, he presented the applied type problem. And on behalf of the organizing committee, let me extend my sincere thanks to both the speakers and for the careful and patient listening for the audience. Thank you. Over to Professor Satish Kumar.
Thank you, Professor Sunoj, for sharing this session in a very excellent way. And also the speakers, Professor Narendra Kumar as well as Professor Ashokan, have done a very excellent presentation. And we are very much grateful to you, Professors, Professor Ashokan and Professor Narendra Kumar, for your nice deliberations through this ICSTC conference.
Thank you so much.
Thank you, Professor. Thank you. We expect your support. Yeah, thank you so much. Thank you. Now let us move to the next session because we are running a little bit late. Next session we have Sheila Mishra Professor Sheila Mishra is here to chair this session. And before Sadinder, please introduce our chair and support her in whatever way to for the smooth running of the session, please.
Okay, thank you, sir. Good evening to all. A warm greetings to everyone. We have Dr. Sheila Mishra, Professor and Head to the Department of Statistics, University of Lucknow, with us right now to chair this session. Dr. Sheila Mishra works in the wide area of estimation theory using different estimation techniques of natural phenomena in variety of fields and problems raised in real life. That includes a study on gender-based work environment in higher education and its impact on women faculties, and improved estimator of population mean using different methods, etc. Her research interests include sampling techniques, applied statistics, gender statistics, biostatistics, and sequential inferences. She has authored and co-authored more than 100 research publications in these different areas of research. More than that, 8 research fellows are awarded PhD under her guidance, and 5 are ongoing. She has several awards and fellowship of the academic bodies. Among them, she has awarded UGC CSIR Junior Research Fellowship through All India level National Eligibility Test for Research and International Educator of the Year award by International Biographical Center, Cambridge, England in 2006. Dr. Sheila Mishra is currently an editorial board member of several academic journals and an active reviewer. Moreover, she is a subject expert in Union Public Service Commission, Uttaranchal Public Service Commission, etc. It is with great pleasure and honor that I invite you, Professor, for chairing this session. Over to you, ma'am.
Thank you so much for the kind introduction, and my namaskars to everyone, especially Professor Satish Kumar, who is continuously so much effort and endeavor he has put in ICSTC, all ICSTCs, and especially 2022. And it is an honor to be at this platform and to hear the excellent research publications and research opinions and thoughts from learned speakers. So it is my pleasure to welcome everyone in the technical session number 16. And we have two invited speakers here. And I welcome my friend Professor Sangeeta Arora from Punjab University. Madam, very welcome to you. And it is so nice to see you after a long time. And she is very senior and a well-known researcher and academician, and has been very dynamically contributing to her research area. And today she is going to speak on ordering relations for some inequality curves. So, madam, the floor is yours. And because of the paucity of time, I think we can take 30 minutes each, and a brief question and answer session if the participants wish so. So over to you, madam. Professor Sangeeta Arora.
Thank you so much. Thank you so much, Professor Sheila Mishra. It is nice to see you, at least on the online platform. We don't get the chance to meet often as such. Anyway, thanks so much. And I am also thankful to Professor Satish Kumar for giving me this opportunity for the last 3 years continuously. So I'm interacting on this platform. So today I'm going to just talk about the ordering relationships. So this is, first of all, let me share my screen so that at least I can see it, you can see it. Is it visible?
Yeah, madam. Yeah. Fine.
So this is the ordering relation for some inequality curves I will be talking of, which is not based on one single topic. So this is a review of the work on the area in which I am working. So this is some joint work along with my colleague, Professor Kalpana Mahajan, and one of my research student, Dr. Preeti Ratan. So this is the roadmap of my talk. This is the concept of inequality. First of all, I will be talking about, because this is ordering relations regarding some inequality curves. So what is inequality? And then particularly, I will be talking about the Lorentz curve as an inequality measure. Then I will be talking about the variants of the Lorentz curves. So how many variants are available in literature? In case we cannot use the Lorentz curve, options are available. Then ordering and relations between various curves of inequality and some dominance relationships which emerge out of it. And then dominance results for the power, and some two specific distributions I will be talking of. Dominance results for power function distribution, and ordering results for generalized inverse Weibull distribution. So let me just start with the inequality. The word of inequality suggests a variation from some idea of equality. This is obvious. So income inequality is explained as a measure of degree to which income is distributed unevenly among residents of an area. For example, if a person receives less than his impartial share of cumulative income, the distribution will be unequal. This is how we perceive inequality in our day-to-day scenario, right? And once we talk of inequality, we talk of two concepts. One is perfect inequality, another is perfect equality. Perfect equality means all the incomes units receive equal incomes, whereas it means income is equally distributed. You can say that X is equal to mu if X is a random variable which represents income. And whereas perfect inequality arises when a single unit receives the entire income. This is an extreme case. It means if there are n individuals, so n minus 1 receives zero income, 1 receives all the income. These are two extreme cases. Generally, they may not be perceived. So we will like to see how much inequality is there. That is the basic concern, and that is the concern of any viable economy, because we will like to see that income, there should be as less inequality, because this is important from social welfare point of view as well. So the main curve, or the main measure which is being used to assess inequality, that is the Lorentz curve. Till date, it is still popular. And Lorentz curve is widely used to describe and compare inequality in income in one or more scenarios. So you can have you can just have 1 year, or you can have the different time periods, or you can have the different, you can just say the different countries or the different places where you can compare you can use the Lorentz curve to see the inequality. The curve gives the connection. What is this curve actually? This curve gives the connection between the cumulative proportion of income units and the cumulative proportion of the income received when the incomes are arranged in the ascending order. So we arrange the income in ascending orders, and then this is a relationship. What is the cumulative proportion? So we arrange from bottom to this, bottom to the, you can just say, to the next target. So from the lowest to the, from the poorest to the richest, we arrange, and then see how much the lower bottom percent, how much, whether they are getting the equal income or not. So mathematically, I will explain it just now. So let X be the income that income X of a unit be non-negative random variable with probability density function Fx and cumulative CDF as equal to Fx, right? And this I can interpret in terms of inequality. This can be interpreted as the proportion of units having income less than or equal to X. Fx can be represented as cumulative proportion of units having income less than or equal to X. And let F1X, this be the proportion of income received by individuals with income less than or equal to S. And suppose that expected value of X exists, and then this F1X is also known as a first moment distribution function. It is being defined as such. And F1, because it is a distribution function, this also varies from 0 to 1. This one can refer to the book by the paper by the Kakwani and Podder also. Otherwise, this is a very well-known statistic. And Lorentz curve is the relationship between Fx, cumulative proportion of the units, and the cumulative proportion of the income which these receive. And it is easy to see that this L0 and L1, how I am using. So this is the parametric form of this. I am just coming. So Fx and F, this way, I can just, this is my Fx, this is my F1x, and this is my Lorentz curve. But to explain it more clearly, generally we use the term L, L1, LP. So LP, let LP be the F1x. Let first moment distribution function be denoted by LP, where P is equal to Fx, and P lies between 0 and 1. And then we can also express that LP is equal to F1x, where P is equal to this. And LP is interpreted as a fraction of the total income received by the lowest pth fraction of the families. And the diagonal, this is called the egalitarian line. You can refer to this figure. So I can just say this is my P, this is Fx, or this is your LP, which is F1x, and this is the relationship between this. So you can just arrange the, you can just say you can arrange the income from the poorest to the richest, from the, because from the bottom to the top. So you can just say the lowest 20%, lowest 40%, lowest 60%, lowest 80%, and that's 100. Actually, should coincide with here. So how somehow the graph is not properly put. So this is the, it means then you can just see this is the curve. This is known as a Lorentz curve. If the bottom 20%, they get the 20%, they will, it should fall here. 40% fall here. But because 20%, bottom 20%, they are getting less than their share. They may be getting 2%, 3%. So that is why this is the curve. So this is, and these properties are being given here. This equation, and one can see that this is the egalitarian line, and L0 is 0, L1 is 1, and this equation implies Lorentz curve is positive and it increases monotonically, and curve is convex to x-axis. So you can take its first derivative, this is positive, second derivative also it is positive, and then it is seen that this is the convex to the fx. And as long as inequality is present, every top quantile group receives more than its share of total income, and every quantile group that begins with the lowest income receives less than its share. Thus, the curve lies below the egalitarian line. And this is known as egalitarian line or the line of equal distribution. This can also be termed as a Lorentz curve in case of perfect equality. If there is a perfect equality, then this will be this equation line is LP is equal to P. This is its equation. So in case of perfect equality, Lorentz curve coincides with the egalitarian line. And now I am going to talk about, because Lorentz curve itself can be used, so many distributions can be, you can just find its distribution function also, and there are so many results, its property also, but I am focusing on the Lorentz dominance and the Lorentz ordering. So what is the meaning of Lorentz dominance? This is one of the most frequently used dominance criteria for judging differences in equality between income distributions. We say that income distribution for X Lawrence dominates a distribution for Y. So X is dominating Y in the Lawrence sense if and only if Lawrence curve of X is greater than equal to, it is above the Lawrence curve of Y. For all value of U, if it is being written U, the U is between 0 and 1. So this implies high, and it means if I have got two type, if you just look at these two, so you can have, this is the Lawrence curve for F, this is the Lawrence curve for G. So then we can just say that this dominates the Lawrence curve for G. So Lawrence curve of F dominates the Lawrence curve for G. So it means, so what is the meaning of, what is the advantage of doing this thing? So I can just say, so you can see, smaller the gap between the egalitarian line and the Lawrence curve, then we can just say, so there is a dominance in that distribution in the Lawrence sense. So we are just, it is not the stochastic dominance, but we are just saying dominance in the this much in the Lawrence sense. So it means there is less inequality in this distribution rather than distribution G, right? And this implies, and moreover, there is one more concept once we talk of inequality, that is a concept of the social welfare. This implies higher welfare for distribution X in the sense that other things being equal, less inequality is always preferred to more inequality. We refer to this condition as one where X dominates Y. So if X dominates Y in the Lawrence sense, then we say there is a also higher social welfare. And this social welfare concept is also important for any society. That is why they will like to see whether there is a Lawrence dominance or not. This is a simple concept, basic concept. So Lawrence are, but the thing is, we may not always get a perfect scenario like this, that we have got the one Lawrence curve of one distribution dominates another. So one can immediately say, okay, less inequality, but what happens once there is a crossing of the Lawrence curve, because they often cross also. So we say this is a partial order. Lawrence order is a partial ordering. Okay? So that is, in case the Lawrence curve cross, one cannot unambiguously say which distribution is preferred in terms of having less inequality. So here one can see that. So here, first of all, F distribution is dominating. Then you can just say, then G is dominating. So what is going to happen? So you can just say that we cannot say which distribution is overall having less inequality or which distribution should be preferred, right? So because of such scenarios, there are certain variants of the Lawrence curves which have emerged in literature. According to the certain specification or certain conditions, some other dominance relationships, they have become prevalent in literature. So I'm talking of some of these variants. An unambiguous criteria for unanimous preference of one distribution of another in such a case when two Lawrence curves coincide may be given by using generalized Lawrence curve, a variant of the Lawrence curve. Shorrock was the one who has proposed it in 1983 in Economica paper. And after that, this generalized Lawrence curve, this has also become a very powerful tool in income inequality. And in fact, many more such variants of Lawrence curves are possessed in literature. A generalized Lawrence curve is one such variant. And now, depending upon the situations, other variants are also there. Absolute Lawrence curve, it has got somehow relation with the Lawrence curve, but not exactly the same. Bonferroni curve and comic curve and associated inequality and inequality indices also. Once we talk of the curves, then there is a very famous, index also. With Lawrence curve, we talk of the Gini index. I think everyone is familiar with these concepts, but with the Gini index is there with the Lawrence curve, and with a generalized Lawrence curve and all that, we have got generalized Lawrence index, absolute Lawrence index, Bonferroni index, comic index, etc. They are also used in literature when standard Lawrence curve or Gini indices are not appropriate measures of inequality. So, a brief description of these variant curves I am going to explain. So what is a generalized Lawrence curve? Shorrock suggested generalized Lawrence curve as an alternative to Lawrence curve in case two Lawrence curve cross and the underlying distribution have different means. For the two Lawrence curves, they are crossing, as I have just given the situation. So to make it just to make an idea that which distribution is welfare superior or which distribution is having less inequality. So dominance of the generalized Lorentz curve is being suggested. And if we compare the generalized Lorentz curve for two distributions, one can unambiguously say, because in the Shorrock he has shown that in many scenarios when Lorentz curve intersect, it has been seen that the generalized Lorentz curve generally don't intersect. So in that cases, it was easy to interpret. So in figure, Lorentz cross plus generalized Lorentz curve do not cross. Here you can see the scenario which I have already shown, they were crossing, but here this is the figure of the generalized Lorentz curve, generalized for F, generalized for G. And how they are constructed, so they are nothing but, if you look mathematically, it will seem very simple. The generalized Lorentz curve is defined as mu times LP. It means you multiply it by mu, by the mean, because means we are not accounting for. So here he says in welfare it is being expressed that the distribution which has got the higher mean, they should be preferred. So to take into this criteria, the generalized Lorentz curve has been proposed. That is nothing but equal to, you can just say it x. If you use the term of f1x, then it is only fx, or in terms of p, I can write it mu fp, and p is equal to f. So it has also got certain properties. They are preferred to the Lorentz curve to rank the two distributions unambiguously, not only in case of two intersecting Lorentz curve, but also in case the dominating Lorentz curve has smaller mean. So there is another situation that, okay, what is happening? The Lorentz curves is f is less than the Lorentz curve of this, but mu of f is greater than this. Then what can we say? So if their means are equal, then there is no problem. Problem is mean of f is greater than this. So can you ignore this criteria? So to take account of this, generalized Lorentz curve, we unambiguously say, it has been proved that it has been seen that generalized Lorentz curve of f is superior than is dominating the Lorentz curve of G in such scenario, even if we have got the such type of scenario. So in case both are having the same mean, then they are identical. So here distribution F is preferred to G in both in the sense of having less inequality, higher social work. And generalized Lorentz ordering, we have the criteria of generalized Lorentz ordering. And because Lorentz dominance consider only the degree of inequality and not the level of income, and higher level of incomes are associated with higher level of welfare, another dominance relation known as is often considered. How we define it? So F dominates G in the generalized Lorentz sense. If this happens, generalized Lorentz curve of F is dominating this. Or equivalently, we can write it in terms of inverse function as such. This is a definition of the generalized Lorentz curve, which has been, so you multiply it by mu and you get this equation. The criteria of generalized Lorentz dominance is met if generalized Lorentz curve of one dominates another. Now we can also associate writing the relation for generalized Lorentz dominance in this way demonstrates its equivalence to second order stochastic dominance. So in literature, we can also call this generalized Lorentz ordering is equivalent to second order stochastic dominance, and a stronger condition for welfare improvement than second order, more stronger condition is the first order stochastic dominance. And distribution for X, first order stochastically dominates Y. It is being written as first order stochastic dominance if and only if F inverse of this. If we have the integral, then it becomes the second order. So what is the interpretation of this? In this case, the level of incomes from the distribution X is greater than the level of income from distribution Y for all population proportions. So if this is the case, then it is first order stochastic dominance, but second order stochastic dominance is equivalent to generalized, and this result is there in literature also. And Lorentz dominance and generalized Lorentz dominance are identical requirements for income distributions with equal means. Okay. Then there is another variant, that is Bonferroni curve. Bonferroni curve, that is also being defined as, so this is the mathematical derivation. Simply you can understand this is LP upon P. This is mu x upon mu. LP can also be written as P mu x upon mu. So this is, what is mu x? Mu x is being defined as equal to this much, which is actually the partial mean or the conditional mean of the people whose income is less than or equal to X. And these are the properties of the Bonferroni curve. So Bonferroni curve, so this is a shape of the Bonferroni curve. So it may not start always from the zero. And these are the some of the properties. We have also got one paper in probability and statistics later. There we have discussed about its properties also, and this is its derivative is increasing. It is strictly increasing, but nothing can be said about the sign of the second derivative. It could be convex in one part and concave in some parts. And egalitarian line is the one which connects the points 0, 1 and 1, 1. This is actually 0, 1 and 1, 1. This is the egalitarian line. And this area, this is known as a concentration area. So in Lorentz curve, if you look, I just go back and show you this area between Lorentz curve, and this is also known as a concentration area. Based on this concentration area, the various indices are defined. In fact, the Gini index is nothing but twice this concentration area, or we define it 1 minus the area under the Lorentz curve. So similarly, in case of Bonferroni also, we can define the various Bonferroni here also using this concentration. Bonferroni index is being defined, and the Bonferroni ordering, if I have to use, then is said to have less inequality than the distribution G in the Bonferroni sense, if and only if Bonferroni curve at P, this is greater than equal to, this dominates, of F dominates the Bonferroni curve of G. So Bonferroni, and it is interesting to note that Bonferroni ordering is same as the Lorentz ordering. This is, there is a paper by Pham and Turker, and it has been given. Actually, one can see that all these curves, they are not only applicable to the income setup, rather in reliability as well as in the survival. They are widely being used, right? But I am particularly taking as the inequality comes because they started with the inequality, but now they are widely being used in the survival as well as these, and also in terms of, you can just say, in the environmental studies to AQI, etc., and their interpretations there also, because one of my students, she has done the PhD using these concepts in the concept of the environment. Then she has environment with what is the AQIs, air quality indices, etc., and their distributions. And another which variant of the Lorentz curve I can point out, that is a cumulative mean income curve. Okay, this is another.
Madam, you have 4 minutes more. Thank
Only
you.
4 minutes, ma'am.
Yes, because 5 minutes for question answer at least.
Okay, then I think I will be only able to just explain all the orderings. Maybe
Thank you so much.
Okay, no problem. Okay, thank you, ma'am. So this is another alternative measure which is given by myself also, as well as Shaurak. Shaurak has suggested as a footnote, and then we have developed this curve. And this is defined as a conditional mean of income less than or equal to xi p, which is a pth income quartile. And this in comic is the mean income received by the poorest 100% of the income recipients when income received are arranged in ascending orders. And mathematically, I can just say this is the generalized Lorentz curve upon P. And if two Bonferroni curves intersect, comics can be used. So these are their interpretation. Once we have to use it, so it means this is their practical applicability. And these are some of the properties. I can skip and show you this curve also. This is the curve. And comic ordering can also be defined like this. So a distribution F is said to dominate G in the comic sense if comic for F, comic is cumulative mean income curve. The full name is if F lies everywhere above the comic for G. So this is the dominance for that. And in terms of income inequality, it may be interpreted that F will have less inequality than G in the comic sense. And then there is, in the literature, we can also have the absolute Lorentz curve. What is the absolute Lorentz curve? Because the concept of inequality is both absolute as well as the relative. So absolute Lorentz curve, this is actually given by this, or in short, I can just say mu of LP minus P mu. This is a Lorentz curve, or generalized Lorentz curve minus P mu. What is P mu? P mu is the absolute equality of the generalized Lorentz curve. This is the geometrically I can interpret. The absolute Lorentz ordinate is the vertical difference between the generalized Lorentz curve ordinates and its line of absolute equality P mu. So all these, they will go below. This is the line of equality, and they will lie always below the vertical line. These properties also, they are there, and this is the dominance you can see. So here F is having dominance in terms of this much. And similarly, we have also suggested one more curve, That is absolute partial mean curve. This is a mu x minus mu. This is a conditional mean, partial mean minus this. Mu x upon mu is Bonferroni curve. And then on the same lines, we have just pointed out this is equal to this much, right? And this is the partial mean and suggests the mean income poorest P% when income is received in ascending order. And these are the, this you can just see the form of this curve. And some results have been I have obtained for the power function distributions. So because I don't have much time, so I can just say this is the power function distribution. This is this, and some graphs for the Lorentz curves these are the Lorentz curve which have been derived, and then we have got certain results that how can, looking at its parameters, we can just see there is a Lorentz dominance or not. The parameters of the distribution are used to depict the Lorentz inequalities, as is obvious from these various theorems. However, the Lorentz ordering is independent of the scale parameter B, as dependent only on the shape parameter. And these are some of the graphs. The only thing I can just say, if there is, Madam, can I take 2 minutes?
Yes, ma'am.
Okay. So this is the one remark I want to say. In terms of welfare interpretation, both generalized Lorentz ordering and comic ordering have interpretation in terms of Rawlsian Laximian rather than equality neutrality approach, which seeks to improve the position of the least well-off income units regardless of all else. Once we talk of the income inequality, one is Rawlsian and what is the inequality neutrality. And these approaches have been given with the help of generalized Lorentz curve. And comic will behave like the same as the generalized Lorentz ordering. And inequality neutrality focuses on P is equal to one end of the scale. And Rawlsian Laximian on P is equal to zero end of the scale. And hence, if one wants to attach more importance to Rawlsian Laximian than in case of power function distribution, this should be the case. And this is the two Laximian which I can explain. Two generalized Lorentz curve are there. One is 0, one P is from 0 to 1. So if we focus on this, so we have to see, it means the least well off, the poorest person should be well off. It means the cake whose smallest slice is better, is more. If you just put a cake is taken, so if cake is higher or bigger or smaller does not matter. It says if the smallest slice is bigger than the other, then we can say that distribution is better. In this case, if the poor are more welfare, the Rawlsian Laximian. If I just say the cake which is better, it means the mean is better. In that case, we have the equality neutrality approach. And in this case, we can just say in case of power function, we have worked out that what can be the Rawlsian Laximian. And Rawlsian Laximian is directly related with the welfare interpretations. And once this generalized Lorentz curve cross also, there also we have got results in terms of the variance, that in terms of the variance of that should be smaller. That I have put in other slides. And just I sum up that Lorentz ordering is same as Bonferroni ordering and generalized Lorentz ordering is comic. And these are some of the results, but because time is less, I'm going to stop. So the same was observed in the inverse Weibull distribution as well. And these are some of the references. And then I just say thank you so much. Now I come back to the questions. You can please ask.
Thank you so much, Professor Arora, for such an interesting and very exhaustive kind of presentation. And you have covered many concepts. So now the floor is open for quick question, if any, because we are running short of time. So we can take.
I skipped so many results, ma'am, because.
Yes, I know. So you can just unmute yourself, the participants, and you can ask the question. If not, then I just have a curiosity, madam.
Yes, ma'am.
Yes, because you were talking about inequalities and the proportions, and like lesser the inequality and the higher the well-being of the people.
Yeah.
So can it be equally applied to the happiness inequality with respect to the income? Because I don't think they move in the same direction, the income and the happiness, or the anxiety level and the income. So how do you see the application of this into that kind of scenario? Just
only thing
curiosity.
is which intuitively I can feel the happiness index should be related with the social welfare as well, which I think the higher the social welfare, I think it should be the happiness index. But it is not in terms of, you can just say the money, the higher money. But if less inequality is there, I think that should be a good criteria for the happiness. But I don't know how the happiness criteria is to be defined. That is something, maybe something subjective. But overall, social welfare, if we just say more the social welfare and more happiness, if we define some index. But I don't know, because you may be into that field, you might have got some more exposure into
No, just a curiosity.
I can think, because social welfare, because all these the results which I have just given, so Lawrence, dominance, and all these, they have been related with the social welfare, and there is a utility function comes into picture. So utility function is the satisfaction level which we get. Maybe the satisfaction level is the same as the happiness we are having. If this is the way it can be combined, so I think one can associate, one can work into that direction.
Yes,
That's
yes.
a
So
good
I
suggestion.
think that can be
I will like to look
interesting.
into this. I will like to look into this.
Yes, yes. Thank you so much, madam. This was really very interesting talk. And I hope that all of us have been benefited by your presentation. So thank you very much.
Thank you so much, ma'am. Thank you so
Thank
much.
you.
Thank you, the
Thank you.
organization. Thank you so
So
much.
now is the time for the next talk. And because of the paucity of the time, we are just giving 30 minutes to the speakers for presentation, and the 5 minutes quick question answer session if anyone is having any. So it is my great pleasure to welcome Professor Indra Neil Ghosh, who is from University of North Carolina, Wilmington. And for me, it is a special pleasure because this time I was in UNCG, sir, last 2 semesters, but there I could not get opportunity to interact with you. So this is a pleasure for me to welcome you on this online platform. And Professor Ghosh is going to talk about some properties of stop-loss moments under biased sampling. So welcome, sir. This is your floor now. Thank you.
Thank you, Professor Mishra. And well, I have been to UNCG a couple of times for the annual conference, and Professor Sadgupta is very well known to me. I have seen you in the abstract and conference abstract, but never got a chance to meet with you. Well, virtually at least we meet. And hopefully in someday, I was supposed to be in India, but I had some things turn up that I could not be there. And also my sincere thanks to Professor Kumar. I've been associated with this conference for about 3 years, and I'm getting more used to this Google Meet. And okay, let me share my slides. Let's see how I.
In the bottom, there is a upward arrow. Yeah, you are trying to stop.
Sir, we have to stop the last presentation.
Yeah. Sir, Arora? Madam, please.
Oh, okay. Let me just.
Sir, I think there is some technical flaw. Professor Ghosh is not able to share his presentation.
Yeah, let me try with that one more time, and hopefully. Yeah, I'll.
Professor Sangeeta Arora?
I think she needs to stop sharing.
Yeah. She needs to stop sharing.
Yeah.
Professor Arora, if you are there, please stop presenting so that the speaker can share the slides. Please try, Professor Ghosh, see
Yes,
if it works.
let me try again and log into the system and try again.
Yes.
Okay, let me try. Sorry.
Still, we are getting this presenting screen. So, Professor Sangeeta Arora, can you please see that your sharing is stopped?
I will just do.
Yeah.
Okay,
Please.
thank you. Thank you so much.
So, okay, now it is fine.
Yes. Okay. Okay, Professor Ghosh. I think now it's fine. Professor Ghosh, are you there? Please try again, Professor Ghosh.
Probably due to the network issues.
Yes, I think he is in companion mode. I don't know what kind of mode it is.
Yeah.
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 Yeah. So I think he is trying from some other device also.
Let us try. Professor Ghosh.
Because his mic is not showing up. Is there any technical team who can help him?
Yeah. Let us try to, first of all, let us try to contact him.
Yes. Please contact him on phone or WhatsApp, whatever.
Yeah, he is there.
Professor Ghosh, whether it is possible for you to share the screen?
Yes.
You are working from Apple?
Professor Kumar, are you saying something?
Yeah.
I couldn't hear you. Can you please repeat?
Yeah. I'm asking Professor Indranil Ghosh whether there is any problem with I think his audio is not working well, probably.
Yes. So will he be able to present or not?
Or otherwise we can present from here and he will speak from there. That's better.
Okay.
If there is difficulty. Let us discuss.
Okay,
with
try this way.
Professor Ghosh, can you hear me?
Oh, he is not able to hear also.
Yeah. Professor Ghosh, please. Yeah.
Somehow it's my Google is somehow not giving me permission. I don't know why. It's supposed to.
Yeah, Professor.
But now you are audible, sir.
The same problem happened in case of Professor Ashokan from Newfoundland University just before. So it's better to send your slides to me.
Okay,
and
I will do that. Okay.
We can, or otherwise you can try once again, no problem. But it's better
Okay,
to.
let me quickly send you that. Sorry about this. So it's
so that we can.
yeah. And I'm gonna send you that.
Yeah.
So
I think you can present now.
Oh, okay. Let me see. Okay, saying that, well, can't share your screen. Okay. I try to go to the option, but I have sent Professor Kumar the presentation slides. Yeah, I guess it's the issue with the MacBook. Sometimes it's.
Yeah. I'm also using MacBook, but there is some problem with there is a permission, I think so.
Yeah,
it's. I mentioned that way. So that is sharing from here. Slides can be shared from here, and you can speak from there.
Okay,
Otherwise,
that's good.
While you are sharing this screen, the audio will cut off. This is what happened.
Oh, okay, okay.
And that is maybe in the companion mode or something like, I don't know what. Yeah. Earlier, my son Nikhil has tried to do something with Professor Ashokan, but okay, please send it. That's better.
Yeah, I
Did
have
you send
already sent it to you with the Gmail.
Okay, we're doing the CSK, that mail, or ICSTC, which mail, please?
Oh, okay. I think it's the ICSTC
Oh,
2000.
ICSTC. Okay,
Yeah.
okay.
Yeah, I have already sent that.
Got it. Okay, got it. Very good. Let
Okay.
us start from here.
Yeah. Okay, Professor, thank you so much. Thank you.
Now it's fine for you. I can make it. Yeah.
Yeah, if you can make this little larger.
Larger, yeah.
Okay.
Please.
Okay, once again, sorry about this technical fiasco. I wish I could solve it. All right, so thank you all for this talk that I'm going to present. So this is a joint work.
Don't worry, he will try it once again. Yeah, while making it bigger, it has gone that way. Please.
Oh, okay. Thank you. So this is a joint work with Dr. Vipin and Professor S.M. Sunoj, and I was introduced to this idea. So I have a very little contribution, to be honest with you all, and I'm still trying to get into this idea, which is quite fascinating to me. So this article has been published in Journal of Applied Statistics this April. So it is about some properties of stop-loss moments under bias sampling. And can you go to the next slide, please? So this is the outline of my talk. I'll briefly introduce to what is the stop-loss moment. There are a couple of mathematical definitions followed by it. There are some examples of weighted stop-loss moments and why the weight factor is important. Then there are several different concepts that floats around in statistical science, such as the hidden truncation or latent variable models, which is, is a whole list of literature that my advisor Barry Arnold has worked on it, and I have done some work on it. So that was my contribution as far as this project goes, is to include the concept of hidden truncation, one type of hidden truncation, and then of course followed by bivariate and conditional weighted stop-loss moments. And I'll also talk about some of the dependence measures that we discussed in the paper. Next slide, please. So the stop-loss moments are generally used as a summary measure for analyzing the data in which exceeds a certain specific thresholds. And such kind of analysis is quite useful in income modeling, in insurance studies. And what happens that, well, in real life scenario, a practitioner may not record the sampling units with equal probability. There could be several various legitimate reasons that one may think of. The selected sample units may appear with unequal probability, that is different weights. So then appropriate weighting factor has to be considered. And that's why in the stop-loss moments, there is we discussed at great length, or my two other contributors, they have talked in details about these weighted stop loss moments and from univariate domain to the bivariate domain. And in the, well, for the sake of brevity, I didn't include the simulation study and the real data application, but it was based on bias sampling. And we considered in the paper bias sampling due to two different scenarios, one with the one with the hidden truncation and one that could appear with a random negligence. Next slide, please. So here are some mathematical definition. If X is a non-negative random variable with a well-defined PDF, small f, and CDF, capital F, then the rth order univariate stop loss moment is given by that integral, which is the expected value of x minus t lower suffix plus. So it is sort of, as if it's truncating. So if we consider that it is defined over the entire region, positive part of the real line, 0 to infinity, it's considering only from t to infinity. Well, t is the threshold level that could either be supplied by the practitioner or it can be obtained from the data. It comes with experience, how we do choose. So that's about the rth order stop loss moment about it. And there are some, as I mentioned earlier, there are some different concept of weighted distribution that can be properly utilized in the construction of stop loss moment. So general weight function is, well, you could see a bunch of x's, I mean, with C1, C2, C3, C4, I mean, one x with bunch of constant, and with different choices of C1, C2, C3, C4, one could obtain probability weighted moments, MGFs, ordinary moments, order statistics, proportional reverse hazards, and so on. Now, in the case of a univariate stop loss weighted distribution, the weight could be considered as the pi of t, which is integral t to infinity x minus t fx dx, that is simply obtained by substituting r in the equation point 1. Next slide, please. So the random variable that is defined x minus t plus, that is, it is considered only if x is exceeding t, with sort of partial moments, are meaningful in the study of personal income. So if x represents the income of an individual and t is the tax exemption level, then this variable that is defined, x minus t plus, represents the taxable income. So income which falls short on tax exemption at level t will have no effect in the computation of taxes. And there are several scenarios in which these type of partial moments would be very useful. And there have been, I mean, well-established literature on these representation of these partial moments with respect to residual life in life length studies. There is a paper by Lin in 2003. In actuarial sciences, this random variable represents the financial loss incurred by an insurance company called risk. And in particular, I mean, well, we haven't explored it, but there could be, for an organization, there could be 3 different type of risk: operational, financial, and the other one, they call it like subjective risk. So you want to thwart different type of, like violations or fraud that goes into your system. Now, operational risk, financial risk, you have data, you have variables, you have values. Now, subjective risk, which is alternatively considered as strategic risk, there is no such readily available data. So a company management has to come up with a type of strategic risk that is, of course, is heavily dependent on operational and financial risk. Now, how would you quantify that? So in such cases, this type of partial order moments would be very useful. And there has been some work done in thwarting risk. And these days, with the banking frauds and all kinds of online fraud set up with these cryptocurrencies and bitcoins and all those, there is a greater to me, there is a greater role of this stop loss moments and identify the corresponding bias net, how efficient you are. So that is another part of the research that we plan to do. But in this paper, we talked about these stop loss moments, and rth degree stop loss transform of the risk is a standard measure of the dangerousness of X, as I was referring to. So it has a lot of application over there. Nair, with his co-authors in 2018, have carried out an extensive study on the bivariate stop loss transform, because in general it's not just the uniform, but you will have different components in bivariate, and it could well be integrated into multivariate setup. And there is an extensive work that is available in the literature by Sunoj and Vipin in 2017 and Nair et al. In 2018. So if you have any questions on this mathematical formulation strategy, I would definitely share your question and concern with the two of my co-authors, and they have better experience than me. All right, next slide, please. So this is the weighted stop loss moments. If X upper suffix W represents the non-negative univariate weighted random variable with an absolute continuous survival function given by that, then the weighted stop loss transform is given in equation 0.2. And one could obtain several useful structural properties of these weighted stop loss moments, such as we discussed in the paper. It uniquely determines the corresponding weighted distribution if it exists through that equation 0.3 rth order derivative with respect to t. It gets to that particular form on the right hand side of that equation. And if r equals to 0, then it represents the survival function. When t is equal to 0, it is the expected value of the weighted random variable. And this weighted stop loss moment is a convex function of t, and it is non-decreasing function in R. So they're all described in the paper. Now, in addition to that, some other reliability concept such as failure rate, mean residual life function, etc., and other properties can be restated, redefined in terms of the partial moments. And there is a paper by Shankar and Hayar in all kinds of these moments, stochastic ordering, and my previous speaker, Dr. Arora, have talked in great length about this. So I think she might get some interest from this article. And this makes the stop loss transform an important and unique tool in analyzing statistical data with the non-negative support. Next slide, please. So the weighted distribution serves a significant role in analysis of bias data. For example, in prevalence studies, some individuals often have less chances for belonging to the sample, and there could be several different reasons. And this can be regarded as a random deletion of particular values of time to event data. It could be simply due to keeping record not correctly, like recording bias. Now, when the chances for these eliminations are proportional to the length of cases, it becomes a length bias sampling. And motivated by this, these two authors, Vadivian and Hassemi in 2015, they introduced this mean residual weighted distribution given by this equation, where the mean residual life function is defined by expected value of the conditional expectation given x bigger than t. And it is not new to the literature. It has been well studied for many different distribution. And the weighted function is taken as expected value m of x, which is the cumulative residual entropy. Okay, so these are, the stop loss moments. With so many of these well defined, available concept in dependence studies, in survival studies, in ordering, can be considered as particular cases of weighted stop loss moments and corresponding distribution. Next slide, please. So if we consider that pi1t as pi t as the weight function to incorporate the bias involved in the observed sample, that's our assumption. The resulting weighted distribution is termed as the stop loss weighted distribution, SLWD in short. And it has an advantage that the former pi t induces the weight as the mean of the residual life x minus t beyond the threshold t without truncating the parent distribution, whereas the MRL weight induces the weight from the truncated distribution. And there could be, argument in favor of one or the other. A big question with the hidden truncation is that how do you guarantee that there has been a truncation in the data set? That's about a separate issue, but it's really important. Now we claim that, or we conjecture rather, that the investigator is more interested in analyzing a data which is biased due to some random truncation. Stop loss weight will be more appropriate. So in such a situation, SLWD will be more preferable compared to this usual MRL weight. Next slide, please. So there are a couple of results that have been mentioned in the paper. I'm going to just briefly mention about this. If f be an absolutely continuous distribution function of a non-negative random variable mean, a finite expectation, and the Gini index is g of x, then expected value of pi of x is mu times g of x. And following this lemma, the SLWD, stop loss weighted distribution, can be defined as follows, where the probability function, it should be y, is given by this equation, and pi of x, so that's the weight, fx divided by mu gx. So basically, it's the weight is expected value of pi of x. And this is called the SLWD for a random variable x. Next slide, please. So again, in terms of Gini's mean difference of the truncated random variable xt, and it is defined in Nair et al. In 2013 as well, that Gini's mean difference with this particular choice of the survival function is given by this equation in 0.6. And we have the following theorem. If x is a non-negative random variable with survival function f bar and the Gini index g of x, and let y denote the SLWD random variable with the survival function f bar of SL, then f bar of SL can be related to this original random variable with the following equation in 0.7. So these are very nice and interesting results that have been mentioned in the paper. Next slide, please. So for example, we consider in the hierarchy of Pareto distribution, because Pareto distribution has so much application in income modeling. And if anyone wants to know about Pareto distribution and its different variants, there is a book by Arnold on Pareto distribution. I think the second version came up in 2015. We consider a Pareto type 2 distribution with a scale parameter sigma and the index of inequality alpha. And this is the form of the density function. And one can easily compute mu of g of x with this equation 0.9. And interestingly enough, for Pareto distribution, moments exist if the inequality parameter has certain restrictions. So for rth order, this will exist if alpha is bigger than r. So in this case, it is only available if alpha is bigger than 1. Now, for practitioners, you might have a question that how do you guarantee that for a data set, alpha is bigger than 1? Well, that's indeed is a debatable issue. One thing could be you have the data, you estimate the parameters, and you go for the testing for alpha. And if alpha is bigger than 1, that hypothesis is accepted, then and only then this model can be considered as a reasonable model to proceed. Now, so the SLWD in case of distribution Pareto type 2 will have the form of equation given in 0.10. All right, next slide, please. So for weighted models, I mean, there are different type of concept like the distance that has been defined here. Now, in this case, in particular in actuarial studies, models are often compared by finding bounds for differences in probabilities. Now, this is questionable at times when tackling insurance problem, in which case the focus would be on the resulting premiums, in particular stop loss premiums. And this because small variations in the probabilities of events hardly influence the decision made by insurance management. And there have been a lot of studies like Denuit and his co-authors in 2006. And based on this, Garber in 1979 introduced this concept of stop loss distance, and which we have considered in the paper as well. And this is the definition is given as the difference of first order partial moments corresponding to the random variables. So you might consider other type of Euclidean distance. And I'm not sure if that has already been done in the literature or not, but my assumption is that, well, there might be some other type of distance measure that are defined based on this stop loss distance for weighted models. Next slide, please. So, and then there are some important stochastic ordering that are also mentioned in the study, such as given two random variables x1 and x2, x1 is said to precede the x2 in stop loss order if the stop loss moment of x1 is less or equal to the stop loss moment, partial moment for all t in the positive part of real line. And for the weighted random variables, well, it appears that x1 weighted version of the stop loss, or for SLWD models, x1 will precede in stochastic order with the x2 weighted version. It implies with the unweighted version. So if the weighted version has the property or satisfies the ordering property, then the unweighted version will also satisfy, if and only if this condition is given in equation 0.12. All right, next slide, please. Next slide, please. Okay, thank you. So another weighted distribution useful in literature when observed data represent a sample that are truncated with respect to some hidden covariates. So if you have two concomitant variables x and y, or several concomitant variables, what is the situation that you will observe x if and only if y is truncated below, above, or it is truncated both below and above? Now, in the paper, and this is what I have, that's only my contribution to this paper, is that I talked about a little bit about this. So we considered truncated from the above. And what happens that this type of truncation, when you observe x only if y bigger than small y, the resulting distribution of the variable, this conditional distribution, it belongs to the same parent family. So if I'm considering a bivariate Pareto distribution where the individuals are univariate Pareto, then if I consider the conditional distribution of x given y bigger than some c, then this distribution will also belong to the same Pareto family, albeit some computational aspect and different reparameterization. So this density can be considered as a weighted density. Well, the weights is given by the ratio of the two probabilities. The numerator is the conditional probability and the denominator is the unconditional probability for the truncated variable. And there is a lot of weighted distribution based on such type of truncation scenario that is studied by Gupta and Arnold. And there is a paper by Arnold in 2000 on hidden truncation models that discuss at great length about these different variants of hidden truncation and how it is related in modeling data, where there is a chance of truncation. All right, next slide, please. So in the context of life length studies, two component system always exhibit there will be a dependence among component lifetimes, and there are various notions and definitions of bivariate dependence that are used in the literatures. And I have mentioned a couple of references. Now, if x1, x2 is a two-component bivariate random vector with absolute continuous survival function, and assuming that the joint moments exist of order R and S, then Sankaran and Nair in 2004 introduced these R and Sth order of bivariate stop-loss transform, which is given in equation 0.14. And Sunaj and Vipin in 2017, they studied the conditional stop-loss transform of this particular form. Well, there is a lot of important aspect of this conditional stop-loss transform because of the data that we look at, even at real life context. You could see that there are a lot of scenarios in which case actually you are looking at the conditional data, which is truncated. For example, in admission studies, the admission committee, graduate admission committee, will look at only those student application who have a certain GRE score, or in our institution coming to the MS program, will only look at students who have got a necessary and sufficient condition that their score, mathematical science score or English or TOEFL score, is bigger than some threshold value. So there is a lot of importance in conditional stop-loss moments in the bivariate domain as well. Next slide, please.
Professor Ghosh, the time is almost up, and we can take 2 minutes more.
Okay. I will wrap it up, Professor Mishra. Yeah.
Thank you.
There are several of these stop-loss dependent measures that are defined in the bivariate domain with the positive quadrant dependent, negative quadrant dependent. So I'll skip for that. Okay, next slide, please. Okay, so these are a couple of, again, some definitions regarding the generalization of PSLD, positive or negative stop-loss dependence. And we have mentioned certain results, lemmas based on this. All right, next slide, please. Well, that's the, so in conclusion, well, we for the sake of time, I didn't include the real life data analysis and the simulation. So simulation was done based on absolutely continuous Rayleigh distribution, and the stop loss moments. In the simulation study as well and the real life application, we consider biasness due to random negligence and bias sampling due to hidden truncation. So that was studied in the paper, and it appears from our simulation study that the empirical estimator based on the stop-loss function is performing almost uniformly better than the other two empirical estimators that we considered in the paper. Now, what will happen with the other types of hidden truncation, for example, as particular weights, truncation from below or truncation from both above and below, that will be the subject matter for a different study. With that, I will wrap up my talk, and that's all I have, and a couple of references that are given at the end. Thank you for your attention. Thank you.
Thank you, Professor Ghosh. Despite of the time limitation and the technical glitches, you have very well presented your talk on some properties of stop-loss moments under bias sampling. Because of the paucity of the time, we may not be able to take up the questions at the moment, but those who are interested can just connect with the author, Professor Ghosh. And thank you very much. Both the speakers have been really wonderful. And I'm sorry not being able to take up the questions. And Professor Satish Kumar, we are really so delighted and happy and thankful to you for giving us the opportunity to be a part of this particular session. Thank you very much. Now over to Professor Satish Kumar.
Thank you, Professor Sheila Mishra, for chairing this session in a very nice way. And also Professor Sangeeta Arora and Professor Indranil Ghosh for their excellent talks. Thank you. Thank you.
Thank you, sir. Thank you.
Yeah, thank you. Thank you. Now let us move to the next session. In fact, we are running now in the right time. the next session, in fact, 7:50. Bhagyalakshmi?
Yes, sir.
Yeah. You please introduce the chair and please support her to manage the session.
Hello, everyone. Now we have the technical session 17 of ICSTC 2022, which is chaired by Dr. Shubha Nair. She is a faculty to the Department of Mathematics and Statistics in the HHMSPB NSS College for Women, Trivandrum. She obtained her PhD from the University of Kerala, MSc in Statistics from the Cochin University of Science and Technology, and MPhil from the Annamalai University. Her areas of interest are distribution theory and biostatistics. She was a rank holder for degree, post-graduation, and MPhil. Dr. Shubha is a lifetime member of Indian Society for Probability and Statistics, Kerala Statistical Association, and a member of the American Statistical Association, and a resource person and invited speaker in various seminars and conferences. Dr. Shubha has always been a source of inspiration and support in all our events, and it is with immense joy and honor that I welcome you, ma'am, to share the session. Without further ado, over to you, ma'am.
Thank you, Bhagyalakshmi, for the wonderful words. Good evening, everyone. So we are entering the technical session, which is the 8th keynote address of this conference. And we have with us Dr. Jaya Sadhagopan for handling the session. I'd just like to introduce her with the shortest possible number of words. Dr. Sadhagopan is actually the professor in the Department of Biostatistics and Epidemiology, as well as the Associate Dean for Faculty Affairs, Rutgers School of Public Health. Her areas of research are, she obtained her PhD in statistics from the University of Wisconsin, and her research focuses on statistical genetics or genomics with application in cancer epidemiology, tumor biology studies, etc. Actually, a few number of words are not enough to describe all the areas of the vast amount of work that she has done. But I would like to describe her as a very nice human being, a humble person, and a dear friend. I welcome you, Dr. Sadhagopan, to present the paper on statistical methods in evaluating gene exposure interactions. Over to you, ma'am. Yeah, ma'am. Okay.
Can you hear me?
Yes, we can. Yes, we can.
Yeah. Thank you. Yeah, let me share my screen. Are you able to see my screen?
Yes, ma'am. We can.
Thank you very much. First of all, thank you all for joining session today. I'm on the morning, so I also say a very good morning to all of you. And before I begin, I want to wish, let me remove this.
Ma'am, there is some connectivity issues, I think, ma'am, because we are not able to hear you.
Oh, okay. So let me stop sharing. Are you able to hear me now?
Yeah, we are, but I think the voice is breaking at times.
Oh, my connectivity says it's okay now.
Okay. Please try once.
I have all the bars.
Okay.
I have all the bars available.
Yeah. Please try again, ma'am. Maybe it'll work this time.
Yeah. Let me share the screen once again. Are you able to see my screen now?
Yes.
Okay. So before I begin, I want to say give a very big congratulations to Dr. Satish Kumar and his entire team from the University of Kerala for putting together yet another successful conference and for giving me the opportunity to present this work today. And thank you, Shubha, for your kind words. I'm going to present a collection of joint works with my colleague, Dr. Alexia Yasonos, who works at Memorial Sloan Kettering Cancer Center in New York City. Empirical studies, as well as research in medical studies, have shown that the benefits of a treatment may not be the same for all the patients, and that timing at which benefits are achieved are very different. Medical studies strive to always, or oftentimes, identify which medical treatments are going to be beneficial for patients. And as part of these studies, they have noted that the benefits may not be the same, and the timing at which benefits are achieved are going to be different. This is illustrated in these two Kaplan-Meier survival curves. These are from metastatic melanoma patients, where the outcome is progression-free survival. These data are obtained from a paper by Larkin and colleagues. And what these authors wanted to do was to determine, they looked at 3 different treatments. One treatment known as ipilimumab, given in the the progression-free survival is shown in the green curve in these 2 figures. I will tell you in a moment what these 2 figures are. A second treatment called nivolumab, shown by the pink curves, and a third treatment, which is a combination of N and I, which is shown by the black curves. By the way, if at any point you are unable to hear me, just let me know, please. And these authors looked at a total of 843 patients. They all have metastatic melanoma. And these patients were randomly assigned to 3 treatments, and their progression-free survival was examined by following these patients for several months. And there are 2 curves here because before they began the study, these authors also measured a biomarker known as the PDL1 gene and found which patients were positive for this biomarker under some laboratory conditions and which patients were negative for this biomarker. They found that 223 patients were positive for the biomarker and 620 patients were negative for this biomarker. And this Kaplan-Meier curve, survival curve shows the survival probabilities separately for the biomarker positive and the biomarker negative patients. And there are 2 messages that emanate from these figures. First, patients who have received treatment N or treatment N plus I have better survival than patients who have received treatment I, because the survival probabilities for the pink and the black curves are higher than the survival probability for the green curve. And the second message is that in biomarker negative group than the N curve in terms of survival probability. Whereas for biomarker positive patients, whether a patient receives N treatment or N plus I treatment, they perform better in terms of their survival probability. Also, what these authors found was that the timing of the treatment benefit is also very different. And the table here gives the median progression-free survival time. As we can see, N and N plus I patients have similar median free survival time for biomarker positive patients, whereas in biomarker negative patients, N plus I patients receiving N plus I treatment have a longer median survival time than patients receiving N or I treatment. And I treatment does the worst in all 3 cases, in both the biomarker cases. And the timing of the treatment is also different, benefit is also different. So early on, all the treatments have very similar progression-free survival. And later on, it kind of starts, it starts separating, the curve starts separating. Here, the I curve at 4 months already starts doing worse. A lot of patients have started dying and survival probability is very low. Whereas the N and I curve, they separate, but still they are very Whereas in the biomarker negative group, yes, all three treatments look very similar. And over time, we start seeing which treatment performs better or worse than the others. So in the medical literature or in the medical science, medical doctors are often interested in finding, how long after what time does these benefits start appearing? And after some time, which treatment is doing better than the other treatment? And is one group of patients, say biomarker negative patients, are they deriving better benefit due to any treatment than the biomarker positive patients? So that if one group of patients are getting better benefit, then they should be prioritized for getting those treatment. And the group that is not deriving the benefit, maybe they should be treated in a different way. So in order to make these kind of assessments, we need to define what is meant by a treatment benefit, number one. And number two, how are we going to statistically compare whether treatment benefit is better in one group than the other? So in order to assess these, let us look at some technical aspects of how we pursue this statistically. So we have a biomarker, which is, let's say, a binary value, negative, 0, and positive 1. And let's say we have an effect, exposure, or treatment, let's say, which is also a binary value. Of course, in the previous case, we have 3 different treatments. But for the statistical exposition, let us take a look at a binary value of a biomarker, binary value of treatment, unexposed or no treatment or a different treatment, and exposed or treated or some other treatment, treatment N plus I, or treatment I and treatment N, and so on. And at any given time, the treatment benefit can be written as follows. Let's say treatment benefit in carriers or people who are positive for a biomarker. The treatment benefit is nothing but a contrast. We all know in statistics how to write contrasts. It is a function of time, some function f of time, among those who are exposed or who are treated with a particular treatment, minus the same function at the same time t of those who are unexposed or treated with a completely different treatment. And all of this occurring in people who have biomarker positive or biomarker value 1, this treatment benefit in carriers. Similarly, we can write treatment benefit in non-carriers as a same function of the time at a particular time for people who are exposed minus people who are unexposed, or people who are treated with N, people who are treated with I, some treatment, other treatment. Everything measured for people who are biomarker negative, that is biomarker value 0. So different choices of F will give different measures of treatment benefit. So I can define my F has to be logarithm of hazard. I will get a particular treatment benefit. And you may say, I don't want F to be a logarithm of hazard. I want F to be survival. So then you will get a different treatment benefit. So you can choose what should be our function. And under that function, we can have our own measures of treatment benefit. And different choices of F thus gives different measures of treatment benefit. Now, we also want to know, is the treatment benefit different according to the biomarker status? Are people with biomarker positive value getting different treatment benefit than people who have biomarker negative value? And to measure this, it's also another contrast. In statistics, we can write a lot of these medical terms in the form of contrasts. The differential treatment benefit, that is how treatment benefit varies between or differs between biomarker positive versus biomarker negative group, we can write it as some function W of t, which is nothing but the difference between these two treatment benefits in carriers minus treatment benefit in non-carriers. And when there is no differential treatment benefit, that is people who are biomarker positive and people who are biomarker negative, they both receive the same treatment benefit. Then we can write Wt is equal to 0, H naught, Wt is equal to 0. That is the null hypothesis. Is everyone able to hear me?
Yes. We are able to.
Thank you. Yeah. So now, how are we going to measure these F and T, and how are we going to measure this W of T? If W of T is 0, we will say there is no differential treatment benefit. So how are we going to measure that? So we can look at some ways in which we pursue this in survival analysis. So when we have survival data, like we have patients followed up for several months, we know who died at what time, their biomarker status, what treatment they received. When we have data of this kind, we typically fit a proportional hazard regression model to time to event data. And what does proportional hazards regression model involve? It involves specifying a survival time, right? Survival at time T for patients who with certain value of biomarker and some value of the exposure or treatment, or simply written as S of T, is nothing but the probability that a person survives beyond a time T. Some random variable T exceeds some given value T, given the values of the biomarker and exposure. And associated with the survival time is a hazard function. H of T is nothing but the first derivative with respect to T of negative logarithm of the survival. And we write the proportional hazards model as H of T is some baseline hazard, H naught of T times this E raised to some value, which involves the additive effect of the biomarker, beta, plus some effect of the medication or the treatment or exposure, E. The effect is given by delta, plus B times E times theta. And this theta is referred to as the multiplicative interaction between B and E. When theta is 0, we say there is no multiplicative interaction. When theta is non-zero, there is a multiplicative interaction. So this is typically the setup we have in a survival analysis for survival data under the proportional hazards regression model. And with this setup, how can we write the differential treatment benefit W of T and so on? So the treatment benefit can be measured on different scales. Treatment benefit is done by this function. I go back a few slides. Treatment benefit is some function of T, right? And in carriers and in non-carriers. So that function F can be defined any way we want. Right? There is nothing stops from defining it in any way we want. So we define F of T as logarithm of the hazard, right? So then we can write W of T is treatment benefit in carriers using the F defined as logarithm of hazard minus treatment benefit in non-carriers. And we can write this for the sake of calling it measure 1. I refer to this W of T as W subscript 1 of T. And we can plug in this value in the F that I wrote in a couple of slides ago. And using the proportional hazards model, H of T as H naught of T times E raised to power B beta plus E delta plus B times E times theta. So if I plug in those values, I get W1 of T is nothing but theta. And so what is happening is if we define F as logarithm of hazard, the differential treatment benefit, which is the measure of how treatment benefits differs in people who have biomarker positive and treatment benefit in people who have biomarker negative. That differential treatment benefit is nothing but our multiplicative interaction theta. So testing H naught, there is no different treatment benefit, is exactly the same as testing H naught equal to 0. We know how to test parameters of a proportional hazards regression model using likelihood ratio tests. So this is very easy to test. Is there a differential treatment benefit? Sure. Test H naught, theta is equal to 0. And this does not depend upon time t. At any given time, it's the same value theta for measuring the differential treatment benefit. But under the proportional hazard, it depends upon the proportional hazards because that's how I got W1 of T equal to theta by plugging in proportional hazards regression model. If the proportional hazards assumption is true, then my W of T does not depend upon T because this theta is independent of T. Now, sometimes proportional hazard assumption may not hold, or more importantly,
The middle doctor may not be interested in looking for a hazard, logarithm of hazard. We don't walk into a doctor's office and ask, oh, is this medicine going to benefit me? We don't say, oh, what is my log hazard, doctor? That's not what we ask. We always ask the doctor, oh, will I survive? Will I live for another 1 year? What is my survival? We always ask the doctor, how long am I going to live? We don't, H of t is the derivative. We don't ask the doctor, what is the derivative of my survival with respect to time t, right? So, but for statisticians, hazard function is very easy to work with. We understand derivatives. But as a patient, we always talk about survival. So in that sense, we can start defining f of t in terms of survival. For example, if I define f of t in terms of logarithm of survival, we get a different measure, w of t, measured in terms of treatment benefit in people who have biomarker positive, treatment benefit defined in terms of log survival among biomarker positive cases, minus treatment benefit defined in terms of log survival among patients who are biomarker negative. And this is nothing but logarithm of some odds ratio, odds of survival in patients who have biomarker positive and odds of survival in patients who are biomarker negative. And we know as statisticians how to write odds ratios, but here the odds ratio is in terms of survival probability. Now, we also know as statisticians how to write survival probabilities. We can write S of t using Kaplan-Meier survival probabilities when there are no covariates available, because we can calculate Kaplan-Meier estimates of survival probabilities in each of these scenarios, biomarker positive, people who are exposed, or people who are treated with a particular treatment, biomarker positive people who are treated with a different treatment, and similarly for biomarker negative groups. We know how to calculate these Kaplan-Meier survival probabilities. Now, if other covariates are available, such as patient sex, their age, and so on, we can still fit a proportional hazards regression model, and we know how to calculate hazards, we know how to calculate survival probabilities, and we can plug in those values at some time t. But a hypothesis test for whether there is a differential treatment benefit under the scale H0, WT2 of t is 0. A hypothesis test is not available, but we derived a hypothesis test. It's not very difficult. I will not go through that process today, but it suffices to know that H0, W2 of t equal to 0 against a two-sided alternative, we can test that hypothesis. Now, if we do not know whether the proportional hazards assumption holds, if it does not hold, we can fit accelerated failure time model. If it holds, we know how to test for proportional hazards assumptions and so on. Now, suppose the proportional hazard assumption does hold, then S of t has some very nice properties, and so does W2 of t. W2 of t, the differential treatment benefit, can be written as logarithm of some baseline survival at time t multiplied by some quantity which does not depend upon t. Under the proportional hazards assumption, we can write it of this kind. Now, suppose theta is equal to 0, that is, there is no multiplicative interaction. Then this quantity will still be non-zero because it's e power beta plus delta minus e power beta minus e power delta plus 1. Now, when does this W of t equal to 0? When is H0 W2 of t equal to 0 hold? When theta equal to 0. When theta equal to 0, W2 of t is 0 only when beta or delta tends to 0. That is when there is a very small biomarker effect or there is very small treatment effect. So when there is very small biomarker effect, that means the two biomarker groups are very identical. When there is very small treatment effect, it doesn't matter whether you are a biomarker positive or biomarker negative group. There is simply no treatment effect. Only when this happens, the treatment benefit in the two groups will be identical, only when this happens. Otherwise, even when delta equal to 0, even when theta equal to 0, the two groups will have very different treatment benefits. So what this slide says is, Suppose there is no treatment benefit under the first measure, under the log hazards measure, that is when theta equal to 0. That does not mean WT equal to 0. Theta can be 0, but we can still have W2 of T to be non-zero, because when theta equal to 0, W2 of T is only 0 when beta is 0 or when delta is 0. Now let's take a look at a third measure. This is a measure as a patient or as a doctor they are most interested in. F of T is indeed the survival probability, because the doctor wants to know, is the survival better due to treatment versus non-treatment in biomarker positive groups? Is the survival better due to treatment versus non-treatment in the biomarker negative groups? And is the gain in survival the same in biomarker positive group versus the biomarker negative group? So doctor always wants to know, will my patient survive? And the patient wants to know, am I going to survive? The patient's family wants to know, is my family member going to survive because of this treatment? So survival is a measure that is most preferred or most thought of during a patient-doctor conversation. As a result, defining F in terms of survival probability is quite attractive. And we can test H0 W3 is 0 against HA W3 is not equal to 0. We can derive a hypothesis test for this. Now, suppose under still have, even when theta equal to 0, this W3 of T need not be 0. That is, even when there is no, even when the treatment benefit is the same in the two biomarker groups under measure 1, that is no multiplicative interaction, we can still have W3 of T to be non-zero. As before, W3 of T is 0 only when beta that is 0. That is, there is very limited biomarker effect or negligible biomarker effect, or delta tends to 0. That is, there is negligible treatment effect. So once again, there can be no differential treatment benefit under one scale, that is under the log hazard scale, but we can still see a differential treatment benefit under the survival scale. So once again, the message of so far is that the definition and the interpretation of treatment benefit depends upon the choice of F. F is log hazard. The differential treatment benefit is theta equal to 0. F is log survival. It's a different quantity. W of T is a different quantity. F is survival. W of T is yet again a different quantity. And the null hypothesis of no differential treatment benefit on scale is very different from null hypothesis of no differential treatment benefit on a different scale of F. Therefore, oftentimes statisticians, we test whether an interaction is 0. And when there is a theta is 0, then we say there is no multiplicative interaction. Theta is not 0, we say there is a multiplicative interaction. That means the effect of biomarker and the effect of treatment depends upon the value of the biomarker. But the lack of interaction does not mean there is no differential treatment benefit under a different scale. And let us take a look at the melanoma example. So I calculated the differential treatment benefit under the log hazard ratio scale, that is H0 equal to 0, by fitting a proportional hazards regression model. And I also calculated no differential treatment benefit on the log survival scale and on the survival scale. But these two scales depend upon the time t. We have to calculate differential treatment benefit at a particular time. And what time do I calculate it at? I chose to calculate it at a time 5.3 months, which is the month at which all 843 patients, if we look at them together, 50% of the patients survived up to 5.3 months. So I calculated it at that value. And test H0, is there a differential treatment benefit? And these are the p-values. None of the p-values are less than, let's say, a type 1 error of 5%, 0.05. Therefore, we say the effect of the treatment is not, even though these curves look very different, they're statistically not very different, we can say. That is, treatment benefit of Nivo N plus I is no better than treatment benefit of N in both the biomarkers, right? So even though the black and pink lines are very close here and they are very different here, statistically they are not different. They are one and the same. So that is the conclusion for this particular data set. But nonetheless, medical doctors will say, well, there is gain by on survival months in the biomarker negative group, whereas there is very limited gain in survival for the biomarker positive group. Now, so the message for the melanoma data is that the treatment benefit is the same for biomarker positive and biomarker negative patients, because we can make that conclusion by looking at the p-values. Now, also said treatment benefit in one scale does not mean no treatment benefit in one scale does not mean no differential treatment benefit in another scale. So to assess that, we conducted a few simulation studies. So first we conducted a simulation study by simulating data using the proportional hazards model. And this model, there is no differential treatment benefit because the theta value is 0 here. There is no beta times E B times E times theta here. That is, theta is 0. So H0 W1 of t equal to 0 holds. And we simulated H0 of t using a Weibull model. We simulated 500 patients. And patients were randomized to 2 different treatments. And we set 25% of treatments to have biomarker positive and the remaining 75% to have biomarker negative, and set 25% censoring, independent censoring. We set type 1 error of 10% and simulated 1,000 data sets. We fitted each data set using a proportional hazards model with an additional value beta times E times theta. And we tested H0 theta equal to 0. And we tested H0 similarly W1 of t equal to 0, which means in the first measure, W1 of t is equal to theta. And we also tested H0 W2 of t equal to 0 and H0 W3 of t equal to 0. So under this setup, W1 of t must be 0. And we must have W2 of t to be non-zero and W3 of t to also be non-zero, because differential treatment benefit, lack of it in one scale does not mean there is a lack of differential treatment benefit on other scales. And we tested how often we reject H0 W1 of t equal to 0, and how often we reject H0 W2 of t equal to 0, and how often we reject H0 W3 of t equal to 0. And of course, W2 and W3 will depend upon the time t. And I chose time t to be the time at which 75% of the subjects are alive. We did the same thing where 50% of the subjects are alive, 25% of subjects are alive, and so on. So what we found is very much that aligns with what I said earlier. Of course, we reject H0 W1 of t very less times, which is very close to the type 1 error. And we will reject H0 W2 of t equal to 0, H0 W3 of t equal to 0 very often, because lack of differential treatment benefit on the hazard ratio scale, hazard scale, does not mean there is a lack of differential treatment benefit on log survival or survival scale. And I said there is lack of differential treatment benefit. W2 is 0 and W3 is 0 only when there is no biomarker effect or when there is no treatment effect. Right? So when there is no biomarker effect, we simulated data using these parameters. Of course, we reject all these H0 W of t equal to 0 under all measures, very close to 10%, which is our type 1 error. And we also simulated data by forcing no treatment benefit under the log survival and on the survival scale. And to do that, we fitted a model, we simulated model using the additive hazard function. And we set this additive hazard function shown here, where log uniform means uniform 0, 1 variable. We set a value in the denominator to get 10% survival probability at some time. And once again, we simulated 1,000 data sets with 500, n equal to 500. And for each simulated data set, we set beta and delta to be different values as shown here in this table. And under certain values of beta and delta and theta, we must reject very often under some scales, but not on other scales, and so on. So when theta equal to 0, H naught theta equal to 0 means there is no multiplicative interaction on the proportional hazards function. That is, there is no differential treatment benefit in the proportional hazard model. But this is not a proportional hazards model, it's an additive hazard model. Therefore, when theta equal to 0, H naught W1 of will be non-zero. And that is what we find we reject very often. And H naught W2 of T, I am 10%, and H naught W3 of T is also going to be rejected very less, and that's what we see, although it's higher than 10%, and that is how we have set up our model. And once again, when theta equal to 0, only when the biomarker effect is very small or the treatment effect is very small. So here I set the biomarker effect to be very small, then H naught W of T is 0 under all the scales, and that's what we find here. We reject very close to the type 1 error of 10%. And once again, we set up different, when we set biomarker value to be small and treatment value to be not, treatment effect to be not small, or the interaction effect to be not small. This is a setup where theoretically H naught W3 of T equal to 0. And that's what we see here. We reject it 9% of the time, which is close to our type 1 error that I showed previously of 10%. So what these simulations show is that H naught W of T equal to 0. That is what doctors want to know. Is there treatment benefit in one biomarker group versus treatment benefit in a different biomarker group? Are they going to be different? Is treatment benefit better for some patients versus for other patients? Medical doctors are always interested in finding this. And what this simulations and what the work that we have shown so far illustrates is that we have to upfront say what is the scale on which we are measuring. Are we interested in looking at log scale, log survival scale, or survival scale? Or maybe there is a different scale in which you want to measure treatment benefit. The scale on which we want to measure treatment benefit is key. And that is the scale. And under different scales, we have different measures of treatment benefit, and we will have different conclusions for H naught W of T equal to 0. So is there treatment benefit? Is there differential treatment benefit? The first question has to be, what scale on which are we measuring? Do we want to talk about hazard, or do we want to talk about survival, or anything else? So in summary, the definition of interaction, that is the definition of differential treatment benefit, depends upon the scale under which our contrasts are measured. And we can always find a scale under which there exists differential treatment benefit, subject to enough sample size availability, of course. And medical doctors always find survival probabilities to be very useful in a conversation with patients. And they always want to know, is my patient going to survive? They are not talking about, is my patient's slope or the rate at which they survive different? They want to know, is this patient going to survive? So as a result, survival probability scale is attractive. But on the survival probability scale, it also always depends upon the time. And the sample size also plays a very big role. So what about the effect of sample size, and at what time, S of T, at what time should the medical doctor think about calculating differential treatment benefits? So this is a work in progress. We are exploring these questions using the restricted mean survival time. And I only talked about one biomarker. These days, we look at many different genome-wide biomarkers. So how are we going to measure differential treatment benefit when we have many, many biomarkers? And this is also a work in progress. We are pursuing a lot of statistical learning techniques on how to define biomarker using certain genetic scores. So I will leave. I want to say thank you for your time. It's very late in the evening for you, dinner time. And I'm very grateful for your presence today to hear this talk. So I will wrap up here. I have to figure out how to stop my screen. Here. I stop sharing my screen. I open up to questions or comments.
Thank you, Dr. Sadagopan, for the very informative session. The floor is open for questions now. I request the participants to please interact with Dr. Sadagopan. We have got 5 minutes.
Dr. Sadagopan, that was wonderful. Let me ask, is there any advantage of trying to model the form of the interactions that occurs?
Thank you, Dr. Banks. Nice to see you. I know it's early in the morning for you in Duke University. Trying to model the form of interaction, that is like model H0, that the theta parameter. There are different ways people have been exploring. If there are meta information, external information about the genes of interest, people would use that to model that. People also have been exploring. There is a lot of work by Frank Harrell and colleagues on trying to model that using spline functions and so on. So there is a lot of scope available on trying to further expand these simple H0 W of t equal to 0 can be pursued in a more functional forms. There are people there is precedence by Frank Harrell's team, and more newer people are also modeling it in different ways. So there definitely is a lot of scope for that.
Thank you.
Thank you for that question.
Anyone else? Doctor, can I ask you a small doubt? You were saying that the effect of sample size, which on such studies, have you identified the minimum sample size that will give a significant result?
Well, I'm not sure that we can come up with one number of a minimal sample size. It always depends upon the effect we want to detect. So in terms of power calculation, we know it depends upon the type 1 error we set, effect we want to detect. However, when we want to measure treatment benefit or differential treatment benefit on a survival probability scale, so at what time do we measure that treatment benefit, right? And we know with survival, patients are dying at different times. And the further we go, when patients have taken the medications for a long time, and we want to know after a long time, is their survival. But the further we go, that is also the time when many patients have died. So early on, a lot of them are alive, and we are losing samples as we move forward. So that's it's not a whole entire sample size. It's also a time. When is a good time to know that enough time has passed that we have to measure? They should have benefited by now. So that's a tricky part. I have not figured out. It's not that as a statistician, I cannot work alone as a statistician, because that input also has to be very interdisciplinary. And guidance also provided by the clinician, because they are ultimately the users. So I'm working closely with a team of clinicians, but it's a very difficult, a challenging question to navigate. I have not come up with a solution, if I can use the word for that. But that's a very pivotal question, nonetheless.
Thank you, Doctor. Anyone else? So I think we can conclude the session. Satish sir, shall we?
Yeah. Thank you. Thank you so much, Professor Jaya, for your excellent talk. We all enjoyed the talk, and we are grateful to you, Professor Jaya, for your wonderful presentation. And we are in fact long back we are associated with these conferences and other with the Professor Jaya from the beginning onwards. In fact, we have started, and now we are in the move to start a MOU with the University of Darkes and University of Kerala. And we are getting very much grateful to you, Professor, for your support. So,
Thank you. And once again, congratulations for yet another conference.
Thank you. Thank you.
Yeah, thank you.
Also, thank you so much, Dr. Shua, for nicely chairing the session.
Thank you, sir.
Now, let us move to the next session. Professor David Banks. Hi, Professor. Yeah, hi. We are waiting for, everyone are waiting for your deliberations. I think, Teresa, please introduce the chair briefly and support him for the smooth conduct of this session. Teresa. Is it?
Should I start anyway?
Anjana?
Yes, sir.
Yeah, please introduce briefly our chair and support him for the smooth conduct of this session. This night, the right time. Please do not waste time.
Of course, sir. Hello, everyone. So we are moving on to the technical session 18 of ICSTC 2022, which will be chaired by Professor Hira Elkol from Michigan State University. Now, Professor Cole is well known in the statistics community all over the world through his research contributions, especially in the areas of inference on stochastic processes, efficient and adaptive estimation, reliability theory, semi-parametric and non-parametric inferences, and so on, and his active involvement in the editorial boards of highly reputed journals. And we are really lucky to have you with us, sir, chairing the session today. So without delaying you any further, I once again extend a warm welcome to you on behalf of the organizing committee and kindly request you to take over the session. Over to you, sir.
Thank you. Yeah. Hello, David.
Hi, Hira. How are you?
Good to see you here. And I'm supposed to introduce, just a brief introduction. Professor David Banks is a world-renowned scholar. His honors include being a past president of the Classification Society and of International Society for Business and Industrial Statistics, being a fellow of the American Institute Association, of the Institute of Mathematical Statistics, and of the American Association of Advanced Sciences. His research areas include models for computational advertising, dynamic text networks, adversarial risk analysis, human rights statistics, agent-based mode forensics, and certain topics in high-dimensional data analysis. I recall meeting David first time in 2005 when we had a big meeting arranged by Professor C.R. Rao, and there was a big gathering, and that time President Abdul Kalam was supposed to come in person, but because of tsunami, he did not. He had to give us a teletalk for half an hour, 45 minutes. And recall, David was one of the first ones to ask him some very interesting questions. So, and ever since every time I'm meeting David, I enjoy meeting him. And without further ado, please take over your talk. You're welcome to start your lecture, please.
Thank you so much. Can you see my screen?
So far, I cannot see it, but maybe others.
Okay, let me try to figure out how to do this.
It is visible, sir.
Yeah.
Please open the PDF file, Professor. That.
Yeah.
It says I am presenting.
Yeah.
Redo
Yeah,
it. Yeah.
it's fine.
Oh,
It's
there we
fine.
go. Now we
You
can
can see
see.
that?
Yeah.
Excellent. Okay, let me make it full screen.
Yeah, excellent, Professor. Yeah.
Okay, great. I want to talk about what I think is the future for us in the modern world of industry, because industry is changing rapidly, and I think statisticians need to adapt. We need a new vision. During the course of my professional life, I have seen probably 2.5 sort of theoretical breakthroughs. There was the bootstrap. There was Markov chain Monte Carlo. The half revolution was in the early 2000s when several different people, David Donahoe, Martin Wainwright, Terence Tao, Emmanuel Candes, worked on the case where you have large numbers of explanatory variables, but only a small sample size. Those were the theoretical breakthroughs that I think have marked the last 40 years. But I don't think we're going to see anything like that going forward. Instead, I think we're going to see something that I call data engineering, not data science. If you're using statistics to determine whether or not there's really a Higgs boson out there, or to decide whether or not there's an extrasolar planet, then you are doing what I would call data science. But if instead you're taking a lot of data and using a whole batch of really good algorithms to try to help Uber pre-position its drivers 1% better, then you're doing what I call data engineering. There are no theorems involved in that. You're not doing mathematical research. Instead, you're using the tools you have to try and produce a better product. And so every single application is going to require a hand-fit solution, and there's not going to be a whole lot of general theory. And that data engineering is creating new businesses and new services. It is essential to things like Google Maps. It's essential to ride-sharing services. It's essential to recommender systems. TikTok, Vivino, YouTube, insurance, almost everything that Amazon does relies upon data engineering. And let me pause for a moment. Satish, you've been so kind to invite me to speak. Let me confirm with you that you're able to see my screen and what I'm saying makes sense.
Yeah, Professor, it's visible and fine, Professor.
Great. I'm not sure. Do you have Uber in India?
We have it. We have it, sir.
Wonderful. Okay, so I'm communicating. That is very reassuring. All right. I think that information technology is the future of industry, and it's a target-rich environment for statisticians. There are a whole batch of new challenges that have arisen. I can only have time to speak about 2 of them, so I'm going to talk about computational advertising and autonomous vehicles. But there are other major areas where we can contribute, and that includes operations management, optimal control of manufacturing processes, a lot of the finance industries, fintech, all that stuff. Those are all areas where our students are going, and we want to make sure that we have the appropriate impact there. So first, I'm going to talk about computational advertising. Right now, it's a $309 billion industry. The interaction of ad buys, auctions, all the clients involved in this is complicated, and it has to be done in auditable ways. Computational advertising relies upon Ed Deming's old tools of experimental design, process control, and sampling, but it also engages with new areas of statistics, such as causal inference, predictive inference, spatiotemporal modeling, and networks. For causal inference, a company wants to know whether or not its ad campaign has led to a lift in product sales. That's a causal inference problem. You want to make a prediction about whether or not a user is going to click on an ad that you display to them. That's predictive inference. Spatiotemporal modeling has to do with when and where you should show a certain ad, and networks have to do with the timing at which an ad is displayed. Because people navigate subnetworks, you want to know when to try and connect with them. Computational advertising poses new and important problems, especially in connection with recommender systems, which we'll talk about in a moment. And these have wide implications for many other fields. And I think statisticians can make huge contributions in this area. So, ad markets. Computational advertising is projected to be valued at $982 billion by 2025. And it is the dominant revenue stream for, lots and lots of companies. One component of computational advertising, and it's perhaps a small component, is online ad clicks. There are many other types, but let's imagine that you type the word pizza into your browser. That's going to trigger an auction that takes place among many different pizza providers. So Domino's, Papa John's, Pizza Hut will all bid to display their advertisement to you. And the highest qualified bids are displayed, with the highest bidder getting the top position. But the process is actually very complicated. Here is a schematic that shows sort of how things work. And I apologize for the layout. It's not easy to read, but let me walk you all through what is sort of a...
Excuse me, David, maybe you can zoom it?
Zoom it?
Yeah. I don't know. Maybe too crowded. Okay, never mind. That'll be too time consuming. Never mind.
Okay. Is this presenting in full screen mode?
Yes.
Okay.
Yeah.
Okay.
It is in full screen, Professor.
Yes. Let me walk you all through this schematic. As you see, you have various lines and arrows, 1, 2, 3, 4. What's going on is, in step 1, a person's browser contacts the publisher's website. So I might go to CNN.com, and that's the contact. The publisher's website sends back contact that includes placements that will need to be filled through an ad server. Now, my browser will contact the publisher's ad server to fulfill placements that were not going to go up for auction. Perhaps CNN has an advertisement for itself, and so it will always publish that ad. So some of the spots on the screen are reserved for CNN. And if I have an ad blocker, then I'm not going to see that. So the publisher's ad server, CNN, sends back predefined content. But there are other placements that are available. And for those, that real estate on my screen, the browser is going to contact an exchange with placement invocation indicating where ads can be put and how many such ads can be placed. So if a placement is marked for real-time bidding, then an auction is set up by the exchange. And once the auction is initiated, the demand-side platforms are simultaneously contacted to participate in the auction. So the demand-side platforms would be things like Papa John's Pizza, Domino's Pizza, Little Caesars Pizza. They all run in parallel. And if Domino's Pizza decides to make a bid on the real estate on my screen, it will send its bid offer and a director tag to the auction. The auction takes place, and the winning bid or bids are sent to the exchange. The exchange returns to the demand-side platform a wrapped ad tag that contains everything that's needed to track the bid, the impression, and the log joins. And it's essentially a link to the director so that one can obtain user information and pass back the actual content of the ad tag. The browser will then contact the demand-side platform's director to obtain the ad server tag, which is a link to the advertising agency of the company or companies that won the bid. the browser receives the ad server tag, and it uses that tag to contact the advertiser's ad server requesting the content. The advertiser's ad server returns all the impression assets and the creative content back to the browser. And nearly all the time, we now have a third party that verifies that the contact has been made and that the impression has been shown. And so at step 15, we contact that third party. That third party tracker sends back a pixel as a verification to guarantee that it's in the loop on things. The ad tag that was sent in number 10 contains the JavaScript that the browser will load when the impression renders. And these signals are passed back only after the creative content is loaded. And that happens very late in this chain of connection. The demand side platform sends back a verification. And if the demand side platform's tracking pixel fires, this information is sent from the browser. And so that 19-step sequence of handshakes takes place in 10 milliseconds. And that leads to all the advertisements that are shown on your screen when you log in. And what I have described is an oversimplification, and it's like 3 years old. So the universe for computational advertising has changed. A rough sketch of what actually goes on. One example of the way in which this is a rough sketch is that it used to be that all of these auctions that I referred to were second price auctions. But now the universe has moved towards first price auctions. And so nearly all of these are going to be first price auctions. And I want to emphasize, computational advertising touches on many, many aspects of statistics. Important topics include design of experiments, causal inference, recommender systems, predictive inference, and time series modeling. But sort of with more novelty, computational advertising can also engage with text and sentiment analysis, dynamic network analysis, probabilistic ad contracting, spatiotemporal processes. You've got sensor data and everything else that you can imagine going on. In the fall, I'm going to be teaching a graduate course on computational advertising, and I'm going to be covering all of these topics in the context of that application. And this is a marvelous opportunity for academic research. I have PhD students who are now working at Google and Amazon and LinkedIn and places like that. And they tell me that they put out fires. They don't have time to develop principled solutions to general problems. Instead, they just work on one problem, get a Band-Aid on it, and move on to the next problem. Additionally, they are not encouraged to publish their work. That gives away a competitive advantage that Google might have compared to Yahoo. And so Google doesn't want them to publish. That means that academic researchers have an open field to contribute. I am particularly interested in recommender systems. They are the workhorses of computational advertising. They help advertisers decide which ads to show to whom. They are also involved in many other things. If you go to Amazon, Amazon will recommend movies that you can watch. They'll recommend books to you, music. You go to OkCupid, people will, and OkCupid will recommend people that you should go on a date with. And so recommender systems are all over the place. And a key aspect is that this is data engineering, not data science. Each application requires a specific solution. Recommending historical fiction is different from recommending murder mysteries. And they have some of the same ideas, but each one of those requires a specialized, tuned solution. And so this is sort of where I think data engineering arises. So a research challenge is to find methods that can actually do that fine tuning in a semi-automatic way. there are two basic starting points for recommender systems. You can do collaborative filtering and you can do content-based filtering. And both approaches start with a really sparse matrix R. And the rows are users, the columns are items, and the sparse entries in that matrix are the ratings that a user has assigned to an item. And the problem is much more general than that. The rating matrix might not be ratings. It could be how much time you spent looking at a book or an ad. It could be it could be a 1 to 5 rating. It could be a 1 to 7 rating. There are lots of things it could be. But to make a recommendation for the ith user, collaborative filtering looks to find other users whose tastes are like those of the ith user, and then it makes recommendations based on what the other people like the ith user liked. In contrast, content-based filtering makes recommendations based on features of the item. So the 3 steps of content-based filtering are to extract the features of an item. Is this an action movie? Is this a drama? Is this a comedy? Is it directed by Hitchcock? Does it star, Matthew McConaughey? So it extracts those features. Then it learns what the ith user likes. Does the ith user like comedies? Does the ith user like Matthew McConaughey? And then, based on that information, it recommends items which fit the user's preferences. So those are the 2 starting point strategies for recommender systems. But all of these are modified. You have hybrid systems that try and combine elements of both, as well as other information. But something that's coming in the future is going to be active recommender systems. Right now, there are not many of these out there. But if you ask a human being to make a suggestion about a movie or a book, that human being immediately comes back and say, well, what types of movies do you like? Do you like Bruce Willis? Do you like action films? And there's a conversation that takes place. And based on that conversation, your friend recommends a movie to you. And I can imagine that one day I will log into Amazon and Amazon will say, David, no matter what, we're going to recommend books to you. But if you let us ask you 5 questions, we'll do a much better job of recommending books that you will actually enjoy. And so that's like playing the game of 20 questions, but Amazon has a prior distribution over me purchasing any item that it has on offer. There are complexity constraints, and we're going to have some non-standard feature selection. And all of this is going to require building a proximity matrix for books or movies that says which books are near each other in David Banks's personal space for books. And I don't know if people have been following the new ChatGPT, but that's technology that could be totally transformative in the context of having these kinds of conversations. So Amazon has a prior probability for me buying any book that it has on offer. And the model for nearness should be complex and personally tailored because some people follow specific authors, others follow specific genres, others follow recommendations in the New York Times Book Review. So that model for nearness is probably going to be non-Euclidean, and that implies that we might use isomap or paramap or some other statistical procedure to determine what the space looks like. So the next step is for Amazon to learn what it needs to ask. And unfortunately, the optimal questions might be something like, on the whole, does David Banks like these 100 books more than he likes these other 150 books? And I do not have the ability to cognitively process that question. So there needs to be a complexity penalty on the questions that are asked. Does David like science fiction books written by female authors that involve hard science fiction? That's about as complicated a question as a person can work with. And so that represents a a regularization threshold that needs to be imposed on what is asked. An additional level of complexity is that ideally the questions that should be asked are ones for which Amazon's prior gives me a 50-50 chance of saying yes or no. That will ensure that Amazon learns at the most rapid possible rate about my tastes. But there could be a problem there. It may be that the first question Amazon asks has a good 50-50 split, but the next 4 questions all have 90-10 splits. So Amazon might learn quickly at the first question, but slowly at the next 4. So to optimize, instead of asking that 50-50 question as the first question, maybe Amazon should ask a 60-40 question if there are a lot of 60-40 questions underneath that would be better. And so this is a general class of problems. I am not aware of any previous literature that addresses such cases, but optimal learning under complexity, memory, and computational constraints is an interesting area of study, and I think the statisticians would have a lot to contribute to that. I want to switch gears. I know I have little time left, but I think another area that is terribly important for statisticians to get involved with are autonomous vehicles. And if autonomous vehicles are networked, the fuel and safety benefits are especially valuable. This would revolutionize how goods are used. This would revolutionize how goods are moved, and it will have significant impacts on the insurance industry, just-in-time manufacture, logistics, all sorts of things. Autonomous vehicles will create new businesses, and it will enable multimodal transportation in a way that will reduce pollution, improve safety, solve congestions, and improve our lives. Here are some facts. The U.S. Department of Transportation said Americans drove 3.4 trillion miles in 2018. The risk of dying in a vehicle are 1 in 77. That compares to deaths by guns in the U.S., which is 1 in 77, dying by a fall, 1 in 83, suicide, 1 in 63, heart disease, 1 in 4, and alcohol and drug abuse, 1 in 34. That's from the Centers for Disease Control. The work time or nap time. We would have more independence. The elderly and the young would have much more ability. If your grandfather could get into an autonomous vehicle, go to the grocery store, and come home safely, then your grandfather could live in the house longer and more independently than before. And finally, the efficiency of transporting goods and people would improve, which would lower costs, create new markets, and be good for everybody. The 2050 problem refers to the fact that in 28 years, the world population will reach its maximum, which is between 9.8 and 11.2 billion people. We are currently, this is a dated slide. We've now crossed 8 billion, and the carrying capacity of the planet is only about 1 billion. Global warming is hard to forecast, but climate scientists say that in 2050, parts of North Africa, the Middle East, India, I'm sorry to say, and South Asia will regularly experience summer temperatures between 120 and 125 degrees. in centigrade, that's like 50 degrees. And autonomous vehicles are one of the few technologies on the horizon that have the potential to meaningfully reduce carbon emissions while maintaining relatively high standards of living. People are concerned that people will be reluctant to adopt autonomous vehicles. I question that, but I am also time limited. I think I only have 2 minutes left, so I don't want to go into details on this. There are 6 levels.
David, you have about 15 minutes left. You have 40 minutes to talk.
I have 15 minutes left? You are wonderful. Thank you. Okay. Then, yes. There are concerns that people will be reluctant to give up control of the vehicle. There's going to be a complicated situation in which you have some vehicles under AV control and some vehicles that are under human control, and that's mixed fleet period is going to be really bad. There are regulations and insurance implications that we have not really confronted yet. The U.S. is moving ahead a little bit on those frontiers, but there's still a lot to be done. We need to worry about cybersecurity, because if somebody could hack a vehicle software, it could cause catastrophic accidents. And clearly the rise in autonomous vehicles would create economic disruption. Truckers, cab drivers, a number of economic sectors would be impacted by this. And I hope that we evolve a system of governance that is morally just and ensuring that people whose lives are disrupted by this type of progress are not deeply disadvantaged. So there are 6 levels of AV automation: no automation, software assistance, partial automation, conditional automation, high automation, and full automation. And with level 5, the driver goes to sleep after inputting the destination. And Waymo is currently testing such vehicles in Arizona and Utah. It works on traditional roads. It fails when you try and go off-road. And then the 6th level is full automation. That's not on the horizon. So I am mostly interested in we'll get there in a moment.
1 minute, excuse me, what is Waymo?
Waymo is a company in the United States. It is a branch of Alphabet. It's used to be owned by Google. It was spun off under a company, Alphabet, that owns both Google and Waymo.
But you might have heard stories that many people driving Tesla have had accidents because they fall asleep. A Tesla is not perfect, I suppose. That may be the reason.
You're exactly right. Yes, and that's terribly important. Tesla, Waymo, Uber, and Ford, and all the major companies are trying to develop autonomous vehicles. And when you say that many Tesla drivers have had accidents, the actual reality is they have fewer accidents than they would if they were driving on their own. So Teslas, despite the bad press, actually turns out to be generally a bit safer than human beings. I'll provide the numbers for that in a moment. AVs have been around in science fiction for decades. Red Whittaker at Carnegie Mellon sort of started this game going in 1995. He put a computer in a small truck, and that truck drove from Pittsburgh to San Diego, and 98% of the journey was autonomous. He did some other stuff, but his student, Sebastian Thrun, then left and he led the development of Google's, now Waymo's, self-driving car. Waymo is owned by Alphabet and was spun off from Google. It runs a commercial fleet of level 5 vehicles in Phoenix, Arizona. And Volvo, Tesla, Audi are also testing these level 5 vehicles. And 29 states out of the 50 in the United States have passed laws that permit autonomous vehicles. So things are changing, and they're actually changing pretty quickly. Here we see the results for level 4 and 5 autonomous vehicles, and these have conditional control and high automation, and we're looking at the number of miles that have been driven by these level 4 and level 5 vehicles. So we're seeing we're getting a lot of miles coming in. In the US, there are 1.18 fatalities per 10 to the 8th human-driven miles. There have been 4 fatalities with level 3 vehicles, which is the Tesla style. There's 1 with the level 4 vehicle, which is the Uber style, and there have been none with level 5 or 6 vehicles. And the number of miles driven by level 3 or higher autonomous vehicles is about 10 to the 9th.
But the question is, how many vehicles have been driven at level 5 or 6?
You're quite right. That's an important question. There are virtually no level 6 vehicles yet. There are some that are in prototype stages.
This is a wrong statement. Then you should remove the level 6 there. Then.
Well, there's some out there, but you're right. I'm pushing. I'm looking at level 3 and higher. And
this shows I'm enjoying your talk.
Thank you so much, and I appreciate the feedback. I enjoy the interaction. If we're looking at level 3 and higher, then it's clear that level 3 and higher vehicles are safer than the human-driven miles are. So I think we can do very much better than this. In particular, if we get into a situation in which all of the vehicles are under joint control, then I think we can drop the fatality rates down from, in the United States, about 45,000 people per year, down to a few hundred per year. And that's going to be from really strange accidents, like a deer falling off of a mountain and landing on top of a car. That's the type of thing that is hard to protect against. So if autonomous vehicles drove as safely as humans, we would expect 12 deaths. Instead, we had 5. So these vehicles appear to be safer, but the risk analysis for this is still complicated. For example, it may turn out that the AV is safer under normal conditions, but the human is safer when it is snowing. And we just have to work out how this works. And statisticians are exactly the right people to do the risk analysis in these complex situations. All of the AV developers use deep learning. The Tesla Autopilot hardware V2 uses NVIDIA Drive PX2 software hardware. It has input from 8 different cameras, and it has something called Inception 1 architecture, a deep learning architecture, to train a convolutional neural network that tells the car what to do. And this involves a lot of training data, and even then you have problems. There was a case in which putting a Post-it note on a stop sign fooled the AI into classifying it as a billboard instead of a stop sign. These are known problems. People are working on them. Solutions are coming up. For example, if you train a deep learning neural network, you wind up at a local minimum. You don't typically wind up at a global minimum. So if you train a deep learner 3 times, you wind up getting 3 different local minima. And so you can imagine a situation in which you have 3 deep learners as your software. And if one of the 3 does not agree with the other 2, then the vehicle automatically turns control over to the human being, who recognizes the Post-it on the stop sign, realizes it's a stop sign, and does the appropriate thing. So there are many solutions here, but I want to point out the problem. From a statistical standpoint, in the context of AVs, there are 3 obvious areas where we can make contributions. We want to perform a continual risk analysis of safety, both for the changing mixed fleet scenario and for the case of networked control. So if everybody is driving, or if a lot of people are driving in AVs, we want to monitor safety continually. And statisticians can develop systems to do that. Secondly, we need to validate the deep learning training of the AI system that controls vehicle operation. And that includes protection against adversarial perturbation. For those of you who are in the business, there's all sorts of adversarial issues that come into training a deep neural network, and we are starting to have solutions to these, and statisticians can contribute. Finally, the onboard software in the vehicle will need regular updates. So the software quality control will be required, and we've worked on software quality for decades, and this application is going to have some novel features, but that's a research challenge for our field. And all three of these topics are going to entail collaborations with other people. And in particular, we need computer scientists, we need transportation engineers, we're going to need policy experts that advise regulatory agencies. But the potential advantages from moving into this field are so huge in terms of saving lost lives, reducing pollution, creating social freedom, that we really just have to move forward as quickly as we reasonably can. So now let me talk about conclusions. Manufacturing industries were revolutionized by the quality control movement. And we are now in a world where the manufacturing industries are secondary. Information technology industries are where the future has to be. And we need statisticians to tool up in order to address the problems that arise in the information technology world. We have a lot to contribute, but I emphasize that we're probably not doing a very good job yet. Our master's and PhD programs are not producing graduates with the relevant skill sets. I don't know about your universities, but in my department, we do not teach Spark. And Spark is essential if you're going to be doing any kind of big data analysis. And both of the applications that I talked about, computational advertising and autonomous vehicles, rely sensitively upon big data. And if a statistician doesn't know how to program in a Spark environment, they really cannot contribute. Similarly, PyTorch and TensorFlow are two tools that are used to train deep learners. And deep learners are also essential for both of the areas that I have discussed. And so if we're not teaching that in our graduate courses, then our students are disadvantaged when it comes to contributing to the future. They're going to learn it. They're smart students. They're going to have to teach themselves how to do that. And at Duke, our best PhD students are studying Spark online, or they're taking courses in TensorFlow online. So they're learning it themselves, but we are not teaching it to them. I think our profession has been slow to embrace big data and deep learning and even data science. And I think we need to step back from our old school inheritance from the mathematical sciences of teaching general theory and proving theorems, and instead learn how to solve one-off specific problems in data engineering well. And I can elaborate on that, but I don't want to use up all of my time.
I can put a comment there. We are asking people to change the total culture. That takes time. It's time.
Essential. It takes time, and the time is now. We have to start. For example, when I was a graduate student getting my PhD, I had 3 courses in experimental design, and I wound up learning about partially balanced incomplete block designs with K associate classes. I have never used that tool in my professional career. That's not what we need to teach today. We don't need to do deep dives. We need to do smorgasbord courses. We need to do graduate courses in which you spend 2 or 3 weeks teaching introductory experimental design. get them through fractional factorial designs, teach them about G and D optimality, let them know, maybe split plot designs. And then when they go out and they're working for Google and they encounter a situation where they need to do an experimental design, which Google does all the time, I'll add. Google runs hundreds of designed experiments each year. And these are complex multi-arm banded experiments in which you have changing probabilities on the different arms. Your PhD student will know the keywords that they need to look up in order to learn about the partially balanced and complete block design that's appropriate for their application. Similarly, in Duke's PhD program, we really do not teach cluster analysis. Cluster analysis is an important idea. Cluster analysis is fundamental to collaborative filtering. You want to find clusters of users who give similar ratings in the rating matrix. We don't need to teach everything about clustering, but we should introduce k-means clustering. We should introduce hierarchical agglomerative clustering. And then when students go out in the wild and they actually need to use these skills, they will have the vocabulary they need in order to know what they need to learn. So my hope is that when I teach a graduate course on computational advertising, I can introduce the basics of many different areas of statistics, all of which are pertinent to their future career. And I don't think that we need to have measure theory be a requirement for all of our PhD students. I don't think we need to have stochastic processes be a requirement for all of our students. Some people will always need to know that. There will always be enthusiasm for those topics. But those are not the critical skills that our graduates need to have in order to make important contributions to the future of the world. And I hope our programs will modernize. So those are my thoughts. I would welcome questions and discussion.
I enjoyed your talk immensely, and you have presented a tremendous amount of challenges for people to follow. And okay, I have one question. You had just some numbers in dollars earlier in the slides. Just something like $982 billion. Is that within the United States or is that global?
I think it is global, but I would have to go back and check the fine print.
Okay, that's fine. All right. Anyone else has comments or questions? This is a really interesting, challenging problem. Well, we have what has happened with the advent of fast computation. Things have changed too rapidly for all of us. So we are all adjusting. And David's talk presents new challenges, and we'll keep adjusting to that. And so it's really very exciting talk, and I find it, and very informative. And for young people, they know what they to do if they want to pursue a career in the so-called, I would say, data science or statistics, whatever you call it. But that's amazing opportunities right now. I invite people to ask questions. We have plenty of time. We have about 5 to 10 minutes. 5 minutes at least.
Let me thank you for being such a gracious host. I really appreciate the interaction, and I appreciate your comments and the fact that you question what I'm saying. That is wonderful.
Well, David, you always I've enjoyed talking with you, and I listen to your talks all the time. So it's a pleasure.
Thank you.
All right, let's see if some other people have questions or comments.
This is Jaya. May I ask a question?
Oh, please go ahead.
Great. Thank you, Dr. David Banks. This is a fantastic introduction to all the problems that are waiting for our junior colleagues out here and others too. The much of the data, when we work with these types of online systems, they are necessarily observational data.
Yes.
And there are people who seek these online resources, and data are available from the people who elect to seek these resources online. So things like recommender systems that push advertisements for them then tend to promote information or products to a particular demographics that are seeking these information. So are there ways to identify where are the other demographics that are seeking this information, and how can we engage them instead of continuing to engage only a particular demographic?
Yes, that's a wonderful point, Jaya. You're exactly right. Google knows a lot about us. Google knows our age, our gender, where we live, how much money we make, a lot of other things. And so Google has the ability to do designed experiments in which they target non-standard demographies in order to see how, well, for Google's standpoint, how an ad works. But you can imagine that there's more general information that might be obtained. Well, this is not directly to your point, but I think it's an interesting aspect that is adjacent to your comment. Google can write a contract to show Papa John's ad to 100,000 people who live in California who are males between the ages of 20 and 50. It can write another contract to show an ad for Little Caesars Pizza to 200,000 people who live in Northern California who are between the ages of 15 and 60. The demographics in those ad contracts overlap. And so when somebody logs in and Google decides to display a pizza ad, which ad should they be shown? That's an optimization problem, and it relies upon knowledge of whether or not a 60-year-old male in Northern California is likely to click on a pizza ad, as opposed to an 18-year-old male in general California. So that's predictive inference, but it also involves an explore-exploit type balance in which you want to learn about the probability that different demographics are going to respond to a particular ad. So there is a lot of statistics under the hood in trying to solve that problem. And right now, I have former students who are now working at Google, and they assure me that they are not solving that problem the way a statistician would. They're solving it the way an engineer who has a problem, who needs a quick solution, would solve it. And so I think we have real opportunities for contribution there.
Yeah, thank you. Yeah, that's definitely it's a challenging problem, but it is being solved in different ways, as you said. At the same time, yes, Google knows a lot about us, and there are all these data we provide when we access different sites, but there is also a concern from the public about their privacy.
Yeah, may I ask you to remit your question, because what other people may ask question too.
Yeah,
Thank you.
Yeah, so it's more in terms of, we also have, in pursuing these types of work, there may be also a responsibility of engaging a trust in data or trust in science by the public.
You're exactly right. It's a complex problem. Privacy is an important issue, and many different stakeholders are addressing that. I will remind you all that privacy is a relatively new expectation. Before 1900, you lived in a small village and everybody knew everything about you. You really did not have privacy. It wasn't until you could move to a large city that you had any hope of living anonymously and having privacy. Now,
I'll add to that. Your neighbors always know what's happening in your house.
That's true. Yes. So,
okay. Anyone else has a question or comment? So I have one comment, David.
Yes.
I think you may say we don't need major theory and all that, but I think we need a person well trained to be able to face all kinds of situations. So graduate education has to be real education, not to train them for a particular skill, but give them basic ground education. Give them education in major theory, but give them also in data analysis and machine learning, whatever they need. But you got to have some sound education.
I agree. We want them to have enough tools to be able to master whatever problem they encounter. And I worry that our traditional training has not kept up with the evolving demand, the evolving
things
need.
have happened too fast. Things have happened just too fast.
Statisticians were not at the seat, not at the table when deep learning came along. And that's clearly an important thing. So,
okay, we'll try to close this. Let's see if anyone else has any comments or questions. All right, I would like to immensely thank David Banks for some beautiful presentation and offering young people possible challenges, come up and save some, save the world. There's a possibility to do that. So with his problems mentioned there, very interesting talk, very nice topics to talk about. Thank you, David, again. It's good to talk to you. And I'm going to therefore close the session of this comment.
Thank you, Hira.
Yeah, bye.
Thank you, Professor David, for your wonderful talk. In fact, everyone interested, very interesting talk. And in fact, we are grateful to you, Professor, for your spending your time, valuable time for us this in this way.
Satish, you are so gracious. It is always a pleasure to talk with you, and thank you for inviting me to speak.
We are always grateful to you, Professor. And also, we would like to extend our gratitude to Professor Hira for chairing the session and making that session very vibrant. Thank you, Professor Hira. Thank you so much.
You're welcome.
Now let us move to the next session. Professor Lahmander and Professor Naufal is also there to chair the session. Okay, Sangamitra, please.
Yes,
Sangamitra, yeah, please introduce the chair briefly and support him for carry out.
A warm welcome to everybody present here. I welcome you all to the technical session 19 with session chair Dr. Naufal Esa. He completed MSc and MPhil in mathematics and did his PhD from University of Kerala. He is currently working as an assistant professor in the Department of Mathematics at CUSAT, Cochin. His research areas include wavelet analysis, framelets, numerical solution to PDEs, functional analysis, representation theory, differential geometry, and signal processing. He has done many publications at several presentations. He is a part of the doctoral committee of Indian Institute of Information Technology, Kerala, and APJ Abdul Kalam Technological University. He has worked as an assistant professor at several educational institutions. We are very honored and happy to have you here with us for chairing the session today. Without any further delay, on behalf of the whole organizing committee, I once again welcome Dr. Naufal sir to kindly chair the session. Over to you, sir.
Naufal, it is not.
Your voice is not audible.
Yeah. There is some problem with the audio. Would you please switch off that? Yeah.
Hello. Yes, it is now. It is.
Yeah. Yes.
Okay. Okay.
I can hear you.
Hello. Okay, Naufal. Okay, Naufal. Now it's okay.
Okay, now we can hear you. Please.
Hello. Hello.
Yes, yes, we can hear you.
We can hear you.
Yes. Hello. Yeah. I would like to invite Professor Lahmander, Peter Lahmander. He's a professor of Management and Economics Optimization, Forest Economics, SLU, Sweden. I invite with all gratitude Professor Peter Lahmander to deliver his talk. Sir, over to you.
Thank you very much for this introduction.
I will try to show my screen. And I think here, can you see it? Can you all see my screen?
Not yet.
Not yet.
Okay. Okay. Please tell me when you can see the screen. I'm showing my screen right now.
We do not see it.
Okay. Okay. In the chat window, I sent the link, the web link to my presentation. So that's an option if.
Yeah, whether we need to present from here, person.
Okay. Can you see the link and can you get the presentation?
Yeah, boss.
Okay.
Now we see it.
Now you see it. Okay. Thank you. So then I do like that. Okay. So now you see the first picture. If someone sees the first picture, please tell me.
Yes, we see it. Rational control of global warming.
Okay, thank you. Well, thank you very much for inviting me to this conference. I'm very happy to be here, and I've been in some of your earlier conferences also, which has always been very interesting for me. So I will talk about rational control of global warming dynamics via the CO2 level, emission reductions, and forestry expansion. And as we instantly realize, statistics is one part of this, but not every part of it. So I think this was very inspiring to listen to David Banks a few minutes ago, because he also talked about problems where the statistics is a part of the big problem that should be solved. And what we see in the picture here is the ppm level, the CO2 concentration in the world from now, 2022, until 2100. And as you see here, you have many options. We can create the future we want. It's just a matter of actually selecting the right way to handle the global warming problem. And we will come to this in a few minutes. So please take the next picture. This presentation is based on the original version of the contents presented in the following open access article. So this is published and everything is okay. However, there are some equations that are not correctly presented in that publication. So if you want to see the correct version of these equations, which I hope, then you have them in the link in the bottom of the page. And there you also find the appendix that is also missing in the journal publication, unfortunately, but hopefully it will appear also in the journal publication soon. Please take the next picture. And that's the abstract, but I will just show this and you can look at this later if you want. I will talk, so please put on the next picture. So I will talk about the following things. First, the differential equation of the CO2 concentration in the atmosphere. We will look at fundamental theory, mathematics, and statistical estimation. Then we'll look at the time pass of the CO2 concentration, and this will be determined without and with arbitrary industrial emissions according to the estimated function. And then we look at historical CO2 observations, and we can see that the model can reproduce these almost perfectly. We will look at the CO2 concentration equilibrium and see that this exists, it's unique and stable. And we'll see how we can use forests in this process in the world to stabilize the climate. And we'll see that intensified sustainable forestry can reduce for future CO2 concentration. And also, the optimal forestry intensification level will be determined as an explicit function of all the parameters, including the parameters of the CO2 differential equation. Please change picture. And here we see the CO2 concentration in the atmosphere in the unit ppm, parts per million, according to the observations from the Mauna Loa Observatory. And this is a volcano in the Pacific, and there they have this longest time series that exists of this. And I show it from 1990 until 2021, because this is a period, the latest period, where we also have industrial emission statistics. Please, next. And of course, we can transform the concentration in ppm to gigatons CO2 in the atmosphere. And this shows this. Please. Here we have a very, very fundamental and simple differential equation. And I discovered that this very fundamental principle that you see here actually can be very useful, because it's understandable and it works well with the data, and we'll see how this will be used very soon. So essentially it says that the time derivative of the concentration is a constant. You can think of natural emissions from volcanoes and other places on Earth, and you have concentration as x, and b is a constant that shows how much is absorbed by the sea and the other parts of the environment. And of course, A should be strictly positive, because we have volcanoes, they emit CO2. And also, the simple idea is that if you have higher concentration, you have more molecules moving around in the atmosphere, and they will touch the surface of the ocean more often. So the absorption in the ocean and other places in the environment is an increasing function of the concentration, which means that B should be strictly negative. So if you have more up there, more goes down to the sea. Okay, and then in the next equation that you see in the bottom of the page, we see the same thing, that the time derivative of the concentration in the atmosphere, x dot, is A plus bx plus f of t, where f of t denotes industrial net emissions. And this information is, as I mentioned, available from 1990 and onwards. And we'll look at this on next page. Here we have empirical data and transformations. And the interesting thing is that all of this data is available for free in the internet, both the statistical data of emissions and also the concentrations and so on. So the data here is what I used to construct everything I needed to do this analysis. Please, next picture. Here you have the blue graph in top. That's the industrial net CO2 emissions to the atmosphere per year. And then you have the change during 1 year of the CO2 level in the atmosphere, and you see that the change during 1 year of the CO2 in the atmosphere is less than the industrial net CO2 emissions, which means that some part is obviously absorbed by the sea and other parts of the natural environment. So in the bottom you see the change during 1 year of the CO2 level in the atmosphere reduced by the industrial net emissions, and these negative values also have a negative time trend. More CO2 is absorbed now than earlier, most likely because of the increasing CO2 level, which obviously follows the ideas in the differential equation that we saw in the beginning. Next page, please. So here we have in equation 8, we have the equation that we talked about earlier, and in 2, we have the equation with the industrial emissions included. And in 3, we see that we can move the industrial emissions to the left-hand side and change sign. So then we have y as a function of t is x dot minus f. So we can simply estimate y as a function of a and x. Please, next picture. And here we see the simple regression analysis of this, where all of this time, these data points were used. And we see that we have coefficients that are, they have p-values well below the 5% level. And so we will use these values in the rest of this analysis. And this was measured in, here we measured everything in gigatons. Next picture, please. Here we see the graph of the X level, and we see the change in the atmosphere, and we see the strictly negative trend as we saw before, and we also see the variation in data points. This is exactly what we expected in the beginning. Next. And here we see the residuals, and they look fairly good, I think, from a general point of view. There is no heteroscedasticity or anything like that. Thank you. Next picture. And here's the same regression made in ppm, and everything looks exactly the same. It's just a scaling factor here. Same p-values and everything. Next picture, please. And here we see the graph of the function, and we again see the residuals around that in the next picture. And here we have the residuals, and they look good again. Next picture. So we have table 1 and table 2. We have the estimated values of A and B for the different units, gigaton per year or ppm levels. And again, we see the p-values and standard errors of the parameters.